Fernando put Professor Niall on stage for us.
Already online, the online meeting is already being recorded. So Professor Niall, can you hear us?
Yes, hello, can you hear me?
Yes.
Yes.
Good morning, Niall. Welcome to our Summer School 2025. The floor is yours.
Good morning, Janice. Good morning, everyone. Thank you so much for the opportunity to provide some opening remarks. It's really wonderful to share this opportunity with some distinguished guests and with all of the people taking part in this summer school. So if you can hear me correctly, hear me okay, I will give my remarks. Great, thank you, Janice. So my name is Niall McDonough. I am coordinator of the OKEANO project. Just to give you a little bit of background, OKEANO is a 3-year project funded by the European Union. And the purpose of OKEANO is to provide coordination and support to the All-Atlantic Ocean Research and Innovation Alliance. This is for a wider understanding of opportunities and the need for sustainable management of the Atlantic Ocean through a large-scale basin effort. So your summer school, this wonderful summer school, is taking place in the context of this quite long-established All-Atlantic Ocean Research and Innovation Alliance, where we have 12 plus years of engagement and growth in our collaboration in our scientific activities to help us address common ocean challenges at the Atlantic Basin scale. And OKEANO is simply a project where the European Union puts some funds, in this case 4 million euros, to enable ongoing support to the broader goals of the All-Atlantic Alliance. And the Alliance itself and the OKEANO project, for us, the key is that we're working collectively with countries and with partners right around the Atlantic Ocean. So we're from Europe, from South America, from Africa, from North America, from small island developing states, and from pole to pole. So it's really an all-Atlantic effort. I should say my colleague, Laura McDonough, who is the project manager, is also joining this opening session and is on the call as well. And Laura is one of our key people in the project. Let me just make a few brief comments in relation to the value of the summer school and the activity that is taking place now this week with you in Brazil, for those of you on the ground there, and obviously some of you joining, some of the early career researchers as well joining remotely. And this very much aligns with 2 of the key priorities of both OKEANO as a project, but of course of the All-Atlantic Alliance more broadly. Firstly, is the Alliance has for many years placed a high priority on building a network and a community of early career ocean professionals, ECOPs for short, as many of you know. This is a really important aspect of the Alliance, and it has become more so over the years. So bringing early career researchers and early career ocean professionals together to work collectively on addressing some of our common ocean science and policy problems and challenges is really important. And I think the summer school is really a tangible activity supporting that agenda. The second priority that is so important for the Alliance is the focus on coastal resilience and the challenges faced by communities all around the Atlantic Ocean in light of climate change, in light of increasing increasing regularity of extreme weather events, sea level rise, warming oceans, changing biodiversity and with impacts on our coastal fisheries. These are really key issues for our coastal communities, and both of these are being addressed by the workshop and by the summer school focus on numerical modeling and data analysis and the application of these tools to coastal reliance studies. So it's taking, those scientific and building that scientific capacity that we need to build to address real life challenges for coastal communities right around the Atlantic. So the summer school is a really tangible activity to provide expert learning opportunity for our early career scientists from many countries to address these challenges. Briefly, I'm speaking to you from Galway on the west coast of Ireland. I'm looking out my window at Galway Bay, which leads out to the northeast part of the Atlantic. And here, as right around the Atlantic, we are dealing with those challenges: increasing frequency in extreme weather events, causing problems for our fisheries, for our coastal infrastructure, for coastal tourism businesses. We see the potential slowing of the Atlantic meridional overturning circulation, or AMOC. What could happen in regards to that? How can science inform us more with more certainty as to whether there's going to be changes this century and what those implications would be particularly for the Northeast Atlantic? But ocean currents really affect our climate and our coastal communities right throughout the Atlantic. And we need expert scientific capacities and expertise to address these challenges and how they impact on society and economy. And we also need to work collectively at the international level. These challenges cannot be addressed by one country alone. That's why initiatives like this summer school are so important. And you will be collectively taking on the challenge to address and lead our response. The early career researchers in the summer school will lead our response in the years to come to so many of these challenges, whether as scientists or as policy and decision makers. So I would like to thank, in concluding, the supporting bodies in Brazil for their leadership in setting up this and running this important summer school. IMPO, CMPQ, the Brazilian Ministry for Science, Technology and Innovation, and in particular to all the experts who've given their time to participate in a teaching capacity this week. That time is so valuable to make the initiatives like the summer school a success. My particular thanks to Day1 and Janice Trott on behalf of the OKEANO project, who are working closely with us in OKEANO, for all your efforts, and thanks for inviting us to be part of the opening of the summer school right now. And finally, just to say, in a few weeks, a large community of stakeholders linked to the All Atlantic Alliance will be meeting in Brussels, and that includes, again, a new cohort of early career ocean professionals, and will include a new cohort of early career ocean professionals from many countries around the Atlantic. I'm sure the success and the work of this week's summer school will be communicated more broadly to the All Atlantic community there, and I'm looking forward to making sure that there's a wider audience appreciating the work that's been done with you this week. So on that, I will conclude. My thanks again for the opportunity to be part of the opening remarks. I wish you all a very inspiring, energizing, and successful week of learning together. Thank you.
Thank you very much for your time, Niall. Yes, we do believe that we will have good reportings in Brussels in 2 weeks' time. Thank you so very much. So without any further delay, let's please check the video that we have received from the president of our National Science Council, CNPQ, that co-hosts this meeting with us at INPO and LAMSI. Professor Landau will have an opportunity to address the floor as well. So could you please get the video? Rolagem. Thank you, Professor Galvão. And now I turn the floor to Professor Luis Landau. Professor Landau is the, how do you call, coordinator, director, president?
No.
For me, you're president. Well,
Okay, people. Yeah, okay. Good morning for everyone. I'd like to say welcome. I'm so happy to second time be together with you, with my colleagues, Luis Paulo, not João Paulo, and Lydia. I'm sure that it will be a very, very nice, very great course because the first one was, and the second is moving. No? So welcome. I think that part of the course will be done at Lancy.
Yeah.
And I think that you will have the pleasure to know our facilities. I think that everybody will enjoy. Have a nice week with us and welcome.
Thank you. Now I pass on the floor to Professor Sejan Stephan, our Director General. Unless Francisco would like to say a few words on behalf of Dr. Nadia Pinardi.
Okay, so yeah, we are very happy to be here. Nadia invited me and Rodrigo from his school. We enjoyed to training. We made several training in the last few years, and to share our work, our tool that we can use for, I think, very testing for what we want to do for reciprocal experience. I'm a scientist at CNCC and work in numerical modeling, and me and Rodrigo and Nadia, I'm very happy to be in this school.
Thank you very much for your presence. Professor Sergei, please.
Yes, we are very happy to have you here in this week. It's representatives of 12 countries are here. This is very important for us, and it's very important for the mission to preserve the oceans together, and especially the modeling of resilience. It's very important for the scientific studies related with ocean and coastal aspects related to climate change. This course has been organized in a joint venture involving the OKEANO CNPq, that is a Brazilian Council for Scientific Research, and IMPO with the support from LANCE, that is our lab from the University, Federal University of Rio de Janeiro, COPE, the lab, computational methods for engineering. This is a very qualified lab that will give the support here in this week for the simulations and different applications related to coastal resilience. It's my great pleasure to have you here, and we hope this interaction will continue, not only with us, but among you, because you, as I mentioned, represent 12 countries. The interaction during this week, and this will be a strong support for all the future studies that will be involved. Thank you very much for being here, and I hope you enjoy not only the course, but also our city of Rio de Janeiro, that is very beautiful. I hope the weather improves and you can have the chance to know better our city. Thank you very much.
Professor Sergei, I believe that we can do a round tour for you to introduce yourselves. I'm quite positive that some of you have already met at the hotel before, but let's formally do it. So I can start with you, José Maurício.
Well, so I'm José Maurício. It's a pleasure. I am from the south of Brazil, and a state called Rio Grande do Sul. And I'm doing right now my master's on applied mathematics.
Good morning, everybody. Nice to be here. First time south of the equator, first time in Latin America. So I'm really happy to be here. The weather is fine. I am a physical oceanographer. I teach oceanography at the University of Law.
My name is Deb, originally from Myanmar, but I'm doing my PhD in Spain, south of Spain. And my PhD thesis is focusing on how the beach geomorphological change in case of climate change. Nice to meet you.
My name is Maria Luisa. I'm from Brazil, El Salvador, and I just began my PhD. So I don't have a project right now. So we had, but we like changing. So now I don't have a project, but I just started my PhD.
I'm Beatriz. I'm from Brazil, and my master's using remote sensing to analyze chlorophyll and solids in water. Hi. Okay. And environmental scientist.
Morning, everyone. I'm Thaisa Jassen. I'm from Maranhão, Brazil, and my PhD is environmental science. I study how climate change affects the coastal areas, and that's it.
So hello everyone, I'm Haja Idmoussi, I'm from Morocco. It's with a great pleasure to be here and to intern personally and to be being selected in this advanced summer school. So I am I have just defended my thesis, my PhD. So now I am searching for postdoctoral opportunities and also preparing for a new project. My PhD was about biodiversity, ecology, and dynamics of along the Moroccan Mediterranean coast, and also at a broader scale in the Alban Sea. And the new project will be about all the Mediterranean Sea, and it's a multi-scale biodiversity project. So nice to meet you all.
Thank you. Fernando, José, and Carla, please introduce yourself as well. You're not ECOPS, but
Thank you for the opportunity. So my name is Fernando Monteiro. I am the coordinator of infrastructure and operations here at INPO. And background is that I am a retired captain from the Brazilian Navy, and I dealt with oceanography alongside with Professor Janice. And now I'm here to try to contribute to the oceanography in our country.
I'm Carla Lage. I'm also a captain from Brazilian Navy, retired. I'm also PhD in computer science. I work with Dr. Janice and Fernando in infrastructure section as analyst of technology. And this is a new tool for us because we try to improve, and then we still adjusting to because we just joined the RNP, it's our research network. Then we are trying this new tool. I hope that you enjoy because it's much better than Google Meet.
can we move on? Yes, please.
Hello, so my name is Ihan. I'm from Morocco, and I am a PhD student. So my PhD is in marine ecology. I focus on socio-ecological interaction in the Moroccan Atlantic ecosystem, and how fisheries can interact with marine ecosystem, and how this knowledge can support marine spatial planning and conservation biodiversity conservation. Thank you.
Good morning, everybody. Thank you, first of all, for having us. My name is Rabah Memo. I'm from Morocco. I'm a master's student in biodiversity, environment, and sustainable development. And I'm hoping and aiming for a PhD in marine biology.
Well, hello everyone. I'm Guido Bassino from Argentina. I'm a research assistant in the University of Mar del Plata. And I work at morphodynamics on each system.
Good morning, everyone. I am Annabelle Maru. I'm originally from the Philippines, and I did my master's in physical oceanography. And now I'm working in Belgium as a researcher for for remote sensing. So we did the validation of the satellites and water quality monitoring in Belgium. I'm working in the Royal Belgian Institute of Natural Sciences.
Hello everyone, I am Rodrigo. I come from a background in engineering, then PhD with mechanics, simulation of turbulence. And since 1 year I joined CMCC and I work with Francesco Trotta and Professor Bernardi in the advanced modeling of with downscaling applications. So we'll be handling the session of tomorrow, organize information with a hands-on session.
Morning, everyone. I'm Gabriel Pugliese. I'm from Salvador. It's like northeast region from Brazil. It's my first time here, and I'm an oceanographer from in Bahia. And now I'm the weather forecast professional responsible in civil defense of Bahia. So I'm the guy doing the weather in Bahia and the northeast region. And that's it.
Good morning. My name is Mohammed. I'm coming from Morocco. So this is my first time here in Geneva. So my background, I have a master in sustainable blue growth from the University of Trieste in Italy. Then I got my PhD thesis in basically numerical modeling and custom management areas. So I used to work with some numerical models to simulate the dynamic condition changes and their impact on coastal environments like most estuaries of coastal areas. So thank you for providing this opportunity to us, and hope that we enjoy this project. Thank you.
Thank you for coming. And now, the two most important people in this room, please, Luis Paulo and Delane, Luis Paulo, and Livia, could you please stand up and introduce yourself?
So I'm Ejilene.
Everybody knows you.
I sent many emails to you all, but I'm not from the ocean area, but I'm from the international area. And my job here, following what Niall said to us, is exactly to bring different stakeholders all together to think on the best science to face the problems that we have on climate change, especially with our big ocean. So that's my job here. I think you have different backgrounds and from different countries. So I hope you have a wonderful week here with these marvelous people from our National Institute of Ocean Science. They are the best we have. So I hope you have a very, very, very productive week. Thank you.
Hello, good morning for everybody. My name is Luis Paulo Assad. I am an oceanographer with a degree in physical oceanography and a doctorate degree in civil engineering with application in environmental issues. I'll be here with you during this week, not only teaching, but as I saw, learning with you also. And it's very nice to see that you have a very multidisciplinary approach here in our table. This is very important for the coastal resilience facts. So I think it's going to be a very productive week. And that's it. In some minutes, we'll start our course.
Morning, everyone. My name is Livia Son. I follow one of your structures. As everybody said, I hope hopefully you'll be very welcome here. We have a very productive week, and
Acho que pode ser, né?
Não vai. Não senta lá no lugar que nós vamos da live.
Eu te faço
Rodrigo, if you wish to sit here, you're welcome. You're not an eco.
Fair enough. I can put them away from here. Chairs because like I was trying to not appear on the camera because I
Why not?
Because I understand this is the chair.
This is part of the process of getting involved.
Okay, so I think you should sit there now. Okay.
Vivian. Vivian. You have to stay there, yeah. So our mentors have to be together, changing the slides, so.
Que nós damos 15. Então vou te dizer. Então será mais interessante. É que o meu tá fácil, né? Eu vou café.
Yes, yeah.
Can we start? So again, good morning for everyone, and good morning for the online people also too. Good morning from Brazil, of course. I will start saying the following. I will pass the floor to Vivian because she want to do the first words, trying to present our typical day here in our course, and then I will start with our course overview, introduction, and contextualization. Okay? So Vivian, please start and.
Hi again. So our typical day here is have 3 parts. First block, the morning block, starts at 12 a.m. UTC, 9 a.m. for those here. Theoretical lectures, and 30-minute break. Okay, then we go to lunch, a 1 hour break lunch. And then the second block at 4, with 4 hours kinds of, starts at 5 p.m. UTC for those remote and 2 p.m. for those here. We have theoretical lectures or practicals. We're gonna have a hands-on session on Wednesday afternoon. Okay. And of course, minute break at the end.
Vivian, can I just confirm that we have 2 group pictures? One today.
Okay.
Shortly after lunch, it's Professor Nadia Pinardi.
Even better.
And the one on Friday.
Okay, even better. The more the better, the better.
Yeah.
Okay, so maybe on Friday we can do with the remotes as well. Group picture with everyone. Okay, so eligibility to earn the certificates. For those on site, I don't think you're gonna have much problem with that, but for those on remote mode, we ask to attend a minimum of 70% of classes. And of course, fill out a post-course form. And we're gonna try to, at the last day, to give you like 10 minutes before the ultimate end so you can fill out the post-course form. Okay, so this is a thing I really like to do to create a welcome environment for everyone. We just have 3 rules, very simple ones. First one, be kind to your fellow attendees. Not everyone knows everything and knows all of it. Everybody learns at a certain pace, so be kind, be gentle, and create your collaborative environment. You're not here to compete with each other, but to learn with each other, okay? Rule number 2, be kind to your instructors and lecturers, okay? We are trying our very best here to deliver to you the best that we can, but we are also humans and limited, so maybe we won't know certain things, okay? So be kind. And finally, rule number 3, can you guess it? Be kind to yourselves, okay? Things happen. Maybe you didn't get a good night of sleep last night. So I don't know, if you're not feeling okay, go to the bathroom, go wash your face, go get a cup of coffee. You're here to get the most of it. So be kind to yourselves as well, okay? Okay, introductions. I think we did everything, but again, yeah, more than anything, but just to wrap it up, I'm a oceanographer from here in New Energy. I did my master's and my PhD in civil engineering, but with climate change. So I'm a climate scientist, and now I'm a postdoctorate here also in this university. And you would want to.
Okay, that's good.
Floor is yours.
So I was as I said, I was undergraduate in oceanography at the State University of Rio de Janeiro. And after that, I did my master's degree in the Oceanographic Institute of University of São Paulo, dealing with numerical modeling of coastal processes. And after that, I did my doctorate also here at the COPE, that is our graduate program in engineering here in Federal University of Rio de Janeiro. Even though there is a civil engineer, I do physical oceanography also, again, because I work with a global ocean model called MOE, and trying to investigate the impacts of El Nino over the ocean circulation in the South Atlantic Basin. And then I became a professor in 2014 here at the Department of Meteorology, but also I was a collaborator in the graduate program of civil engineering here in the same university. And I don't know how to classify myself as a professional. I'm an oceanographer, but I deal with a lot of things, a lot of issues. Some of them I will show during our course. So today, I don't know if I'm only an ocean professional, because I have to act together with different professionals as you are. And of course, all of you has a communication and integration with ocean and ocean sciences. But I saw that you were graduated in different sciences, so this is very good, very nice for our course. So that's why I rather not classify myself as a specific professional. So let's go. In this first part of our course to 11 o'clock, I think so, we're going to talk about ocean resilience and vulnerability, some basic concepts about this. And we're going to talk a little bit about the investigation methods that we're going to deal with in our course, okay? So we're going to talk about numerical modeling. We're going to talk a little bit about remote sensing and in situ data. Of course, during the course, we're going to be together with some professionals that's needed that will talk about with more detail and more technical detail about these issues, okay? I will only do an overview about our course. So this is our goal, to provide fundamental knowledge, basic knowledge in ocean, atmospheric, climate, computational modeling, and of course, together with some in situ and remote data analysis, with a specific emphasis to attend some demands related with coastal resilience. Okay, so we're going to use a lot of examples here in Brazil. That is very nice because, as you saw, as Professor Sajani showed to you, is a continental dimensional country. Okay, and these are some figures of some issues that we're going to see during our course. So we have remote sensing. We're going to talk a lot about social impacts. We're going to talk about atmospheric process that interact directly with the ocean processes. We're going to talk about the coastal ocean, environmental index, data analysis, ocean processes like waves, tides, okay, and climate change, of course. And of course, this is our very beautiful photo of our city. You are very near this block area. This is Botafogo, that you are in Flamengo, Capete, very near this place. Hope that you have an opportunity to go to some sites. So let's go. So during the morning, we're going to talk about why it's important to study the oceans. I think that everybody knows, but I think it's important to do a kind of normalization of our knowledge here. Ocean service and interaction with humans, coastal resilience is going to be the basic concept in the section after the course overview. So I took this figure from an article produced by Martin Wisnek, a very known ocean professional from Europe. And this is from 2017-18. And this is what we call the sustainable circle of the ocean. So as everybody knows, or at least most of the people of our planet should know, oceans are very important to us because of the many different services that they provide to us, like regulating climates, the habitats and breeding grounds, the capture of CO2 from the atmosphere, support functioning and stability of ecosystems. So the service provides society a lot of benefits, like natural resources, speed quality, safe jobs, energy, food, and different benefits, a lot of different benefits. And this is very important, but as all of you know, we have a lot of threats in our ocean, like climate change, ocean pollution, destruction of coastal and marine habitats, and non-sustainable exploration of the marine resources. So, of course, the United Nations gave to us some years ago a kind of agenda, the 2030 agenda, with all of the sustainable development goals that give us some lines how to keep developing our planet in a sustainable way. So all of these goals are very important, but they must be seen as isolated boxes. They are integrated boxes. We need to integrate the different kinds of science that we develop here in our planet. And this is very important. Sometimes here in Brazil, for example, we have a lot of isolated boxes. Professionals from different sciences don't talk with each other, and this is very important, especially for coastal resilience impacts. So these are some traits, and these are some impacts that you see. So we have, for example, domestic sewage, plastics, industrial pollution, engineering interventions that most of the time are done without any previous studies of their impacts, and of course the climate change. And these are some impacts at the coastal areas. You have the coastal erosion, for example, marine pollution, sea level rise that impacts directly, causing, for example, erosion problems in our coasts, and extreme weather events that comes with the climate change. The intensity of these events and they're becoming more frequent and more intense. And of course, you have a problem because some coastal areas are important, for example, because they have an impact in capture of CO2. And now with the humans impact in these areas, they're becoming, in fact, they are providing more CO2 for the ocean. So this is important for us also to study and to understand how we can take some applications, some better applications to improve these environments. So this is a history around the world about the human-ocean interaction and development of the cities in our planet. So as you see in this map, you have different colors. In red, the most altered coastal regions, in yellow, the altered regions, and in green, least altered regions. This from the United Nations Environmental Protection Agency. And as you see, more than 40% of the global population lives in areas within 200 kilometers of the ocean, and 12 from 15 mega cities are in coastal areas. That's why it's so important for us to study coastal regions. And as you see, related with the population growth, you have the increase also of the shoreline damage. So it's very important for us to understand how to keep with this situation. As you see here in our line in Brazil, you have almost all of the coast in yellow. So we have already very altered coastal regions. Okay, if you see in the most developed countries, as the Europe and North America, for example, have also in red. So a lot of areas that are most altered. So we need to deal with these things. We need to try to change the path of the things that are happening in the coastal areas. So this map show a little bit, we must be animated. Oh yeah, the growth of population in our country until 2010. So as you see, this represents the things that I just said to you, mentioned to you. We have a lot of people and the development of the cities in Brazil near the coastal areas. So we have a not homogeneous growth around all of our country. Okay, and some things. Professor Jean said some things about our country, but it's very nice to show some examples here in Brazil because, as he said, Brazil is a continental dimensional country. So we have a lot of different things in the same place, in the same country. So it's an opportunity maybe in some areas of Brazil, you're going to see some things that are very near the conditions that you're going to find in your countries. Okay, so first of all, of course, more than 70,400 kilometers of coast, very wide coast. We have the 2,000 first kilometers, our economic zone. Okay, and we have the rights to explore the resources here inside. There is called also the Blue Amazon, as Professor Cezin said. And in our country, we have different ecosystems. These are some kinds of ecosystems that we find in our country. We have other different ecosystems, coastal ecosystems that we have tidal plains in the north region of Brazil. They are very important. Sometimes you're going to have for about 60 kilometers of wet and dry regions because of the tides. We're going to talk a little bit about it. We have the one group that are very important along almost all of the coastal area of Brazil. The South Marches here in the south, with groups in almost all of the extension. They are very important for us, even for the coastal resilience of sea level rise. And then you have coastal reefs, of course. You have sand beaches, of course, a lot of urban areas with their problems. Island environments also too, rocky coast, and much other ecosystems, okay? So you're going to have also different economic uses of our coastal ocean. Maritime transports, of course, maritime tourism, not only maritime in the coastal regions, mostly in the coastal regions, oil and gas industry, industrial and artisanal fishing, and now we're going to start the development to go to the ocean to extract renewable energy. So wind energy is one of the things that we are discussing in our country to start. We don't have any turbine over the ocean now to have on land, but we are planning in the next 2 years to start to have. And this will be very important to study also because, as you know, any kind of energy brings their own problems. Okay. And this is very important to say also, talking about, sorry, some words in Portuguese, but I can translate that to you. This is the classification of climates that you have in our country. So as you see, as a continental country, we have 1, 2, 3, 6 different kinds of climates, but at the coast we have 1, 2, 3, and 4 different kinds of climates in our country. So this is very important to understand, of course, because this kind of climates will impact the different environmental forces that act in our coast, okay? We also have different biomes in our country. So we'll have six different kinds of biomes, and you have at the coast the Amazon biome, Caatinga biome, Atlantic forest biome, okay, and even Pampa biome. So these different kinds of biome also will include more complexity when you want to start study the coastal resilience and coastal environment aspects in our country. Okay? Each one responds in a different way for different impacts. This is very important also to say when we talk about coastal resilience and vulnerability of the coast. The social and economic aspects. We also have a very strong inequality in the social economy aspects of our population in our country. So, trying to simplify the things, you have a kind of the regional gradient of socioeconomic with riches and more developed social in the south part of Brazil, and less economic and less rich people in the north parts of Brazil. Okay, of course, this is not so simple as I showed to you. If I go to the state of Rio de Janeiro, this is the map of the city, that the state that you are now, okay, you can see a lot of different complexities, of course. In the same city as, for example, Rio de Janeiro, we're going to see a lot of inequalities regarding the social and economic aspects, as maybe you can see when you came here at the Federal University of Rio de Janeiro. And why this is important, starting to do an approach for our basic concepts of vulnerability and coastal resilience, because this kind of social aspects will be directly related with the resilience that each kind of community that lives in the coast will deal with. So another thing that is very important to say, and directly related with the social and economic aspects that I showed to you, we have in our country, for example, different social, economic, environmental characteristics, as I said. We have different oceanographic and meteorological conditions. This is very important for us to understand, for example, how tide, how winds, and how waves act in different coasts along our coast of Brazil. And we have different ocean observation structures. It's very important. That's why the INPO is so important for us, even is so young. It's very important to understand the structure of ocean observation that we have in our big country and try to integrate and do some strategy in order to try to homogenize, in English, normalize the distribution of ocean observation structure along our country. Okay, so let's go. So let's talk about coastal resilience and coastal vulnerability. I think it's a concept that, even for me, is most important than coastal resilience. And I'll show why. You have resilience that could be classified as the capacity of a system to adapt and recover after being affected by a disturbance. Disturbance that could be a climate change impact, an oil spill accident. Okay? After being affected by disturbance, restoring its functionality and returning to a state of equilibrium. So, of course, resilience is direct associated with different issues, and, for example, the social and economic characteristics of a place. After that, we have susceptibility. That refers to the likelihood, the probability of a natural phenomenon such as coastal erosion, flood, the ecosystem, oil spill, degradation occurring regarding of social or human factors. Okay. After that, you have the sensitivity that represents the degree of fragility of the environment to a given phenomenon. For example, if I'm talking about an oil spill, a mangrove will be affected in a different way than a sandy beach than a coastal rock or coastal rock. So we need to understand the sensitivity, and all of these three things are very important to understand a characteristic called vulnerability. And vulnerability is a function of the character, magnitude, and rate of a given phenomenon and the variation to which a system is exposed. So to understand vulnerability, I need to understand the resilience, the susceptibility, and the sensitivity of a region. Okay? And I need to know what is the phenomenon that I'm talking about. Oil pollution, climate change, weather extreme events, health, all of these things must be integrated. So, what I'm trying to say to you, of course, here we're going to talk more in a detailed way about numerical modeling, data analysis, and most of the data that we're going to talk about is oceanographic data and meteorological data. But we have two oceanographers here, but you must know that other science, like social science, economical science, biological science, are very important to be integrated in order to understand in a better way and a consistent way how resilient a coastal area is. Okay? And that's what I'm trying to show to you here. A multidisciplinary approach. Here I give some of the science that must be integrated in order to understand the resilience and the vulnerability of a coastal area. Health science, social science, oceanography, hydrology, I repeat meteorology here, sorry. But it could be any other science that will.
Very important.
Very important, yeah. let's repeat the Sherlock, no, sorry. And then I approximate ocean science with other science. This is very important. You cannot live in isolated boxes. You need to understand and integrate with other science when we are talking about resilience and we are talking about coastal resilience. So let's start to talk about our investigation methods and talk about, for example, numerical modeling. Yeah, some of the things are important to understand. Yeah, when you want to apply numerical modeling with analysis to study, for example, resilience and vulnerability at the coast. First of all, we need to understand what are the aspects we need to consider to understand coastal resilience. Okay, so I have already shown to you that we have different science that wants to be integrated. So we need to understand what I want to understand. I want to understand, for example, the impact of our oil spill at the coast. But in each way, I need to understand the vulnerability of the place. I need to understand, for example, the impacts in the health of the communities that lives in that area. Now, I need to understand how the mangroves of that area would be impacted by the oil spill. There are different approaches, and depending on the approach, I need to have not an isolated monitoring or understanding, but an integrated monitoring, integrated impacts. I will have the opportunity, I think at the last day, to talk about a very strong oil spill disaster that we have here in Brazil in 2019. The guys from Brazil know very well about this disaster, and it was, of course, not a good example, but a good example for us to show how important it is to understand these things integrated, for example, related with on oil spill. We have problems in different ways. With economic problems, of course, because of the tourism. We have health problems because we have fishers that just go directly to the oil, to extract the oil without any equipment from the mangrove areas. Okay? And we have social problems related to this also too. But we're going to talk further in the class, our classes. We have also to understand the scale of our problem. Okay? We're talking about a problem that is planetary scale, country scale, state scale, or territorial scale. Most of the time, what we have is a multi-scale monitoring, a multi-scale understanding, because the scales, the space scales, they talk with each other. I cannot understand, for example, climate change, a sea level rise that is directly related with climate change, only looking at my region. I need to understand how the remote process of the oceans and the atmosphere act in our area. That's why I have the pleasure to have here Nadia and Francisco, for example, showing to us a very nice YouTube investigation method. There is downscaling, there is the use of surfing now. Rita also will talk about some kind of this definition during this afternoon.
No, not this
Oh, this afternoon? I thought it was.
Thursday.
Thursday, okay. So it's going to be very important to have this kind of techniques that could integrate these different space scales, okay? And of course, as I said, again, these choices will depend on the kind of demand that we want to investigate. Again, pollution, climate change, engineering demands, environmental vulnerability, coastal resilience studies. So talk about directly with numerical modeling methods and the integration of the observations that are very important. So these are two aspects and two investigation methods that we're going to be working in our course. So I will talk of oceanography and meteorology directly, okay? And these are our chosen aspects to understand the impacts in coastal resilience. And what I must say to you, they're strongly coupled. So we have even a science called ocean atmosphere interaction. I am a professor of ocean atmosphere interaction in the undergraduate course of meteorology here at the Federal University. And these two guys are very and strongly coupled. So they need to be integrated at least when it's possible in a integrated way. So we need to have, if we think about observation, the ideal thing is to have, for example, net ocean below what called meteorological oceanographic windows that apply in an integrated way, in the same time, oceanographic data sets and meteorological data sets. It's very important for us, not only to understand directly the dynamics of the ocean atmosphere in an integrated way, but also to feed our models with data that could be assimilated or even could be used to validate our model results. Okay? Please feel free to ask some questions. Okay? And the other thing that is important, as I mentioned to you, is you need to apply some multi-scale approach. You need to use techniques like downscaling, nesting schemes. You're gonna, I think that there are some people that already know this kind of concepts. I know that everybody, I don't know if everybody knows, but you're gonna be normalized with this knowledge. I'm certain about that in the next classes that we're gonna have in our course, okay? And this is some application, grid nesting scheme, no structural grid models. And then you have modeling and observations together. How can we integrate model and observation? In a two-way, basically. What kind of observation I'm talking about? Remote observations and in-situ observation. When I talk about remote observation, I'm basically talking about the satellite data sets that are very important for us that study the oceans. But we have also some sensors that will show you that are remote, but are installed in continental areas, like antennas, high-frequency radar antennas that now is very used nowadays to study, for example, in real time, the ocean circulation, surface ocean circulation aspects. Okay? And in-situ observation, we have different kind of in-situ sensors. I'll show some of them to you. And you have modeling, represented here by atmospheric model, oceanographic models, and climate models also too. There's a different class of numerical physical model, but it's very important, of course, to understand this planetary scale, how the climate works in the planetary scale. And I can use these two kind of things. First, in validation. So there is one error that just points the model to observation. So I had a numerical model result, and then I can compare with the observation in order to see, okay, my model is producing results that agree with the reality that observation gives to me. Okay, so I can have a confidence in my model results and go with my investigation process. And there is another process that called assimilation that must be two errors here, then one error down to model and other error for observations. That is the process that we're going to talk a little bit about. I will explain to you some basic concepts about data assimilation. There's a technique that is used to basically what the model did is to use in an interactive way during the simulation process. They acquire the ocean observation, the atmospheric observation, in order to bring the numerical results to the reality of the observations. Okay, I will talk much better about the concept of data assimilation during this class. Okay, but it's a very important technique that is used to increase the consistency of numerical model results. And of course, now we have data science. Data science is using a lot today, of course, in different branches of research, of areas of sciences, okay? And in ocean sciences and atmospheric science, they could be used with both, with observations and with numerical model results also. The big challenge is because we have a lot of physics in the ocean, and you have to bring this physics to the data science models in order to have a consistency of not only the diagnostic representation, but mainly for the forecast representation. Okay, but data science is also very important. I think that we're not going to present any example of data science model, okay, but we're going to talk a lot about physical numerical model. And these are, now talking about observation data, this are only some example of sensors that we have acquiring meteorological oceanographic data sets. So, of course, coming to the most modern equipment, we have the gliders or the underwater autonomous vehicles, okay, that are just bringing a revolution to observational oceanography, okay. It's very useful. We have some equipment of this here in our laboratory, and I'll show some example of a project that uses this equipment to acquire salinity and temperature data set that was assimilated in our hydrodynamic numerical models. These are other equipment that is autonomous also too, because it's a surface vehicle. Okay, this is a model called Sailboat, but we have different models, and we have also different models for the gliders. And this guy here would acquire, for example, wave data sets. We have sometimes a meteorological station, weather station that can acquire meteorological data. Okay, we have of course the wave we use, like with hiders and other we use that acquire wave data sets that for us in coastal resilience is very important. We have tidal gauge sensors in order to acquire the sea level time series of a region, and of course extract the data necessary to have a good tides forecast for a region. We have the land ocean views that I just mentioned, meteorological oceanographic views. We have ADCP, acoustic Doppler current profilers, that can be used not only to acquire currents, but also time series plots from wave, for example. We have this understand, for example, the space evolution of currents. For example, here we have an example of a map produced here some years ago to understand the dynamics of Brazilian currents, that a very important current that just passes through our southeast coast here in Brazil. Okay, and this is a section produced by the glider that is very important for us because this data could be, as I said, assimilated in our regional oceanographic model, not only to increase the consistency of our surface results, but at the water column also. And this is the satellite, okay? That is a tool with great potential to many different studies, of course. These are some examples of oceanographic data that I think that most of you know very well, that you can acquire with satellites, with temperature, salinity, surface height. Some of this data could be used directly to understand some ocean features, ocean dynamic features that we have in our coasts. For example, we can use the color of the ocean to have the idea of the chlorophyll concentration. The chlorophyll concentration will give us some understanding about some most important oceanographic processes like wetting, like meanders and eddies that we have that are very important for us to understand different things. And talking about satellite, we have basically two different kinds of sensors. The ones that acquire radar synthetic aperture radar images, and the ones that acquire optical images. So the optical sensors acquire, for example, the color of the ocean that could be used for the quality, water quality of a region, or maybe for understand chlorophyll and other processes. And we have the radar ones, okay, that you can, for example, use this to understand if you have an oil spill at the surface. Okay, this is an example. And now this technology is also being used to renewable energy. We have some projects here that are using SAR images to understand and to estimate the wind resource field over the sea surface. It's very powerful tool because we have, of course, bigger regions at the ocean. So the use of satellites is very important. Okay. And of course, all of state data could be also assimilated in our numerical models in order to increase the consistency of the numerical results, and also it could be used to validate the numerical model results. So other things that are important when talking about the coastal and the products that we can acquire in our remote sensing data, satellite data, is, for example, topography, that is very important, okay? And the ecosystem characterization, of course. I will have the opportunity to show a project that we developed in the equatorial margin of Brazil, the north part of Brazil, where we use satellite data to characterize the ecosystem that we have there. Of course, most of the part of the area is covered by mangroves, but we have also sand beaches, urban areas, and this kind of product is very important for us to characterize these coastal ecosystems. That is very important to understand, for example, the susceptibility and the sensitivity of these ecosystems, for example, for noise to accident. Okay? That's okay? My English is okay? Yeah. Let's go. So And this is the guy that I told you about, the high frequency radar antenna. This is the antenna that was recently, 2 years ago, installed in the city near here, Cabo Frio. Yes.
Sorry, just a question. Will the presentations be made available?
Sorry?
Will the presentation, yes.
I was going to say before you start, the presentations will be available.
Yes.
They don't have to take pictures.
I asked because a lot of this material.
I know, I was the same.
Yeah, my students think that this isn't real, but here it is. And if they see it, right, they'll believe me.
Yes, of course. This is this was started antenna in the city of Cabo Frio, the mountain in Cabo Frio Island, it's an island near the city, and acquired this kind of data. And this is also used during, then you have surface current data in real time. It's a very powerful tool. And this was used a lot during the deep horizon accident that you had in Gulf of Mexico. I think that Ana Vaz will talk about this accident further in our course, and we'll show certainly some examples of the use of this kind of equipment there. And we have the opportunity to use these data sets to have data simulation operational numerical model of the ocean circulation in this area. For about 2 years ago, we worked in a project that we simulate this kind of data sets. It's very powerful to increase the volume results. And this is an example of a radar also, but now this is a ship, okay? So we have a shadow zone because the radar is at the day. And this is the wave field that you can acquire also information about the wave gauge field, okay? Another applications of remote sensing, and you have the opportunity to be with Breno Vasconcelos, is our colleague, also geographer, that is specialized in remote sensing and geoprocessing. And certainly he told about some applications like this one. This is a part of the littoral of Bahia State, is near a city called Belmonte, I think so. There's a project that we're at there. And one of the things that we are interested in study is this kind of process that you're seeing in these photos. Having that place a very strong erosion processes, okay? And what we did was to acquire some images, of satellite images, historic satellite images, trying to understand, for example, what's the difference of the coast between 2005 and 2011. So here you have the 2011 coast just projected in 2005, so you can understand what was lost in coastal areas in that area. So this kind of instrument is very nice to understand, for example, the impacts that the coastal erosion in coastal environments, okay? And trying to match these things, for example, of oceanographic, the history of the oceanographic process and meteorological process that you have in that area. So you can understand a little bit and maybe try to separate which is, for example, associated directly with the climate change process and which what part is related, for example, for some coastal process. For example, some people just alter the river flows that goes to the coast and transport sediment to the coast, and maybe they decrease the discharge of the river and then alter the sediment transport to the coast and produce also this kind of coastal erosion processes. Okay, so that's it. And of course, this talk about other area of research is very important. Is geoprocessing techniques, acquiring to remote sensing techniques. You need to integrate these two kinds of science or methods, if you prefer, in order to understand a process like this. And so now, I will try to integrate all of this knowledge that you have here to understand another investigation method or approach to study coastal resilience. I told you about the concepts of vulnerability, susceptibility, and sensitivity. So now I must say to you, I think that some of you know, that understanding the schemes of space and time that you are interested in, understanding the data sources that I have, and integrating the different nature data sets I can have what they call environmental index. We have susceptibility, sensitivity, and vulnerability index. What are these indices? They are basically statistical index that try to integrate different nature data sets, different scales, different sources of data sets in order to understand in space and time how a coastal environment is vulnerable or sensitive or susceptible to a given phenomenon. Okay, so I'll show some examples of this. Okay? So first, the sensitivity index. NOAA, for example, some years ago, a lot of years ago, produced the environmental sensitivity index, for example, applied for oil spill purposes. And basically, what this index gives to us, what NOAA gives to us, is a table with a rank of ESI regarding the kind of coastal environment that have. So for example, mangrove have a very high sensitivity index for oil spill, of course, because of the characteristics that they have, the importance that this kind of environments have. They are very sensitive for oil spill accidents. Exposed rock shore are the less sensitive ecosystem for oil spill purposes because it's easier to clean this kind of ecosystem, for example. And we have different kind of ecosystems here, like for example, sandy beaches, we have intermediate sensitivity index. So basically this index is related with the shoreline classification of the kind of ecosystem that we have, okay? And then you can put the sensitivity index in a map where you can integrate, for example, with the fauna, the animals that fauna and the vegetation that you have in that area. And not only with this, I'm going to show in the next slide, you can have maps of this that you can integrate with the equipments that you have in that area. For example, hospitals that you have, roads that you have to access a different coastal region, or in order, for example, to mitigate an oil spill accident. So this is one thing. And basically, the sensitivity gives to us a vision based only in the ecosystem classification. Then you have, yes, of course, I give an example of oil spill, but I can give an example, of course, related to climate change. There's another phenomenon that's very important to understand our course, okay? So I could say also, and this will be very different because we know that mangrove is very resilient, for example, to sea level rise. So maybe these things will change. So depending on the phenomenon that I want to investigate, things will change. Talking about the susceptibility of an index, is calculated value that indicates how prone an area or object is to experiencing a particular hazard. And then I will start to need another kind of methods to understand very well the susceptibility of a place. For example, again, talking about an oil spill, sorry about a lot of examples of oil spill, but we have some experience in our research group dealing with this for about 20 years. I will show some examples. That's why it's more near. It's near. Okay? But as I showed, all of this could be applied also to sea level rise and climate change purposes. So to understand how prone an area is, for example, for an oil spill, I can do, for example, use numerical modeling to understand in different hydrodynamic scenarios related to hydrodynamic and meta-ocean scenarios, meteorological, so how different winds, currents, tides will act, for example, in a dispersion of an oil spill. So understanding, for example, that at this point I have an oil platform, an oil structure, for example, I can simulate, I can understand the hydrodynamic, how the hydrodynamic changes time and space, and uses this hydrodynamic information of current velocity and direction to fit a numerical physical model that will try to evaluate an oil spill over the sea surface. And then I can understand, for example, in different scenarios, if a place is less susceptible to an oil spill or more susceptible to an oil spill. Okay? So I can combine these things. Sometimes you can have, of course, also a probabilistic approach to a lot of simulations to understand this kind of susceptibility and use this as a very strong tool, for example, to strategies, okay? To apply some strategies to trying to mitigate or even avoid some kind of accident that was alive. And now I'm talking about in sensitivity. I was talking only about the ecosystem characteristics. Now I'm talking about meteorology, economy, oceanography. Why economy? Because I need to deal, of course, with the economy related to the oil transport near the shore. Yeah? What is the probability of a ship carrying oil has to pass over this area? Okay, so there is other issues that must be at the equation in order to understand the susceptibility of an oil spill in a coastal area. Okay, and then comes vulnerability, and now I need to put also social layer in our purpose. So this is a kind of, now I'm talking about an index. Sorry about this equation, okay? But the most important thing to understand here is that the index of vulnerability regarding to, for example, climate change relates geomorphology, sea level change, coastal slope, mean tide range, shoreline change rate, land use, human activities. So now we have economy, social characteristics here, population. And then this is an example I just take from the internet in the India. So we have the vulnerability associated with sea level rise in this area. But this vulnerability index uses all of this information. And here you have not only the oceanography and meteorology related, for example, of climate change scenarios that came, for example, from the IPCC, okay? The climate change intergovernmental panel of the United Nations. And give to us a lot of scenarios, historical scenarios, and disturbed scenarios regarding the emissions of the gases. Yeah? And then you can use this to feed numerical models, numerical visual models, in order to understand, for example, in the local way, the sea level rise, how the sea level rise will impact in a specific coastal area. Okay? And to do that, use again the technique that I told you about, called downscaling, and using nesting schemes grids. I'm going to talk about a lot about these techniques during our talks. And that's it. Understanding vulnerability is crucial for developing strategies to build resilience and enhance adaptation to negative environment change. This is very important because most of the cities that you have, at least in Brazil, okay, I said more confidence here in Brazil. Most of our big cities that are near the coast are not prepared for the new climate scenarios because they were designed 5, 6, 8 decades ago, 100 years ago, some of them, like Rio de Janeiro. And then the scenario that you have, the climate scenario that you have, was totally different than we have now. And of course, will be now it's totally different that we're going to have in some decades ahead. So it's very important to understand and to use this kind of tool that you're going to learn and you're going to hear about some techniques here in our course to understand the impacts in coastal regions around the world, and of course to contribute to the governments to develop strategies to adapt and mitigate. Here are some coastal resilience vulnerability examples. So this is a project that we have in the south region of Bahia State, and called it was Projeto Japi. Japi is the name of birds that we have in that area, very beautiful area in the south region of Brazil. A lot of mangroves, a lot of artificial fishing activity there, and there's a company that was interested in studying the impacts related to oil spill in that area, and the purpose was to monitor the marine coastal ecosystem sensitivity due to oil spill in the southern in this area that I told you about. And to do that, we use satellite remote sensing techniques. Okay, we use together with geoprocessing We use, of course, numerical modeling. We acquire these data sets, I will show a little bit, in order to understand the environmental sensitivity index. But in this case, we didn't work with, how can I say, static environmental sensitivity index. We need to, at that occasion, that was some years ago, this is what not so normal, we need to understand the dynamic of the environmental sensitivity. Because, of course, you can imagine if you have a low tide scenario, you're going to have a kind of sensitivity to oil spill. If you have a high tide scenario, you have a very different kind of sensitivity because the oil goods arrive in different areas, in high tide scenarios. So that's what we have. This is a kind of a methodology that we apply in our project in order to have the environmental sensitivity index maps. Okay. So as you can see here, we integrate almost all of the methods that I just showed in the beginning of our class. Okay. So we integrate hydrodynamic and atmospheric models. We use the in situ data sets, not only the buoys that we launched, the drifters, but also we use some ADCP data. We use geoprocessing with some data that came from satellite to do geological information to have land use. All of these things enter in our equation in order to understand the environmental sensitivity. And then we produce this kind of maps that we're seeing here. And as you see, they are different, especially here you have the low tides, and the low tides, you have some sandbanks here that are exposed. And then the oil could reach them and stay there. And when you have the high tides, you don't have more of these islands. Okay? And of course, you have, as I showed you before, different information like the fauna, vegetation, and equipment.
Sorry, can you say what's the difference between a non-static and anastatic index?
Yes, that's it. This is I think that an events, is it? How can you say event?
Made up.
I think that made up now. What I'm talking about is the following. As I'm showing to you, some years ago, many years ago, we don't have these two kinds of maps. We have people only deals with one map because they don't consider, for example, the dynamic nature of oceanographic process. The tides and the currents are not constant in time. They change in time. So if they change in time, they change the way that they could transport oil at the sea surface. Okay? So this will change the susceptibility and sensitivity of a region to receive this oil. And so you need to work in a dynamic vision. Okay? So I think it's better to use dynamic vision. Okay?
Thank you.
You're welcome.
Excuse me, is it produced during like a real-time scenario? Like
sorry.
The map produced during
in a real time? No. We just need to acquire all of this data, doing the numerical simulations in order to have these maps. In fact, we produced for about 12 maps, 12 different maps. Because we combine different scenarios. For example, we have a low tide scenario with a southwest wind, and we have a low tide scenario with a northeast wind. And so they are quite different because this will impact in the way that the surface field, current velocity field, will work. So we need to combine different scenarios. Okay, and this is an example of two of them. Okay.
So, for instance, there's an oil spill, and we need a forecast of where this oil spill goes to which area. So this came later.
No, this is important. You always need to have, or at least when it is available, when it's possible, to have an operational system to be ready to attend on emergency demands. Okay, this is a problem that you have in the disasters that I told you about in 2019 here in Brazil. But the other thing is you need to have at least prepared with this kind of maps to understand. For example, oh, there was an oil spill. Some people said a ship just threw the oil at the sea surface. Oh, how is the tide now? How is the wind? How is the weather? I go to my map. Oh, so I think that this area will be more sensitive to this one. So I have a strategy to take my team of contingency and just go there that area and not to the other area. Okay, this is a thing that we are trying to be proactive. I don't know if there is this word in English. Yes. Not reactive, but proactive. But of course, as you said, operational systems are very important to not only to identify the oil stability surface, but to understand in real time from where. Of course.
Yes, guys. Think about this is a very big area. If you do not have this information ahead, there's an oil leak. To answer and be prepared to the oil to get in all of this area is just not feasible. So you had an idea during certain conditions of where the oil is gonna go, and then you can put your efforts to protect that coast and not the other one. Okay. Yeah.
Yes, I was curious because this gives much information during high tide or low tide. This is the area that's affected. So.
Yeah, during high tides and the northeast wind and the currents in a certain way, the oil probably goes on to this area, to the north, not to the south. So the efforts can go there.
That's it, exactly. The idea is not to be completely blind in the next attack. So it
Could you validate the model?
yes,
This is a scenario.
this is about it. I think this is a very nice question. This is here in Brazil now. I think to have 1 year and a half, we have a federal law that permits, because to validate an oil special model, you need to do some simulated experiments, some idealized experiment and launch some oil the controlled way at the sea surface to prepare the satellite to acquire the image and to run the model to see if the model is okay. It's the way. Other countries around the world already done this kind of experience. In Mexico, we have the opportunity to participate in an experiment. I think that Norway also. But here in Brazil, it's not allowed since about 2 years ago. Now there is a federal law that permits this, but it's a federal law, and the environmental agencies have a specific organization in Brazil, for example. If I want to do a kind of this experiment here, on the coast of Rio de Janeiro, it's very difficult because the state agents, environmental agents, still don't permit this kind of experiment. So to validate the oil dispersion in Brazil now. So
with the 2019 spin?
Yes, no, you can use the it's not good, of course. This kind of act for us is a kind of laboratory. So we can use the accidents trying to re-simulate, simulate again the condition and see if we are if the simulation agree with the real.
And it's good.
Most of the time. I will show an example in Guanabara Bay. In 2000, we have an accident in Guanabara Bay, a very strong accident. That it was important for us in Brazil because after these accidents, the oil companies and the environmental agencies see in a different way how you must deal with the oil production in Brazil. So we must be proactive, we need to acquire a license in order to produce oil. That's it. But we're going to talk about this further. I'm worried about the time, but I will run. Okay. So this is the downscaling. I will not talk so much about this because we're going to have the class of Livia, you're going to have the class of Francesco also too. But the idea is to bring to the local interested area the remote influence of ocean atmospheric processes. That's the idea, and you will have a numerical physical modeling technique to do that. And how we do that for climate change, for example, we use the IPCC scenarios that are publicly available for us. We have different emission scenarios. These are the RSCP scenarios, but now we have the SSP scenarios. You have climate models, Earth system models, and most of them, all of them produces projections for the future. And we can use these projections to use as what you call boundary conditions or initial conditions, or if you prefer, data input in our regional models in order to produce forecasts in front of climate change scenarios, to understand firsthand the impacts of sea level rise and the winds over the coastal ocean bases. Okay? And of course, it's very important to evaluate the historical climate scenario using available observation and scientific literature information. This is very important because when you want to understand how the climate change will impact in a coastal process or any other process, you need to have a benchmark. You need to understand the climate at the present, and then simulate the future, and then basically do the difference between the future and the present to understand how different we are. Okay? So, and to do this difference, you need to know if you get to represent the present in the consistent way. So we need observation, okay, in different nature.
To validate the data.
To validate the data. Validate your numerical simulation.
Yeah.
That's it. And this is a paper that I produced with now a colleague of myself, but always a colleague, but in that time he was supervised by me in his doctoral thesis. And what he said was a downscaling to understand the impacts of sea level rise along a very wide region in the Brazilian coast. So this is the scenario that she worked with, the RCP 4.5. There is a medium complex scenario. The model has Jane, which is the model, and these are the grids.
Como a gente parou de compartilhar para quem está online?
It's not.
It's not sharing for those who are remote. It's not sharing.
Okay, let's go. So this is very interesting to see because not you guys, I'm certain about that, but most of the people, and you must know that the people that not are involved directly in science, you must know how to communicate with them. It's a very important message because when you see at the journal that the sea level rise will be increasing 50 centimeters. They get scared, of course. Yeah. And you know there is not homogeneous way in all of that. Okay. So as you see here, the RCP scenario along the coast of Brazil, we have different tones of blue. Okay. So this area is acting in a different way regarding the sea level rise. So what we did, the downscaling to understand very well and with more detail how the sea level rise will impact in coastal areas in Brazil. That's what Raquel did using this scenario. This is first the sea surface temperature field, anomaly fields, the difference between 2100, the end of the century, and 205. So you can see here that you have different colors regarding the sea surface temperature increase. So in red you have 2.5 degrees Celsius, and in blue you have 1 degree, 1.5 degrees Celsius. So you can see the increase of temperature in the sea surface, and you can see also the sea level rise. So now you have this scale in meters. So you have some regions with orange, that is 0.8 centimeters, meters, 80 centimeters, okay? The difference between 200 and 1995, in fact. And you see here in Rio de Janeiro, the yellow areas that represent another sea level rise of 70 centimeters in 100 years, okay? So this is now, for all the coastal points, what we have in the first 10 years, 1995 to 2015, there are 5, and then the last 10 years of this century, so we have an elevation rate of 7.5 millimeters per year. And these are some results. I will pass because I think that we are not more faster, okay? And these are some results, and you're gonna have the opportunity to see, and I can pass of course the paper of Raquel. Now, last year, we published this paper trying to see the results in a detailed way for the city of Janeiro. And what we see, this is an area of the, we are here, okay? We are in this island. So here is the bottom of the bay, Guanabara Bay. This is the simulation that represents the process of tides over the mangrove tidal plains, okay? And this is the percentage of flooded area. So the present scenario, we have these colors, and these red colors represent that these areas are not all of the time flooded. Of course, we have the tides in the present scenario, but in the future scenario, we have all of this purple area. That is the permanent area flooded. Okay, so this is what happened in an area where we have where we don't have mangrove is the city area, the down city, okay, of Janeiro. And then what you have is almost impossible to see this gradient of colors because you don't have tidal plains, and you have urban areas. So when you can see the difference, and I can say, if you look at Copacabana, each will be flooded in for about, estimate, of course, is 100 meters ahead. In this scenario. So, of course, this is very important to say. I'm certain that people that will deal with numerical modeling in our course will talk about, but numerical modeling will have a lot of course, uncertainties. But still, people that deal with numerical modeling is most of the time a manager of numerical errors that you have. Sorry, Francesco, feel free to say a comment about that. But you must manage these things and, of course, be more approximate from the real data that you have, the observation that you have. And this is the area of mangrove that I told you about, the area of Guapimirim, the environmental protection area of Guapimirim. It's very important for us. I had already shown these results. And what we did, we have a more broad area in Brazil. And what we did is we applied the index of climate change flooded in this area. That's our index, so the scholars represent more affected areas, more vulnerable areas, and less vulnerable areas. As you see along our coast, we have different colors. So not all of the coasts react in the same way of the sea level rise, okay? But our application in 2017 used only oceanographic numerical results. So even though the index is called vulnerable, this is not the vulnerability because you need to have social, economy, and other aspects to understand the vulnerability of a place. Okay, but this is what we have at that occasion. And this is the details because when you have the downscaling, you're going to have the oceanographic process in a more resolution, with more resolution, and you have more resolution in this kind of index. But as I said, it's important to integrate the socioeconomic areas. For example, this is a vulnerable maps for the Guanabara Bay region, where we have now. So this is the present. Sorry, it's important. This is increase of vulnerability in this direction, okay? So you increase the vulnerability to high vulnerability in all of the area. But of course, this is not totally right. Why? Because we have different social and economical communities in the area of Guanabara Bay. And of course, the resilience of these communities that are social and economical difference will not be the same. So this will change, okay? And we need to put these things here. So we need to integrate the social, economic, and environmental science data sets, okay? So this is another index that we're going to have a talk about this. This is a ODOT paper from 2012. That is the Ocean Health Index. That is very nice because also combine different things like carbon storage, food provision, sense of place, all the different kind of information to have a rank of ocean health. And you have this site that you can access this for many different regions around the world. What is the challenge? To have all of this kind of data in a good resolution in many places around the world. For example, here in Brazil, we did a specific application of Ocean Health Index. We didn't know. Some people did this in 2014. And as you see, some of the information, like for example, coastal protection, is quite the same for all the coastal regions, this is not real. But this is the information that they have in the application. So they're using what they have. So we need to increase the efforts in data acquisition. Okay, this is very important. And the limitations of this study. Only navigation tax was considered. Oil and gas industry was not considered in Brazil. It's very important to consider this. Offshore wind developments that we're going to have in the future. It must be considered. Many data like region, detail, and national average were used. We use in many places the average of data. But the northeast force in artificial fishing is completely different than the effort of artificial fishing of the southeast and south region of the sea. So this difference were not considered in this study. We need to increase this kind of information. And that's it. Sorry, I'm a little late. Okay, this is only a course overview. I think that video will hate me because it's not so updated. But the idea today is to have this class with me at morning. At afternoon, numerical modeling coastal resilience application with Vivian. And we're going to have the day of tomorrow, Francesco and Nadia, be the whole day going to do the surf applications. We're going to have the lecture of Dr. Mauro, I think it's tomorrow, also talking about Brazilian coastal monitoring system, a small project that we have here in along the coast of Brazil, by net ocean data sets. We're going to have a hands-on session. Yeah, tomorrow. No, the day after tomorrow. The day after tomorrow, I'll talk a little bit about that project of the Bahia State. No, the Equatorial Margin. Another project, the Equatorial Margin, Brazil, that we deal with development of methods to understand the vulnerability to oil spill. As I showed you, is a very different area in the coastal area in Brazil regarding the oceanographic, atmospheric, and the river discharge effects. And then on Friday, I talk about downscaling techniques also. On Friday, we're going to talk about ocean health with some guest lectures from Africa and from Brazil. And we're going to have a visit to OKEANO. There is a laboratory here that has the simulation of waves, currents. It's very nice to see. And we're going to have a section of oil spill impacts with the presentation of Ana Weiss here from IBO. She'll talk about the deep horizon accidents. And a lecture by myself again to talk about the oil spill 2019. And then a visit to the laboratory that we work in. That is the Laboratory of Communication Networks Engineering, the LANCE, that is just here. And we're going to have the opportunity to see some equipment that we have there to visualize some numerical results, okay? That's it. Let's go to coffee. We need that coffee. Thank you very much.
Thank you, Luis Paulo.
We have time to pause?
We have, of course. No, I think we should do some announcements, logistics. Okay. We are going to stay outside the meeting room for coffee breaks. Lunchtime will be at a break. Hi, Peter. How are you? We have a restaurant next door. It's a nice buffet restaurant, so you are all invited for lunch with us. We are planning at 1 o'clock, is it? So we have a sort of a healthy break because we presume you had a nice coffee at your hotel. Then we have a more substantive coffee break in the afternoon. So we can interrupt and go for coffee, and we'll be back in half an hour. Is that what the agenda plays? Okay.
I think that's it. You can 15 minutes.
15 minutes. Yeah. We can get back on schedule. Okay. Coffee time. So Peter, what happened to you?
I'm lost.
You were lost in Sao Paulo, were you? Yeah. So that's why I don't like Sao Paulo, you see? So I'm glad you came. That's great. Oh, I forgot to announce about toilets. But it's just outside the main door.
Okay.
You have men and women and a handicap one in the middle. Yes, please.
It's more outgoing. It's not running. It's crashing and reading up the lights.
Francesco, 11 minutes, is it okay if the driver gets to pick her up?
For now, then we
Yes,
finish already.
please, because he knows how to get here, so
11 minutes.
11 minutes. And then we'll send the name of the driver and contact to her. I think, I just realized that I think I have Nadia's WhatsApp. I have to check with you whether it's the same. Yeah. All right, so.
Tá compartilhado, tá compartilhado.
Não, vai deixar aqui, vai ser. Não está ainda não.
Acho que nunca
Vai
esteve.
ter revisão, não.
Pode fazer? OKEANO, aplicativo.
Oi, tem a lista de presença. Tem.
A lista.
Não oficial não, mas sim. Mas eu anotei.
Você quer?
Mas tá todo mundo, né?
Todo mundo. Eu deixo isso embora. Agora, como que vai ter online, hein? Essa galera que tá online. Teve uma que me passou um e-mail dizendo
Não, seria você consegue? Eu acho que sim.
ela tá com dificuldade de entrar no colado, e aí eu mandei tudo de novo para ela, as instruções, até
So let's go. There is another kinds of ecosystems in coastal region that are very important. I will mention this one time because we don't have enough time to talk about all of these environments. But for example, the environments that are under the water and that have offered to us important ecosystem services like the coral reefs, for example, the algal banks also. But I will not talk about this. But of course, you must know that every process, physical ocean process that we're going to talk here, is important to understand the ecological dynamics of these environments. So let's go. So we're going to start talking about, the waves. So ocean waves are disturbance in the surface of the ocean. Okay, they can be created for different mechanisms, force of different mechanisms. Of course, we have, for example, the tsunamis that is associated with seismic movements at the continental crust. We have, for example, the wind-generated waves that are the ones that we're going to talk about in our course that are very important to understand the impacts over the coast. And of course, there are some basic variables that you already know. For example, the amplitude of the wave, the height of the wave, there is the distance between the crest and the calm, the wavelength, the period of the waves are basic parameters to describe the waves that are very important to consider and to understand the different products that we have publicly available for us, for example, related to the forecast of the wave climate in one region. Okay, but I know that you already know that, but it's important to say. And this is an energy spectrum. So what this represents? Suppose that I have a measure of the sea level in one region, acquiring data for 1 year, 2 years, 3 years. After that, I can use the sea level heights, sea level heights measure, and to construct an energy spectrum. So we're going to see this energy spectrum, some regions where you have the different types of waves that you have in our ocean. For example, we have 2 peak seas related with 12 hours and 24 hours. There are the tides that I'm going to talk later in this class. Okay, the semi-diurnal and diurnal tides. We have another part of the wave energy spectrum with a lot of gravity waves. And why they call gravity waves? Because the gravity is the mechanism to restore the formation of these waves. So we have, for example, the tsunamis, sages and storm surges, earthquakes, wind and other wind waves, and here in this part of the spectrum, only the wind-generated waves. Okay? We're going to talk about the wind-generated waves and the one specific wave that's caused by storms, and it is important to understand because they act direct at the continental shelf. I'm talking about the continental shelf waves that are kind of it's a confined wave at the coast, and this is important because they turn the sea level rise a little higher. We're going to talk about these waves. And all of these types of waves interact in coastal regions in different time scales, okay? So let's go. So you have the wind-generated waves. So we have a beautiful plot of the wind-generated wave out of that zone of generation of the wave, okay? Out of the influence, direct influence of the winds. So they are well organized in a swell, okay? And here you have one schematic draw showing this things. Here you have also another gravity wave that's very important, the planetary waves and the Kelvin waves that are very important, for example, to understand climate phenomenon, large-scale phenomena, for example, like El Nino. Okay, it's very important. We're going to not talk about this kind of wave in our course, only the wind waves, but they're important for you to know. And the tsunami, of course, that we have, and the tides. There's another kind of gravity wave, but now, of course, not forced by the winds, but by the astronomical forces regarding the system, Earth, Moon, and Sun system. We're going to talk later. Okay, and all these 2 waves that we're going to talk in this class, there are much important waves that act directly in the coastal regions. Okay, so talking about the ocean, the wind generated waves, basically the wind wave generation will depend basically on these three aspects: the wind speed, the wind intensity over the sea surface, the wind duration, the period that the wind acts directly over the sea surface, and the fetch, that is the area of the ocean where the wind acts. Okay, so basically all of these three components are directly related with the height of the waves. And here we have this diagram with the fetch, the area of the sea surface where the wind acts. Okay, and depending on the time that they act and the intensity of the wind, we're going to have a characteristic related of wave heights. So here is the kind of sea, okay, the wind sea that we have in the generation zone where the waves are generated, created over the sea surface, this kind of sea. Of course, most of the times we're at the beach and sometimes we have a very strong wind. You have this kind of sea, but in a local region, okay? And talking about this wind local at the coast is not able to produce big waves because we need a very big area of the ocean, a fetch to produce big waves. And we have out of the direct zone affected by the winds, the organized waves, the swell. So the waves will try to organize in characteristics related with the wavelength and the wave field. Okay, so they will, in fact, they will transport their energy in group waves. But I'm not talking directly about this. But this is the wind sea and the swell. And the swell act directly over our coast, and we understand very well this kinds of wave. This is another a draw, separate wind waves from swell. So as you see, the swell is more organized, and the wind waves, when you have the generation zone, you have different waves with different wavelengths and periods in the same area. Okay, significant height is another characteristic that is important to say. So wave height is a kind of a statistical entity of a wave. Okay, you have, in fact, is a measure of the average height of the highest 1/3 of all waves in a given area. So you can have a distribution of the wave height. The significant wave height represents 14% of the whole distribution during a period of the waves. It's an average, it's a kind of average. But this is the entity, the variable that we use to produce our forecasts, like this one that you have available. This is a wave height field, wave significant height field in a global scale. Okay, that is produced by a numerical model. So as I told you in the first part of our class of the physical numerical oceanographic models that acts with circulation, ocean surface currents, we have models that are dedicated specifically to forecast and to reproduce the wave height field. All that characteristics that I told you about, wavelength, wave periods, okay, and wave direction of propagation. So it's very important also. Now, bringing these concepts to our coast, here in South America and Brazil, of course, as I mentioned, waves are associated directly with atmospheric conditions of wind from the atmosphere, of course. And here in Brazil, we have at least in the south, southeast, and a part of northeast region of Brazil, we have a very strong influence from the cyclones, extratropical, subtropical, and tropical cyclones that happens over surface ocean regions, okay, in South Atlantic. That these cyclones are associated with low pressure fields over the sea surface, and low pressure fields are associated with very strong winds that acts in a very big area for a very long period. And when these cyclones happens here, we have the perfect condition to produce high waves that will impact the Brazilian coast until some parts of the northeast of Brazil. Okay, and this is a picture showing the three zone areas of different cyclones, atmospheric cyclones. This came from a paper. After the class, I can pass these papers for you. Okay, and yeah, using climatology of atmospheric in this region,
they identify areas of subtropical, extratropical, tropical, and subtropical that produce swell that comes from our coasts. And here you have a remote sensing picture with some pilots. They identify here Rio de Janeiro City, Brazil, of course, Atlantic, and here's the cyclone. Cyclones, most of the part here is associated with a cold front, okay, that brings dry and cold air for us here. I didn't see the forecast. Hope that there is any cold front coming to here for the weather. And that's it, a reanalysis showing a fetch. Here you have a fetch region associated, for example, a cyclone that happens in this area with very strong winds. These areas indicate the direction thanks to the winds that produce waves that comes, for example, direct for our coast here in Rio de Janeiro. This is a extratropical cyclone. In fact, this is an image of the first registered hurricane here in the South Atlantic, near the coast of Brazil. Was called Catarina, because we have the state of Santa Catarina here. And this happened some years ago. And this is a simulation of the wave-height fields in this area. Okay, so the colors represent the significant wave heights, the arrows, the direction of propagation of the waves. Okay, and this point here represents the point where I have the time series evolution of the wave-height fields related with this event. So you see that the waves becomes, here's the wave, okay, in the vertical axis, and the height of the wave, and here's the time, 5 days. So you can see that the swell starts to be small, and then after the events act and produces the wave propagates to this area, and the wave heights increase, and after the passage, start to decrease again. Okay. Oh, sorry. Watch this.
They have to learn more.
And then you have here another important entity to understand, and to understand also the impact of this wave, the energy of the wave. That it could be estimated by a formula like this one, the total energy per unit area. That, as you see, is directly proportional to the height. This H represents the height of the wave. Okay, so it's directly proportional. So if you have the height of the wave, you can translate this to the energy. And this information is very important, not only to understand the impact, real impacts associated of the wave fields, but now here we have some guys that deals directly with renewable energy, and waves are now being used to generate energy, renewable energy also in the ocean. So it's very important for this also too. But the thing to understand here is that these equations use to estimate the wave energy, and these 4 processes to dissipate energy that you have in there. So the first one, the wave break. When the wave arrives and starts to sense the bottom floor, the sea bottom floor, it started to decrease, lose energy by drag, okay, and also because the wave break, okay. And you have physical attenuation, dissipation by heat. When the waves at the ocean, for example, have that white caps, okay? The white caps that represent the break of a wave, attenuate also, how can I say, dissipating heat to the atmosphere. And you have air resistance, the drag of the air, of course, again, the wave propagation. And another effect called nonlinear wave-to-wave interaction also. That is very important to understand. That can sometimes cool attenuate, but sometimes together with sea surface currents could increase the wave height also. I have some phenomenon about that. It's called free waves. I'm not going to talk about this. Okay, that affects sometimes big ships over the ocean. So let's go and understand the bottom influence now. That is important for us for coastal regions. So when waves reach intermediate and shallow waters, they start to sense the bottom, okay? And so we have a very important process called the refraction that represents basically a change in the wave direction propagation, okay? So basically, if you can represent a wave as a
a wave crest as this line here, this blue line here, okay? When it starts to propagate to a host, and this propagation, if this propagation is parallel to the isobathymetrics that are these lines with the same depth, okay, the waves will not suffer any refraction, okay? You still remain parallel to the isobathymetrics. Of course, this is almost impossible to see. Most of the times, you have an incident angle of the wave over the isobathymetrics. And what happens is that this part of the wave fills the bottom before than this part of the wave. So we start to sense the drag and the wave velocity decrease in this area and remains the same in this area. So the waves try to make a kind of a curve or trying to be more modulated or becoming more parallel to the isobathymetrics. Okay? And this is very important because this angle also will be associated with a phenomenon that we're going to talk further that is called the coastal drift. Okay? The waves near the shore will also be responsible to currents that are very important to understand the sediment transport, the dynamic and the equilibrium of sediment transport near shorelines. Okay? So, coming back a little bit, imagine that we are talking about an ocean-atmosphere interaction processes, that is the wave formation that depends on the wind energy. And we are living in a planet that the climate is changing, the wind circulation is changing. Okay? The conditions are becoming more extreme, and so what we know as a climate of the wave will change the next decades because of this global warming, because of this change of the circulation. Okay? The cyclones will be more strong, okay, and would change their positions also too. And so the tools that we're learning here would be very important, again, to understand how this change will be and how I must prepare the coastal regions to receive these different impacts. Okay? So let's go. Wave refraction. So just some slides. It's very nice to see this slide because I have rock points, and most of the times surfers like these rock points because the waves, now we understand the refraction concepts. Waves start to break here, and now you have an area just inside of these rocky points where the energy dissipates. So it's a good position for surfers, not a good for fishers. And this is another process, it's quite the same of refraction, but it's called diffraction, that absolutely have obstacles. Obstacles that could be made by the human and obstacles that are nature. Okay? And so you're going to have diffraction that will also will act to change the propagation of the waves. Someone wants to. So talk about modeling. As I said to you, modeling is good because you have the possibility to represent in high resolution the wave fields and the possibility to understand coastal impacts associated with different climate scenarios as I told you about. So here you have an application of a downscaling, for example. So here you have a global wave model. This is if you can show Wave Watch Trace, it's a very and it's a very useful and popular ocean model publicly available. So you can pass from the global scale to a South Atlantic scale grid, and then to a southeast Brazilian coast grid, and then you can come even from the coast of Copacabana Beach. Okay, this is a hotel Copacabana. This is, I recommend that you, if I have any time to go there, this one time, and then you can see when you have high resolution. These colors represent the wave dates. You can use other models that represent better the refraction effects near the shore to see this difference that you have. For example, in this occasion, you have bigger waves in this side of the beach and smaller waves in this area of the beach. And this is important also because you approximate your result to engineering demands, for example. Suppose that the engineer wants to construct anything over the beach that are, which I not recommend, of course. They need to know this information to understand. So Let's go. And this is our some impacts that you have related to waves. Oh, yes.
So that last simulation, so you before shows.
Can I go there? To hear you well.
Okay, so we had you have on the slide with data from the Catarinas.
Catarina,
hurricane.
yeah.
That was a data, right? That wasn't a model.
No. That was a data. That, in fact, what I showed to you is a satellite image. It was a satellite image from the Catarina hurricane.
It's because there is like a super interesting difference that the contour.
Yes, the boundary.
The boundary, exactly. The boundary of the coastal side, which is like the important thing because you want to know when, if the water is coming to the earth, was almost
contrary.
Constant
Constant.
on the Catarina measurement. But in the mathematical model here, it is changing as if it was part of the ocean. Like the boundary condition is super, because that if we have the wind from the Catarina, didn't depend on if it was outside the terrain or if it was on the ocean, right? So the wind was strong here.
Yes. I think that I'm understanding what you are saying. You're talking about the influence between the boundary between the land mass and the ocean.
Exactly.
Yes. To the ocean waves, the importance is how the wind is strong over the sea surface. Okay.
Yes.
But of course, what happened with the hurricanes and in general is that they are pumped, they are generated by an ocean atmospheric processes. So you have sea surface temperatures higher, warmer. This is good for the production of cyclones because it puts more water vapor and energy to the atmosphere. Okay, and then you produce more energy and the cyclones. And the cyclones, one time it was generated over the sea surface, they started to propagate. And when the phenomenon meets the land masses, this ocean feed of energy in form of water vapor just decrease, finished, and then start to decrease. But the winds are very strong. So this finish of the cyclone sometimes, much of the time, is not at the same time. And that was the problem because it's still the atmospheric system is still there with strong winds causing a lot of damages at the coast.
Yes, my question was really going to be how do you overcome this numerical simulation? Because what arguments can you use? Because the contour again, I'm sorry. The boundary. Yes, because in this case the boundary is changing a lot. The height level, like by this model, the height of the Brazilian coast is changing a lot, right? If I am reading this graph correctly.
I don't understand very well talking about the boundaries because this simulation, you're talking about the representation of the cyclone with this grid domain.
Not about the cycle, but the sea level on the coast, close regions is augmenting a lot in this graph.
Yes.
But this is true. It does change that much.
Yes. Now I understood. Yes, this is true. It is true. It's true. But I will show some photos and you will see that it's really true. Yes, sorry.
I'm sorry.
Can you open your microphone and ask your question?
Yes, can you hear me?
Yes. Hi.
Hi, I'm very sorry that I'm not there. I'm really missing all the colleagues and the physical presence. Anyway, thank you very much for your presentation. I got to learn a lot. My question is about if you know the recent incidents happened, especially in Switzerland and this area in Europe, where these icebergs they melted, right? They got melted, and that's why I believe there will be a huge change in the ocean mass balance. So I'm curious to know if is this balance has any impact, or how, or like in which, what would be the threshold for the ocean physical process, and will it be could we see it in the modeling part as well?
Very, very good question. And of course, yes, I think that, can I want to respond? Can I respond?
Go ahead.
Okay, so complete myself if I forgot anything. Yes, okay, mic is there. Can you hear me? Are you hearing me?
Yes, I can hear, I'm hearing you.
Okay, the climate, even the regional and the climate models, now you have parameterizations that try to represent physical parameterization, try to represent all of this balance that you told about. For example, the climate models, that the ones that are used for IPCC, for example, represent the best way as possible the process associated with melting of the ice, and how this melting of the sea ice and the not sea ice will affect the sea level rise. And of course, all of these processes are integrated in this kind of climate models. For example, the melting of ice is a reflection, for example, of the warming of the sea surface level and the warming of the air also. And these changes of energy between the different components of the climate systems are well represented in these climate models. Of course, uncertainties will always happen, okay? Because as I mentioned, not all of the processes are represented by what I call universal laws, okay? Like Navier-Stokes equations. Some of them, we need to use physical mathematical parameterizations, that, as the name parameterization says, is a simplified formulation to represent physical processes. But this process are represented. You asked how this will impact in a specific area.
Is there a threshold limit?
Yeah. There are some people now studying, some years ago, what they call tipping points. I don't know if there is the direction of the response, but the tipping points are points of no return. So yes, there is. I imagine that there are some thresholds. I don't know now to say exactly what is the threshold associated with the ice melting. What I can say to you is that many different turning points or tipping points, we are arriving at many different tipping points, unfortunately, now in our planet. About the sea ice melting, I don't know to say very exactly what is the threshold.
No, not about the sea ice melting, and about that breaks of the ice and the land ice. As far as I know, in what I've studied for my PhD, there is kind of there is misrepresentation of the climate models, the Earth system models, about all of the aspects of the climate interactions, especially when you're talking about land ice melting and how it goes to the ocean. Is that we have a land ice model, and this land ice melts. And think about different boxes, okay? We have a land ice model. This land ice melts and send this melting water from the land ice model box to the river model box. And then this river model receives that melted water. And then through the river, it goes into the ocean to another model. So all of these interactions are not so very well tuned. Okay, so we have a lot of limitations about with these interactions. So I'm not sure we have so good projections about that, but I know there are a lot of limitations on all of this process. I'm not sure if I was clear enough. Amida, you're here? Are you there?
Hello? Hello?
Yeah, I mean, it always takes time to unmute myself. Yes, I hear you. I heard you, and it's clear for me.
Okay, okay. One thing that I think is important to say, one of the directions that numerical science is going now is to have unstructured grids. I mean that one unique grids, numerical grids, have different space resolutions in order to understand well the representation of these land, ocean, atmosphere processes in the same grids. Okay? It's a technique maybe, I think that's Francesco will said a little bit. Okay. I think that tomorrow you're going to hear a little bit about in the application of SURF. And I think maybe we'll tell
a little
something.
bit
Yeah.
more about
So
today.
let's go to some impacts here so here's Guanabara Bay. We are here at these islands, where is the university city where we are now. Okay. So here you have the ocean part of the city of Rio de Janeiro at this side, and the city of Niterói, the other side of Guanabara Bay. So, sorry. So here you have some impacts, the waves. Okay. So here is the Ipanema beach. So you see a wave acting directly over urban construction, okay? So here, believe me, you have a sand beach. Most of the time it's here, you can go there. And here's what happened in 1999, okay? Look at the fort here, okay? There's another photo there. This is the Leblon Beach. Leblon Beach is the same beach of Panama Beach, but the other side, okay? So you have here a lot of sand. Okay, so what we did, I will talk about this, but you have the beach as in the normal state of the beach with all of the vegetation. We just some decades ago ignore the vegetation, remove the vegetation, and put some streets over there. And remove the vegetation, remove the structure that fixes the sediments there. What you cause erosion. What is the sea just took again what is a dynamic system, as I said. So here you have the airport Santos Dumont that is just inside Guanabara Bay here, okay? So here waves just almost reaching the floor of where the plane just arrived. And here you have Niterói, Sicaraí Beach, the other side. Another wave acting there. And you know that for the waves to enter inside the bay is not it's not common. It depends on the position of the cyclone systems, where they happen. And sometimes they change the position, and so they change the direction of the swell. Waves that generate the propagation of the waves. You change it. And there are some conditions, specific conditions that you have waves, and people surf inside the Guanabara Bay sometimes, big waves. And as you know, Guanabara Bay is very important for have maritime transport. You have people that sails over there, people that swim, different economic activities, fishery. So it's very important to understand this process and forecast this process. To be operational is very important.
Just a question. That's the results of CITES?
What? Sorry?
The results of CITES?
CITES?
SCICES. Siege.
Siege?
City?
Siege? Like on waves?
No, this is waves that arrive, enter the bay, and just right here.
The Leblon?
Leblon is sand. Sand that was green by the waves, because the waves, you have a transport.
But they siege?
No, sand. So all of these examples are sand beaches. So now I'm sorry. I'm not a geological oceanographer. But there is sand beaches, okay?
Like the waves.
Waves transport. Seixas, I mean the waves.
The waves. It's
Yes,
caused by Seixas. I don't know if I pronounced it correctly.
No, yes, you have two waves acting there. You can define the waves generated by winds, high frequency, and the low frequency waves also too. You have that stations and storm surges also related with the atmospheric events. When the cold front just passes, it just also generate waves, low frequency waves that has also, I will show them, the role of increasing the sea level rise for some days, 1 day, 2 days. And this will sum with the tides and with the high frequency wind generated waves, okay? And so you have a buildup of water near the coast. And it's a very huge problem, not only because of this, but because when you have the drainage of the precipitation, the sea, but you have a hydrodynamic barrier that don't lead the water to. And you have a lot of floods inside the urban city and center of Virginia. That's it.
Yeah, I think.
Vamos lá, let's go. This was a cycle path. Look what happened. It's a very beautiful place to cycle, but unfortunately, I think that the people that construct this ciclovia, I don't know how to say, bike path, okay, didn't hurt any oceanographer because it's a very common phenomenon over this region of Virginia. And what happens is that the force that becomes stronger as a normal street from the upper to the low parts, okay, to the upper. The structure is not ready for that. This is the continental shelf waves, or the low frequency waves. I think the Seixas storm will be the same classification. And now waves related with extratropical cyclones. This is the Catarina, images of the Catarina. Okay, so these cyclones and hurricanes produce waves that propagate. How can I say? The coast is here. Okay, they propagate. The propagation is parallel to the coast, and the effect of this is just to create a kind of a sea level rise during the passage of these waves. That is related to 3 to 6, 7 days here in our coast of Brazil, and are related with the cyclones. The cyclones produce the wind, the high frequency wind generated waves, but also these low frequency waves that will have the effect to increase more the sea level, okay, when we have a passage of a cold front system and cycle. And the effect is the one that I said. This is in the Jardim Botânico area, the place where I live in Rio de Janeiro, during a passage of a cold front, okay? So we have high waves and the water of the drainage that goes to the ocean didn't get to go to the ocean because we have a barrier, okay? And of course, we have some lack of maintenance by the mayor of Rio de Janeiro also too, okay? Because they must clean the galleries. Okay? But this is this is important to say. Here, urban cities, the contribution to flood events in coastal cities, this kind of wave must be considered, okay? Because cold front systems are associated, of course, of rain, increasing rain. So you need to drain all of this water in urban cities. Okay? So now talk about the other kind of waves, the tide waves. Now they are also gravity waves, okay? But they are forced by astronomical forces. Basically, the gravitational forces associated with Earth and some system. So we have, of course, an harmonic, what we call harmonic phenomenon. So what is important to say, this tide is a very predictable phenomenon because the nature is astronomical, and we know very well all of the movements related to the Earth and some system, not only for today, for the past, of course, and for the future. So if you ask me how will be the astronomical tide in 2056 here in Guanabara Bay, I would have to say at least astronomical tide, of course. Okay, so you have centripetal forces and gravitational forces. The sum of them will generate the tide-producing force. Okay, that these combinations will just do these things. Okay, so you can see the level of a sand beach. I think this is in France, and this is in Fundy Bay, very known and very popular oceanographers because of the resonance effect that we're going to talk about further. Okay. Yeah, that's it. Due to our astronomical nature, tides are highly predictive. And these are some basic concepts. Okay, this is a tide register. I think that tidal record. Okay, a time series plot of the rate of the tides. We have the high tides, the low tides, the mean sea level. Okay, there is an average of the sea level rates for a long data series. We have the spring tides. Okay, with high amplitudes associated with full moon and new moon, and the neap tides associated with the first and third quarter moons. This is the tidal amplitude, quite different from the waves that we saw before. There's the difference from the low tide to the high tide. And here you have the astronomical conditions. Okay, I think everybody knows that. The spring tides, you have the conditions of full moon and new moon. And I think it is changed. This is the new moon, that is the full moon. First quarter moon, third quarter moon. So of course, here you have the sun, moon, and land in the same position, or in opposition, or in composition, and then the resultant tidal producing force will be higher. That's why we have higher amplitudes in mid-spring tides, and smaller amplitudes in neap tides because they are not composed in the way that the resultant tidal producing force is strong. Okay? So here you have all the classification regarding the periods of tides. I have semi-junior tides with 12 hours of period, and mixed and junior tides of 24 hours. Tides, here are some time series records for different places around the world. San Francisco, Bistro, representing the mixed dominant semi-junior tides and semi-junior tides. And here you have time series from Manila and Gulf of Captain, Australia, representing junior and mixed junior tides. It's quite the same, okay, only representing. And here's another classification regarding the amplitude of the tide. We have micro, meso, and macro tides. Okay, so micro tides less than 2 meters amplitude tides, meso tides 2 meters to 4 meter tides, and macro tidal tides are the ones that are higher than 4 meters tides. And here you have a representation that is not what brings complexity to the representation of tides. The ones, of course, are the land masses. And if the world was wholly completed by only ocean, we didn't have problem. It didn't exist also, but we didn't have problem. And now you have the land masses. And you can see, for example, along the South American coast, you have regions of microtidal tides. The north equatorial margin of Brazil have high amplitude microtidal amplitude tides, with at least 8 meters of amplitude. But in along all of the rest of the coast of Brazil, you have mesotidal and microtidal tides. Okay, and there is distributions along the whole planet. And this is another example. Here in Fundy Bay, you have this kind of processes that is not related only to the macrotidal currents, but also because the resonance that we're going to talk. And here you have the northeast region of Brazil, tides, mesotides. So it's very neat, it's a very beautiful place also. So imagine, again, you have places with different coefficient of tides that will front in a different way the impacts related with sea level rise, for example. Let's consider this kind of difference when you study coastal resilience or when you study coastal vulnerability. And this is the combination of the ocean basin geometry with the Coriolis force brings to us the amphidromic systems. That is this point where you don't have the variation of tides, and you can include, for example, the movements of these tides in the counterclockwise in the southern hemisphere and counterclockwise in the northern hemisphere. And you have this dynamic vision of tides that comes with a theory, called dynamic theory of tides. And this is another vision of the amphidromic points. And these lines here with 1 hour, 2 hour, 3 hour, of course, are called cotidal lines. That are lines that represent the same amplitude and the same phase of the tides. And I'm showing this because when you go to our planet, you can see a lot of amphidromic points, and around these amphidromic points, you have the cotidal lines just moving. Okay, so this is very important to understand. And of course, this is a picture from the global with low resolution, and this is a picture, for example, of the same processes in the part of the coast of Europe. So you can see more complexity when you go to these regions. And you can take access of this kind of information in different sites, public sites. You have tideforecast.com. You can take the time of the high, the low tides to any city around the world. And you have models, numerical models also, like the XO and the FAST model also, that you can use for, they are very important to produce time series plot that can use as boundary condition in your physical numerical hydrodynamic models in order to represent the tidal currents that we're going to talk a little bit further. Okay, or you can also acquire what we call harmonic constants. Okay, I'm not talking detailed about this, but the harmonic constants lets you do the forecast of tides. Okay? And these are some examples of resonance that you have. Okay, so here at Fundy Days, you can see the geometry of a specific coastal environment, coastal marine environment, for example, the Bay of Fundy, to the following. The tides that enter in the mouth of the bay with 5 meters, inside there would be 15 meters of amplitude. And you see this kind of processes over there. Okay, so it's very important to understand the resonance. I talked with a friend from Bahia. There you have the Santos, Bahia de Todos os Santos Bay. Okay, and he was told me that at the mouth of the bay, you have one amplitude of tide, but when you enter the bay, you have an amplitude much higher. So it's important to represent this, also to understand aspects related with coastal resilience to tidal rise. Okay? The impacts of different regions in the same coastal body could be very different. This is an example for here. This is Sepetiba Bay, the complex. We call complex Sepetiba and Ilha Grande Bay in the south region of Rio de Janeiro, very beautiful region. We call Green Coast. Okay, and here you have the tides enter in the both bays, but you can see. I try to show you. This is very old. Okay, it's a simulation with a model called Crystal Ocean model, very old. And what you see here is of course, is exaggerated. Okay. I don't know if you can see here, this is the island of Ilha Grande. This is the Sepetiba Bay, and this is the rate of the tide when it's entered. You can see at Sepetiba Bay that when this part of the bay, the Ilha Grande Bay, is already totally low, the Sepetiba is still high. Because you have not only the resonance, but you have the influence of the geometry in also delay the time of the tides. Okay, so this is very important to consider, and of course, our numerical physical ocean coastal models got to represent these things. You need to have experience to turning the model to represent this, and very important, you must have data, because without data, you don't have the real world compared from the numerical results. Okay. So talking about tidal currents, of course, the gradient of sea level heights, sea surface heights, okay, will produce gradients, pressure gradients, and the pressure gradients will produce tidal currents. Here's an example from Guanabara Bay. Okay, you have this arrow enter and going out the bay because of the tides. The tide is the mechanism that dominates the circulation over the Guanabara Bay here in our side. Okay, so the colors represent the intensity of the currents, of course, near the mouth because of the geometry of the bay. They are very strong. Okay, and here, this middle part of the bay, inside the bay, they are also very strong because they have the more, let's say, depths, bigger depths, because it's the navigation channel.
Yes, which model are you using here?
Here, the regional ocean modeling system.
Bronze, okay.
Yeah. And then at the end of the day, we have very shallow regions. So the circulation intensity, the currents is smaller also too. And here we have the time series plot, okay, of the tides. And here it's very important to say, if I can take a time series plot of the velocity, of course, there are 9-degree time lag between them. So when you have the tide just increasing, you have the strong velocity currents. Okay, they have tides, and when you have the low tides, it's happening the low tides, you have the most velocity, the most intense velocities. Okay, and we have a phase, a time lag between there. And you can use this, for example, trying to represent the oil dispersion inside Guanabara Bay. This is not happening. Okay. Happen another kind of accident that I showed to you, but this no. Okay. But I wanted to show some applications that you can do, and you can integrate this, for example, with social, economical characterization of this area in order to understand better the vulnerability to an oil spill in this area, and understand the resilience of the communities that lives around the Guanabara Bay to an oil spill accident in different hydrodynamic and atmospheric scenarios. And this is the power of the tool that you're going to learn and you're going to have about in our course. And this is happening. Unfortunately, this happened. In 2000, we had a very big oil spill accident inside Guanabara Bay that, even though it was very bad, it was very important for the environmental policy here in Brazil. Because after this accident, okay, that is represented here by a SAR image, a satellite radar image. Okay, so this black shadow here is oil that came from a refinery, or it's another refinery that you have here at the bottom of the bay. This is the simulation of the oil, and this is what was observed. Okay, so as I said to you, this kind of accident is not good, but for the development of the mechanism, it's a chance for us to prove if our model is representing the accident in a consistent way. And this model was developed in a class of numerical methods in meteorology, because this exercise for the classmates, and then they started producing a model in a class. That's good. So talking about some important systems or coastal environments that we have, and that are whose dynamics is directly related with tides. The first one is estuaries. Estuaries are very important. We have to think that everybody knows what is estuary. Yeah. Okay. This is large, partially enclosed body of water that just find the meets between the ocean waters and the river waters. And you have most of the time the seawater that's salty and more dense near the bottom, and the fresh water that is less dense at the sea surface. But in fact, to understand the structure, you need to study the ballast force between the river discharge and the tides. And what we see is a classification. And you have the south edge estuaries, when you have a very strong river flow and a very low, very small tidal variation. And when the tide starts to increase, the mixture at the water column of the estuary starts to increase also too. and then you have to a well mixed estuary. And this is a tidal current profile in a well mixed estuary where the tides dominates. Tides has a paratropic nature, so affects the whole water column in the same way, and then you have almost all of the vertical profile of water going from one side to other side when you have a well mixed estuary. This does not happen in the very stratified estuary like the south wedge. And what is important related with climate change? These environments that are strongly dependent of the tides dynamics will suffer in sea level rise. Okay, will suffer a lot because in sea level rise, we will change the effects of tides, and maybe we can increase treating coastal ecosystems and freshwater supplies because we want to increase the range of the saltwater inside the estuary. Okay, so this will change a lot the uses of the estuaries.
Just to add something, remembering what Flamida asked. On the other hand, if you have a land ice melt, then you're gonna have like a increasing river discharge. So you're gonna have the other way around.
The other way around, yes. Each case must be studied.
Yeah.
Maybe in one place,
yeah,
one process.
Example of everything is
Yes, it's connected. And that's why you need to study each place in a different way. Apply the same tools, but must be a wide mind to understand that you don't have a fixed one. This is quite the same thing, only looking at the profile of the velocity inside an estuary, going to the direction where tides dominates and the direction where river discharge dominates. You have also negative estuaries, okay? Estuaries associated with very shallow areas where the evaporation exceeds precipitation. So you have salted waters more than the ocean. Then you have negative circulation. This also can change the climate change scenario. And this is what happened, of course, in the future. Estuaries are very important because most of these mega cities that I told you about near the coast, in the beginning of our present course today, are near the coast. And of course, the use of this area for sewage, for any other use is high frequency, the use of these things. So what you see here, in the present days, you have low tide, and of course you have a drainage for the water that is in human cities to one place. Okay, under sea level rise scenario, this place that will be low and the drainage, okay, is now is higher. So we have a hydrodynamic barrier, so it's not go out. Okay, so these things are important to understand in the urban places. And numerical physical model will bring us a lot of information about it, but we must use with responsibility. So before doing our forecasts, we need to understand if our models are got to represent well the present conditions. And we need that. Again, I said data because we have a lot of problem of data in Brazil. So talking about another biggest marine environment, okay, Amazon region, Amazon shelf. So here you have the Amazon River, the Pará River, okay, and here you have some satellite image products related with the plumb of river waters from the Amazon River. So it's very nice because you can see some large scale phenomena, like for example, the retroflexion of North Brazilian movements here. August to September to October, you can see this feature. You can see also a lot of water of the river going in the direction of our neighboring countries, Guyana Francesa and others. And this region is very complex because you have not only the river discharge, you have the strong tides, macro tides in this region. We're going to talk about more detail this in the presentation that I will do for you the next days. You have the strong North Brazilian movements. That is not a river like this line, of course. We have a lot of edges and meanders associated with this flow. And you have the winds that are on most of the time because they are related with the intertropical convergence zone that acts directly in their region. They are the trade winds, the southeast and the northeast trade winds. Okay, so to understand all of these dynamics and the dynamics of this estuary system, okay, that is quite different from any estuary around the world, we need to understand the different time scales associated with these different meteorological and oceanographical forces. So this is a work that time series that represents the different variability in time of this forces. So it's very important to understand this. And I must say that this is one of the regions that maybe will be in the next years the new oil production area in Brazil. So it's very important to understand, and there are many people studying a lot the dynamics of this region. Not now, since a lot of years ago, but now these studies are increasing a lot. So talking about storm surges, we have started to talk, but the non-astronomical influence over tides. Okay, so as I said to you, when this cold frontal system passes through our region, for example, we have winds that just fill up the water over the coast, and of course, this effect is you can add the effect to the tides, and then produce more sea level rise, even higher than when you have only tides considering, of course. And this is a sea level time series. And here you can apply some filter analysis, like Fourier analysis, and you can, for example, decouple what is a storm surge, that is this red line here, that, as you see, is not harmonic, of course, because depending on the atmospheric events, and this black line here, that is very harmonic as related to astronomical tides. So you can separate these things, trying to understand the influence of storm surge in the sea level rise. And of course, these are things that I just happened. Meteorological conditions can make actual high tides higher and low tides lower than what is forecast by prediction models. Yeah? And these storm surges are here in our energy spectrum. Okay? They are here, saging the storm surges together with the tsunami. But the tsunami only seismic movements. Okay? And here the tides. So you have talking about still storm surges, let me remember why I put this slide here. Okay. Here you have, only to show the new, not so new, scenarios from IPCC, the socio-economic shared pathways. That's it. And this is the study from Metofsky until 2019, showing what we already know, the increase of extreme weather events, hydrological, meteorological, climatological events, okay? And this is the scenarios of SSP, and this is some photos around the world here. Again, in Ipanema, I have 10 regions, because I had already lived there. It's a very beautiful area. That's why I took this photo, but as you see, you have a condition, okay, of the sea just arriving. This guy is not in a good position here, okay? And these are things that represent these storm surges and the influence of storm surges over the tide effects near coasts, okay? And this is what's happened really. This is a study from the NOAA showing the change of sea level going to 20 centimeters, the blue, the more strong blue, okay, in the last 30 years. So things are happening. And now talking about the wind-driven currents, okay, of course, the wind will act over the sea surface and produce a vertical profile of velocity that, of course, will higher near the sea surface and will decrease with the depth. And this is depending case of the wind, of course. And when we consider the rotation effect, we have the Coriolis force, and then thanks to Ekman, that in 1908 produces was the Ekman dynamics theory that said to us that the current generated by a wind will diffract for about 45 degrees to the left in the southern hemisphere, to the right in the northern hemisphere. And then we have the ECMO spiral, okay? And you have this is important, this theory, even though it's an analytical theory, okay? I think that anyone had already seen exact ECMO spiral in a data set, so maybe it's something here. You have also these dynamics help us to understand, for example, the upwelling, the coastal upwelling events and physics. That is very important for coastal regions, of course, because you have the Ekman transport in the 9 degrees. And so here you have an example of upwelling happening in a coast in some place in the northern hemisphere, okay? And this remove the waters near the sea surface. And it's important, for example, for the increase of our lagoons, for example. And of course, brings a lot of, has a lot of importance for fishery purposes, okay? And of course, these events that depends on ocean interaction processes will be affected also in the climate change scenario. And so if you think in a resilience related with the economy of a place that lives directly with fishing, you must consider this kind of effect. You can produce, for example, a vulnerability index associated with fishing in one place regarding the climate change scenario. How will it change? There are questions that you can respond. And this is what happened in Cabo Frio. Cabo Frio is a city very near here. So we have nutrients, organic matter at the bottom, outside the photic zone, okay? And then you have winds that just going out of the wall, okay? You're going to have an Ekman transport, this redirection, and by volume continuity, you will have the nutrients over there. This is a satellite image of sea surface temperature showing the region of Cabo Frio that's here, okay? So you can see very low temperature values near the coast. That is not common. That place is common because you have upwelling conditions. That's the place. And, okay, let's go. Now talking about some other continental shelf environments that are important for us. This is a map showing in white the areas of continental shelves in the whole planet, okay? And in this continental, this is a detailed picture from South America and Brazil, where this area is very important. And it's very important by the same reasons in any place around the world. You have a lot of economic activities there, okay? And it's important socially, of course. Social and economic parts came together, and or must be together. And that's it. And here in Brazil, we have this different usage of this area of our country. Here is a detail of what we call Southeast Continental Shelf. So Rio de Janeiro is here, and Santa Catarina State is here with its capital, Florianópolis. And we have this moon shape here of this region. Okay, this is the bathymetric map. And you can subdivide the continental shelf in 3 areas. In fact, this is I will show to you a physical oceanographic classification because it's based on physical ocean processes. You have the inner shelf, that is here, this is a detail for Rio de Janeiro state coast, okay? Guanabara Bay, Sepetiba, Ilha Grande Bay, they are here. So the inner shelf will be strongly affected by river discharge, tides, waves, wind currents, and density currents also. When you have water masses with different density, of course, they will produce also pyroclinic pressure gradients and will produce currents also. And have the mid shelf, where basically you're going to have the wind currents. Of course, some of these processes could affect the mid shelf also too. This is not a static picture, but it's dynamic, of course. And you have the outer shelf, where you have the large-scale wind currents, for example, the Brazil currents. Okay, so all of these processes must be integrated when you try to simulate or represent a numerical model. Okay, you cannot look to the Guanabara Bay without considering the effects of the mid-shelf at least. Okay, it's very important because you're going to have waves, you're going to have other processes that are generated outside and will affect and will be important to represent well the circulation inside Guanabara Bay. So let's go. Still talk about continental shelf environments. Only to say we are in this region, we don't have only estuaries, as I said. You have, for example, coastal lagoons that are very important. You have Lagoa dos Patos, Patos Lagoon, that are very big lagoon complex in the Rio Grande do Sul state. And it's very important. Here you have Porto Alegre, the capital of Rio Grande do Sul, that unfortunately during the last years suffered a very huge impact of rain due to climate change. And we must consider that and consider the dynamics inside there. Because Porto Alegre suffers a lot with floods. And these flood conditions happen because lagoon of Patos just increased its level, okay, or the level of the lagoon, and we have a lot of rain, and the drainage also was affected, compromised. Thank you. Okay. We have estuaries, that we talk a lot, and we have sandy beaches also. I will not talk about all of this, but I will talk a little bit about sand beaches. Now, just a little bit because I have people that use directly with sandy beaches, okay? I'm not a geomorphologist, but I think it's important to say. So this is a sandy beach, the shoreline composed of deposits of sand, okay? These dynamic environments are shaped by the constant interaction of sand, water, and air, and are influenced by factors as wave, energy, and tidal range, okay? And sandy beaches serve as important buffer zone for coastlines. Buffer zones are very important when you think in climate change scenarios and scenarios. Okay, so maintaining these environments are very important. And I didn't plan this, but I think that is important. Participate in a meeting last week when people talk about solutions that could become from engineering, but there are solutions that are much more simple that came from the nature-based solutions. If we not interfere, or less we interfere in this kind of environment, better for us. Okay? If we interfere, short feeds, remove the vegetation, not good. So this is a profile of the beach. You have different areas, surfer zone, breaker zone of the waves. You have this profiles here. I think that here is a profile from summer, and this from only different profiles of beach. And here's with cliffs, berms inside this kind of small dunes that you have over the sands. Okay, and the subdivisions of a sandy beach are extremely dynamic, of course, because they depend on the winds and the waves and the tides, and these forces are dynamic. So the transport of sediments and the beach profile will be very dynamic. So here you have different ones. This is the Cupi Beach in the Pernambuco state, very beautiful beach. Look at this. This is Ipanema Beach, okay, here in Rio de Janeiro, and this is Caleta Beach in Santa Catarina. They are quite different. Okay? As you see here, the type of beaches depends on the kind of processes that deposits the sediments there. So you have chemical and physical chemical aspects in the lower latitudes of Brazil and more physical processes in the southern part of Brazil. So we have more cliffs and mountains near the coast, and in northeast you have more sandy beaches with plain areas. Okay? And of course, these are directly related with the granular, how can I say? Grain size. Grain size. Oh, grain size. And this is very important to understand the sediment transport also too. This is beach profile dynamics. So in summer, the same place you can have a wide sand area, And during winter conditions, you can see huge debris. Okay, winter conditions and in summer conditions, you can see these small domes over the sand that are called berms. Okay, so we have a strong dynamics of these sand beaches, and you have the vegetation, vegetation, or any kind of vegetation that are very important to fix this sediment there. This is a region, I think, this near New Jersey, in the east coast of the United States, and what happened during Hurricane Sandy. This was before the hurricane, it is after the hurricane. You can see what happened at the beach. What happened here is this. Things that can happen. And this happened because you have at the beach, because you have transport of sediments that must be understood. And the transport of sediments of a grain, for example, silt grain, depends on the drag component, the gravity force, and the lift force. And you have a water vertical profile, higher velocity at the surface, and smaller velocity at the bottom. This will act in the sediments and will transport the sediments. Okay? And then you have another concept that is important, there's the longshore drift, that is the combination between waves, winds, and tides also will combine and do this drift, that's the current that happens near parallel to the coast. Okay, and we transport the sediments to one area of the coast or other area of the coast, depending on the wind direction and the waves direction. Okay, so this is produced the equilibrium of sediments in a beach area. Okay, so before you want to change something along the beach lines, you need to understand very well this equilibrium. Otherwise, you would be going to a not equilibrium state, as you understood. Okay, so maybe these things could happen. Sorry, very childish thing, but imagine that you have one region, one channel here, and these are wave crests, okay? And these will have the wind, and these will have the longshore drift, okay? So see. And then suddenly you see a coastal erosion this size. What people like to do? Let's gonna solve this. We're gonna do a barrier here, okay? And then you do a barrier and coastline increase here. Good. But the other side, you have a new coastal erosion. And then you have to do what? Put another barrier here. Then you can see your beaches, a lot of barriers. It's very common, different places around the world. And this is one thing that before you start to put one thing, you must study very well. Okay? But this is one another place. I say Iracema Beach, Ceará, state of Ceará here in Brazil, northeast. You have this place, this barrier here, and you can see very well the beach here and the beach here. You have more sand here and less sand here. This is the east coast also of the United States. This blue line is how the shoreline is before the installation of this structure here. Okay. This is Ipanema Beach in 1940. And you can see here in Ipanema Beach, this is vegetation. Okay. When you go to Ipanema Beach nowadays, present day, it's like this. Walls, remove all the vegetation. What happened? This happens. And sometimes at the summer, you don't have high waves here, but you have strong currents that, how can I say, remove the sand in the direction of that direction of the beach. And if you don't have vegetation, you have only concrete wall. So I have the power to fix the sediment and then to cause erosion, even in summer conditions. And that's it. If you have coastal vegetation, that's okay. You send the beaches to remove when you do urbanization. You don't have to fix the sand. Okay? And that's it.
Thank you. Very good.
Okay?
Questions? Oh, yes. Here's one.
Regarding the longshore, is it, can you extract that in the circulation model or it's another model?
No, you can use the same hydrodynamic model, for example, that Francesco will present tomorrow, and that I mentioned for my friend. Right. Ron's model, the both models are able to represent this kind of phenomenon. Okay, but the important thing is that first you must implement the model in the right way. There are numerical issues. There are physical issues that you must adjust well. And the most important thing is to have data. Because the data will help you to validate your model results, to see if you are going in the right direction to represent consistently a physical process or no. Okay? So that's it. But all of the models that we present tomorrow is totally able to produce these things. You have a transport sediments model inside
Imono. I think perhaps best as the after Nemo.
Nemo don't have a sediment transport model, but you have other models. For example, the oil spill models, generally, the hydrodynamic models don't have oil spill models inside them. So you use the information that they produce, the hydrodynamic field that produces the hydrodynamic model, and uses as a data inputs or a boundary information, this condition, in your oil spill dispersion model. Or you can have a sediment transport model also. Or there are some models, for example, Ron's model, regional ocean system, you have sediment transport model inside them. You can use in the same model, can represent the same model, the hydrodynamic and then sediment transport. Okay? Let's go lunch. Breath a little bit, right? Does anyone have one question online?
Probably.
You can
Because some guys in the university, they call it,
Se quiser assim também não tem problema não. Quer colocar o seu?
we need to go what I need. You don't like to see how still can like so you know your side looks like you have friends.
I don't know, as a guy, the military, right? I am not looking for the superiors, but the procedure. What is the
So you are not.
Also trying
Right? That's why a lot of girls are outside this. And then say, oh, so why, us, the guys, why do you go to other countries for us? It is because you guys understand. This is one of the last Pokemon games I ever played before I got into this game. So they would play a song.
That's mine as well.
That's why we
I'm leaving Europe using ball and later or something.
So that is why
I know how like
say, oh, so this is what's going on. Yeah.
I spoke as well and your best friend.
Typical. This is Guaraná.
Yeah.
Very Brazilian.
It's my favorite drink.
I saw it. I had no idea what it was. So it was
Really?
Yes.
Yeah.
Great. I'm gonna explore. I came here to experience the best that.
There's no alcohol.
I drink para check.
I'll carry the truth.
There's some
I really love this.
Yeah, it's very sweet.
One is coxinha. This I can tell you.
Yes, the came the food. That's good. I'm ready to get you.
This is like typical.
Yeah, it's call it Guaraná.
Yeah.
We only have it here in the whole.
Welcome back to Guaraná lunch. Okay, so now we're gonna talk a little bit about models, numerical modeling, and because it's a subject that can be a little difficult at the beginning, we're gonna start very small, okay? So, what is a model? Okay, so models are any representation of reality. So it can be a drawing, it can be a model of a building, it can be a wax doll or any kind of doll. So any kind of representation of reality can be considered a model. And the amount of details in a model makes difference. Okay, so in that doodle, previously,
That can be anything. It can be me, that can be Morgan Freeman, that can be Professor Luis Paulo, the David, but anyone. And when you begin to put details on your model, the less you need for the represent. So here we don't need like a photograph to know what people, what person that is. Okay, so but even a simple model can tell us a lot. Okay, so not all models have to be so carried with details and complexity. So even a simple model can tell us a lot. So what can we extract of information from that drawing? The doodle, it's a living being, it's not an object. It's from an animal kingdom, it's not a plant, it's not a bacteria. It's bipedal, okay? It's a hominid, and it looks at it. It's not used for information, but there you go. But so from more than 8 million species, our simple model allows us to convert to a single species. So just to introduce you the mindset that a model has to be as complex as you need it to be. Okay, so it depends on your application. So, and we have several kinds of models, several types of models. We have statistical models. Okay, so we do have regression, we have linear trend, we have machine learning. So these kinds of models try to represent the behavior and characteristics during time of a phenomenon that you want to predict. So it has a history, and based on that history, it tries to predict the future, or it tries to construct a model that you can use for other applications. So in that way, we have kind of a training set, which the model goes through your history, okay, and you have a test set. So you separate a part of your time series to see if your regression, for example, fits well with your data. Okay, and you have mathematical models. These are the ones we're going to study more in this course. We're going to see more in this course. So we have regional or short-range models like BRONZ, like WRF, like GFS, like NEMO, that you're going to see tomorrow on the surf session. We have hydrological models. These kind of models, they represent how the rivers are gonna behave, or how much water they're gonna have for this month, for example. And you have climate, or more recently, Earth system models. So you have CSM, you have the climate model for the GFL and GFDL, sorry, and all of those from the IPCC. Okay, and they describe phenomena through equations. So you have a physical phenomena, and we describe them through equations, and then we construct these models. And just for an example of how to build such a model, a mathematical model, I have here a wave, and that's just an example, just because a wave is more easy to represent or to look in the nature. So in a certain way, or I can describe this wave through a mathematical formulation. Okay, so I take this nature, okay, and I describe it through math. And then I apply numerical methods so I can be able to solve these equations, okay? And then I built a numerical formulation. And that is what we solve the numerical models. Okay, this is part of the WaveWatch 3 code, okay, that I took from the CSM, which is, this is a Earth system model, this is a wave model, and this is exactly what the computer reads and tries to solve. Okay, so we take a natural phenomenon, we kind of transform it into a math formulation, and then we apply some methods to build it into a numerical formulation. It's not, yeah, I want you to try to understand all these formulas, just so you to have a notion of how we build a model, okay? And how does a model work? So very simple here again. I have a person here and I have a patch of almost 300 meters of extension, and I have some boundary conditions. And I have initial condition, which is time is 0, the space is 0, and I'm gonna evaluate this person every 10 seconds, okay? And I have that it's gonna run, he or she, this person's gonna run at a pace of 9 meters per second. What I have is that at the time 1, which is 10 seconds, remember that I'm gonna evaluate every 10 seconds, it left from the point 0 to point 90, and so on and so forth until the end of the fetch. So after 30 seconds, this person went through the fetch. On the other hand, if I have a much slower person, what do you think is going to happen? It's going to take much more time, right? So here I took 3 time steps, okay? Every 10 seconds, I have a time step. So it took here, this person 3 time steps, and here it took 9 time steps. So that's essentially how a model works, okay? I have a phenomenon, and I have how it's gonna evolve over time, and I have my initial conditions, okay? Which is, we're gonna see more later. So knowing how my process works in its initial stage, I can determine its evolution in time, okay? So now I'm gonna show you some types of modeling, and the first one is hindcasts or back testing. Which Paulo said, talked about that a little bit earlier, with when we went to do simulations to test a model. So I want to see if I can represent a phenomenon that happened in the past, or I can, like with that project, I want to test different conditions of meteorological and oceanographic conditions, to see where my oil is gonna go, so I can see where my most sensible areas are. So I do that for the past, okay? It's not a prediction, it's a hindcast. So also simulations of past periods are performed and compared with measured data to validate a model. So, and they can also be used to reproduce phenomena of interest, like I said. So here are some examples. I have here Earth system model. Different, it's not doing things for the future, but doing a hindcast from 1979 to 2005 for both examples here. Here is precipitation, and here is the zonal wind. So you can see here, so why am I doing this? I can access the sanity of a model. So I implemented a model does it represent the climatological features that I'm used to, that I have in my papers, that I have in my books, so that I can say, yeah, this model represents climatological features, it represents reality, so I can use it to study other things of interest, okay? And also validate the model as a control parameter. So this model here, okay, it represents reality, so I can try to alter parameters. For example, if I wanted to increase precipitation in the Amazon on 3 times to see how the system reacts. I can do that, but first of all, I have to have a control parameter. I have to have the reality. I have to have what? Here I have my reality without any change. Then I can make a change and I can compare with my reality. Okay, so far, so good? Yeah? Remote as well? Hopefully. So this is a real case as well. So an example of a high gas, a storm here in Rio de Janeiro, Brazil, 2018. We had a strong winds with gusts above to 90 kilometers per hour. We have flooding, we have inundations, falling trees, collapse of cycle paths. We had 6 fatalities, so it was very, very concerning event. Here we have satellite images, and we can see the storm here approaching. And here as well, here is the radar data, okay, and we have here the core of the storm. So what is my interest here? I want to implement a model to see if I can represent this condition, see if I can represent where the storm hit and how and with which intensity, so I can maybe study how it was formed. Okay, so where did it come from and how it was formed? So maybe if I can understand how it was formed in another event, I can identify that by satellites and then try to prevent this kind of things. So this is a kind of study that we can do, and this was done with the regional model called ETA. Okay, and this is a satellite, and you can see that here is the precipitation, and it can represent kind of well the storm. So now I can understand how from where it came from and what type of atmospheric phenomena made up this storm. Okay. Another type of model are the predictions, and I think these ones are the ones that we are most used to. Okay, so we predict to the future. We are interested in things that are not happened yet. So this is a line from Yerkes, 1904, was a very important study that with modeling. So given an initial field of the state variables, that could be pressure, temperatures, temperature, winds, it worked with atmosphere. Knowing the equations that govern their evolution in time, which are the same ones that we can use for hindcasts, we can in principle find their future state. So the thing that I told you. So remember that guy that was running? Given an initial field of the state variables, so time and space here in their evolution in time, I can predict or determine their future. Okay? So of course, models are very powerful tools. We can do a lot of them with them, but we have to understand that they carry a lot of uncertainties. And do not think that we're gonna implement an ocean model for Guanabara Bay here, and if you, I don't know, put a leaf in the water and see where that leaf goes, then your model is gonna tell you the same thing. It's not, okay? You have a lot of uncertainties, and maybe at the end of this slide, you're gonna ask me, so why do we use model? It has so many errors, but it's still very useful, okay? And again, we have to know which tool we want and we need to have for what kind of application we are interested in. So remember that way we talked about earlier and the math formulation of it. So I have errors in the mathematical representation of the process. Of course, I'm taking something from the nature and I'm writing an equation of it. Naturally, we're gonna have errors. Maybe we don't even know how to represent all of we see in nature in math, okay? I have errors in parameter estimation, and then I have errors maybe estimating the height of the wave or the period of the wave and stuff like that. So if I don't know exactly the velocity, you can agree with me that my equation is gonna have some errors, okay? Again, this kind of equation doesn't have, it can be solved, okay, analytically. You can do math and solve that on paper. You cannot. We have an infinite solution with infinite limit. So what we do, we have, we kind of, let me see.
Numerical approximation.
Yeah, we kind of, yeah, numerical approximations. So we have truncation errors. So because you have like an infinite number of processes, and you have eventually to, okay, that's enough. And you have truncation errors, as you have to stop at some point. Yeah, of course.
Translate this passage that leader is saying is basically is passing the real and continuous word, the discrete word. Okay, so we're going to transform the points operators, okay, the derivatives will pass to deltas, finite difference, finite equations. So that's it.
Yeah.
Difference equations will become algebraical form. That's it. And of course, you have a lot of errors involved in these things.
Involved in that. Yeah. Yeah, because you know what, we live in a continuous world, but we always measure our continuous world in a discrete form.
Yeah.
Okay, we have our measure tape has 1 centimeter, 2, 3, 4. We cannot measure between the millimeters. Okay, so this is an error because we cannot measure a continuous world. And of course, during calculation, we have rounding errors. Depending on your machine, we have a bigger or smaller representation of your numbers, okay? And then eventually we have an approximation solution that is good enough so we can use our numerical model. So believe me, even though all of these errors, numerical models are still very, very useful in our world of oceanography, meteorology, and of course, to estimate threats in coastal zones. So, talking about horizontal grids, we talked about continuous and discrete world. So we try to imagine that we're gonna implement a numerical model from the whole world. I cannot, and there is no way to solve those mathematical equations on the whole world. I had to choose points on where I'm gonna solve these equations. So imagine that temperature field. Those points will be some points in my field, or in that case, imagine the whole world that I'm gonna have temperature values and where I'm gonna solve my equations and where I'm gonna have my solutions. So now for the whole world, I have these nodes here where I have my equations and my solutions. Okay. And we have different types of grids, okay, of how to represent these points in my domain. Okay. They can be divided basically into two types of grids. We have structured grids, so they have the same spatial resolution throughout the domain. And if you can imagine the whole world, so same resolution of the whole world, so they are easy to implement. They have greater numerical stability. We're gonna talk about this kind of things now, but if you're gonna work with numerical models, it's something that you should study a little bit about. And to increase the resolution near the edge, so in one part of the domain, you should increase resolution in all parts of the domain. Okay, and of course, increasing because you have to increase resolution in all of the domain, it causes increase in computational cost, which is how much time your computer is going to take to solve your equations. And you may think that's it's not an important thing, but there's a very funny example that we in Project Azul that we had in our lab. And the first time we were gonna implement an atmospheric model, like a weather prediction model, it took like 3 days to predict for tomorrow because of computational cost as well. So it's not a thing to discard. So it's very important.
Especially for operational purposes.
Especially for operational, yeah. So we have here some examples of structured grids. So this is for the community atmospheric model. Okay, it's the atmospheric model within the CSM, which is a system model. Okay, this is 2 meter air temperature. Okay, it has 288 points in longitude per 192. Okay, so it has 288 here and 192 here. The same thing can be done for the ocean, and different in the atmosphere. Here, we don't have points in the continents, of course. Okay, so we have 360 per 180 points. And again, in each node here, the formulas are gonna be solved by my computer. Okay. And we have unstructured grids, also called meshes. So they have variable spatial resolution in the domain. So I can have greater resolution in one part and coarser resolution in other parts. So when we're talking about domains with coastlines, they adjust better on these regions. Of course, it's ideal for cutout regions. It's possible, like I said, to have greater resolutions near one point and less in the other. And adaptive meshes, which is something that is growing, can reproduce various scales of interest with reduced computational cost. Okay, so I have here two types of meshes. We have a local mesh, this is within a lagoon, Another thing, you can see here the darker colors are where we have much more nodes or much more resolution, much more points. And in lighter areas, we have less points. The same thing here in a global mesh. We have in darker areas, we have much more resolution. Okay, so again, why we are interested in meshes when we have grids? Because of this kind of things. We have a grid, and mostly a global grid, and I talk about that when we discuss downscaling and why to do it. When we get near the coast, this kind of things happen. We don't have solutions here. When the blank areas is where I don't have data, I don't have information. So around islands as well. So because of my continents are not squared, I cannot reproduce well the coastline. So what we do, we use meshes to represent much better these regions. So this is the ROMS model. ROMS can use both meshes and structure grids. So here we have denser grid points near the coast. You can see here it's in kilometers, so it's the distance between points. Okay, so we have less distance here than in here. Same thing there. Okay. So I have 250 per 360 points. Okay, so far so good. Yeah. All right. So another example of meshes is the MPIS, the model for prediction across scales. It's an atmospheric model. It's gonna eventually replace the community atmospheric model that I showed earlier. And rumor has it, maybe even worse. So it's a global model, but it's also called adaptive mesh, because it can go from global to local or regional in the same simulation, in the same domain. Okay. So we have here 90-kilometer mesh global with 25-kilometer refinement. Okay. So instead of I have a simulation with 25-kilometer all around the globe, I reduce computational cost by using refinements only where I need it. Okay. It just another thing about MPIS, it has these types of cells. It resembles a honeycomb, so that's why it can be next to each other. And if I have a smaller one, I can put three smaller ones inside or next to a bigger one, so it goes well to represent the cutout of continents. Okay, and this is the type of So, and we have also staggered grids. This doesn't have anything to do with horizontal resolution or types of grids. It has to do with how the variables are calculated inside the model grid. Okay, so so we have, imagine that we have a grid of a square or even a cube if you consider the vertical part. So I have types of grids that I have tracer and density would be represented by T, and you have components of velocity. So each type of variable is solved in one part of the grids. And this has everything to do with the type of model that we are talking about. So the C grid is usually, we have velocity being calculated over the edges, and we have tracers in the center of the grid, and these types of grids are used in ROMs, the ROMs model, the MPIs that I told you, the NEMO that you're gonna see tomorrow. And other types of grids are more for climate models and Earth system models, like the B grid, where the velocity is solved in the nodes, okay? So the Parallel Ocean Program from CSM and the Modular Ocean Model from the GFDL, both climate models, okay? So differences between them. So the big grid, again, from climate models, mostly used in coarse resolutions, like I said, does not resolve inertial and gravity waves well, and resolves geostrophy well, normally used with vertical discretization in vertical levels. And the C grid is mostly used in finer resolutions, so in regional models, resolves gravity waves well, depends on where resolved velocity field features to resolve geostrophy, and typically used with vertical discretization at isopicanal levels. I'm not gonna talk about vertical discretization today, but why am I showing this to you? Because when you're gonna apply a model, okay, it's important to know its characteristics and know also its, again, it's what it cannot do, more than what it can do, what it cannot do, and you gotta know that, because you're gonna evaluate your results based on that. Okay, so if I have a model that does not resolve inertial and gravity waves well, and I need it to know about gravity waves, and if I'm interested in gravity waves, maybe I'm not going to use this type of model. So this information is useful for you. Okay, so now we're gonna talk about horizontal resolution and what does that mean. So remember our world and our grid here, and remember that the equations are solved for each node here in our grid. Okay, so we have this spacing between grids, okay, between nodes, and this is our horizontal resolution, okay? So in our world, we have 360 degrees in longitude and 180 in latitude, okay? Our horizontal resolution will be the number of points, the degrees in longitude or latitude that we are gonna represent over the number of points, okay? So if my world, who has 360 degrees in longitude and 180 degrees in latitude, if I have 360 points and 180 points, I have a 1 per 1 degree resolution, okay? Because I have 360 degrees over 360 points, okay? Another example here. So that's what happens in this case, okay? This atmospheric model, okay? So another way to understand resolutions in kilometers, okay? So if I have my Earth diameter is 12,733 kilometers, I have my radius of around 6,000 kilometers, okay? So my perimeter, my circumference is done by this equation, so I have 40,000 kilometers of circumference over the equator, okay? Remember that. So, see, over the equator, I have this circumference, and we have 360 degrees. So if we divide one for the other, we have 111.12 kilometers. So 1 degree in the equator means that distance. So if I have a model, an ocean model or atmospheric model of 1 for 1 degree in resolution, I know that over the equator, I have a distance between my solutions, between my data of around this distance. Okay? Of course, when we go north or south, the circumference of the Earth is gonna decrease. So we had to do another calculation. But over the equator, we have an idea of distance that we have of between our grid points. Okay, so we have some examples here. We have the community atmospheric model. I have 288 for 192 points in longitude and latitude, and it's global. So if we apply the equation there, the number in degrees over the number of points, I have that this model here is 1.25 degrees per 0.94 degrees in latitude and 1.25 degrees in longitude, okay? If we apply the distance over the equator, is this distance. So each grid point in my model has this distance over longitude and this distance over latitude. Okay, but what if in a non-structured grid, okay? When I have, here I have 250 points in longitude and 360 in latitude. Because this grid is not rectangular, okay? So here, it's difficult it's not the latitude, the longitude limits are not well defined. So it's difficult to do this kind of calculation. So usually the model kind of can give you already the distance, or you can kind of, some models you can input, I want this kind of distance, and they give you the solution. So this kind of equation does not apply in unstructured grids. So, okay, so I have a 1 degree per 1 degree model resolution, and I want to increase my horizontal resolution. So, or in this case, I have 25 elements or 20 elements here. I have my Southeast Brazil here, but I want more. So what does that mean? Is that I have, if I take one grid element here, is about 100 meters. So I have every 100 meters, I have a solution. That means that for 100 meters square, I have, for example, one value of velocity of ocean current. Okay? If I increase my spatial resolution, and now I have 4 grid elements, so I have a distance, a spacing of 50 meters instead of 100. I increase 2 times the resolution, and now I have 4 grid elements. What does that mean? Is that instead of 1 value of velocity, now I have 4. And you can see now that not all 4 are going to the same direction. So not only I have more values of velocity, I have a refined information, I have more detailed information of what I'm seeing, of what my coast current looks like. Okay. So if we add breakpoints, we increase resolution, we decrease spacing between points, it improves process representation. Okay. So far, so good? Yeah? Okay, so if we are going to draw a parallel of increased resolution would be with picture pixels. Okay? If we take a picture and we zoom in, we see that these squares here represents pixels. Okay? In a low resolution picture, we have bigger pixels. If we increase the resolution of this picture, you can see that here we have smaller pixels and we have better representation. Okay, here we can read what's written on the bicycle, and here we cannot. Another example is here. In 1:1 pixel, we have nothing. And we can increase to 100 to 100, and we have a perfect emoji. Okay, so this is what happens when we increase resolution. Okay, in the ocean, it's the same thing. Okay, this is our three versions of the same ocean model. Okay, it's the climate model from GFDL. This is a 100-kilometer resolution, which means that every 100 meter I have one information. And when I increase resolution, you can see how much better I have my temperature distribution, and even my continent representation is better. Okay. But again, imagine here how many equations I have to solve every 100 kilometers, and how much more equations I have to solve here in 10 kilometers. Think about if I want to see large scale process, global scale process, do I really need this, or this will suffice? That's the kind of thing you need to think about it when you're gonna acquire or run your own models, okay? This is always better. I agree with you. This is always better. This is the ultimate goal. But how much time is this gonna be ready for you? More than your whole thesis time duration? So maybe this one is better, or even this. It's always gonna show you about computational cost. It's the same thing. How much time do I take to draw this? I timed it. Okay, I did my own drawing and I timed it. It's around 5 seconds to draw this. What about that? What do you think? Several hours.
Was it you?
What?
The draw, was it you?
I can only draw this. And very badly. For me, it would take a lifetime, and I wouldn't finish.
Several days, months.
So this is what computational cost looks like. If I only need to have a model that gives me the species, maybe 5 seconds, it's enough, because it's gonna have the same information as this one. If I only want to have a model that will give me the Homo sapiens species, why do I have to spend several hours in my computer if I have the same thing 5 seconds? So think about that when you acquire model results, or you're gonna run your model. What do you need that model for? What you're gonna investigate? Okay. Go ahead.
Oh, I already said one thing that came to my mind now. Coarse resolution grids, like the primate global models that you just say,
sometimes seems for our purposes here, for coastal resilience purposes, don't have too much resolution to solve. Yes, you don't have too much resolution. And maybe you can use this kind of low resolution information in other way, understand processes that would affect your regional area. And
No, of course,
give integrate this with the final proposal. Of course, the higher resolution models are most, how can I say, can apply in a better way to investigate coastal resilience acts or coastal processes in a way. But you can use coarse resolution to understand some processes in other scales that could affect the regional areas.
No, of course, maybe you have your coastal process, but you need to know what happens in a global scale.
Yes. And
some things like that.
And then we have today a lot of products that are publicly available, not only in Europe. For example, OKEANO has a very nice base, but also in the United States. So it's nice to work what we have now in hands, okay, to use.
So another thing that you have to have in mind about, but if you can think, okay, I'm not gonna run the model, I'm just gonna acquire results, so I can acquire 5-meter horizontal resolution results because I'm not gonna run the model, even though I'm interested in global scales, but things aren't always pretty. If you have higher resolutions, your file will be bigger as well. Okay, so I had a experience recently. I was acquiring Earth system model projections, and I acquired the in a monthly frequency. So one solution per month, one value per month. And the global file is not a global, was cut into the South America. It was about 200 megabytes, okay, not much. And then I switched to daily frequency and went to 8 gigabytes. So yeah, just for the South America, just one. Yeah, I think it was 1 month.
1 month.
Yeah, so think about that. Even though you're only gonna use the results, you're not gonna run the model. Not only the average solution of Cursor models are faster than high resolution models, the files are much lighter. Okay. And okay, so again, if I want to increase resolution, I increase 3 points. I increase physics and dynamics. I increase integration time. I increase processing. So, but I have more information. Okay. So in this example, I can run a 2-day forecast in 5 hours. If I increase the horizontal resolution 2 times, I go to 20 hours for 2-day forecast. So another thing to think about. And again, we need to know the scale of interest that we want, okay? So if we want to work in a territorial way, we don't need to work with global solutions or global models. You won't have much or any information in territorial way if we work with only Earth system models, which are global and very coarse resolution. okay? And we have to think about the scales of interest of the phenomena we are interested in, okay? For example, in the ocean, air-sea gas exchange happens in 10 to minus 3 seconds, okay, in temporal scales, and like 10 to the minus 6 in spatial scales. It can happen in very little areas in very fast way. On the other way, deep water formation can take several years and happens in a very wide area. So just an example of know the phenomena you want to represent to know what kind of tool is better for you. Okay. And another example of scales of interest we have here, for example, in ocean, bubbles happen in a very small scale, both temporal and spatial scale. And if we are talking about Milankovitch cycles or thermal circulation, it's much larger scale. Same thing for atmosphere. We talk about tornadoes or turbulence cascade. They are happening very different scales. Okay. So now we're gonna talk a little bit about grid nesting. We're gonna talk more about that when we talk about downscaling. I don't know which time is
3 o'clock. What time is the clock?
The clock?
3. Coffee is at 4.
4, okay.
Oh,
I have 1 hour.
According to the program. But
No problem.
you always have to change it if you.
Okay, can we go for another hour? Yeah, okay. So grid nesting. Okay, so it's the process of nest one grid inside of another. Okay, and why we do that? Because we can increase horizontal resolution and temporal resolution without have to increase in all of our domains. So, for example, this is the example of ROMS, the Regional Ocean Modeling System. I have 3 nested grids, okay? 1 kilometer, 240 meter. So why is that important? I was interested in that area, and I wanted that area to have 40 meter horizontal resolution. But was not feasible for me to have all of this area or all of this one with that resolution, with I solving my equations every 40 meter. So what I can do, I can have this region with 1 kilometer, and then I have an intermediate one here with 200, and I can put my interested area with 40 meters. Okay. And why didn't I just put this one with 40 meters at once? We're gonna talk about that a little bit further when we talk about initial and boundary conditions. Okay. So you can see here, I can with this, I think this one was 200 meters. I do not have information in all Guanabara Bay. And now with the 40 meter grid, I have the information in all the bay in
200.
this one?
Yes.
Oh yeah, the 40 was this one. Yeah, I think it's the next one. Yeah.
It's
Okay. So the same thing. I have here I have 1 degree, 1 kilometer, sorry, 200. And we can see here this this is this one. Okay, here I don't have any information. And here in this loop here, I have, now I have information because I increased my grid.
Is this a three-dimensional model or?
Yes, it's a three-dimensional model. Yeah, I'm only showing you the latitude and longitude, but it has depths as well. Okay, so when you increase the resolution, you also increase representation in the vertical. You can, you do not have to increase the vertical levels, but if you're increasing the horizontal one, you also improve representation. So this is for an atmospheric model, okay, for work, the weather research and forecasting. Okay, this is a 27-kilometer grid. And this is a 9-kilometer grid, more for the Rio de Janeiro. Here, this is Guanabara Bay, but
Simulating a passage of a code from.
yeah, this is the passage of a code front here. And we have, you're gonna see here. Okay, now. Where is it? Okay, that's, yeah, here. You're gonna see here much more detail. And here for the Guanabara Bay, 1 kilometer grid. Okay. So types of grid nesting. I have one-way grid nesting, which means that I have mother grids, I have child grids, and I have information sent to my other grids. So in one-way nesting, I only send information from the coarser grid to the finer grids. Okay. So this one sends to this one, and this one sends to this one. Okay. In a two-way nesting, I have this one being sent to this, and the other way around as well. So the feed is going in both ways. Okay. So in another example is for adaptive mesh that you already seen. In that kind of mesh, there's not a different grids, okay? There's only one mesh that is changing the resolution in certain ways. So we don't have this type of thing here. Okay, it's just another way, but this one is a regular grid. Okay, in unstructured grids, you can increase resolution without changing grids, like we said. Okay, so far, so good? Yes? Okay. So we're gonna talk about initial conditions. So initial conditions, like we said, is the initial state that my model is gonna begin its integration, okay? But we have a problem with initial conditions because we don't know the exactly initial conditions in any model, okay? Because measures cover only a few points within the domain, okay? Interpolation, which means that I have one measure here and one on the wall, and if I interpolate from here to there, I can do like a linear interpolation, and I have kind of solutions or information between both points, but it's not real, okay? I made it up through calculations. So you're going to say something?
You have always a problem to misrepresent.
Yeah.
Misrepresents the initial conditions of your prognostic variable.
Yeah, we do not have the exact initial conditions. So it remains to use climatologies or model results, which you already learned that have inherent errors, okay? And climatologies can be misrepresentations as well, because they are averages over a long time, okay? So if we don't know where the person comes from and when it comes from, I cannot define its evolution. So if it comes from further, go ahead, from here or here instead of here, do you agree that my solution is going to be different? Yeah. So that's our problem here. And so atmospheric and ocean models use initial conditions. These are some of the most common initial conditions of ocean and atmospheric models, or these are variables that we have to do in all of our domain. So if you're gonna run a global model, we have to have this information for all the globe, okay, at time 0. Okay, so for the oceans, the velocity, temperature, salinity, sea surface height, and for the atmospheric model, also velocity, means temperature, geopotential height, relative humidity, and pressure. Some models can have more or less of these variables, need more or less of these variables for input, okay? So, and initial conditions have everything to do with chaos theory. Have you ever heard about chaos theory? Yeah. So I think you heard this sentence: the flapping of a butterfly's wings in Brazil can generate a hurricane in Texas. And Lawrence is the responsible for the chaos theory. And chaos is a pattern of organization within a disorganized phenomenon. It's an organized disorder or apparent causality. So a chaotic phenomena is a phenomenon that cannot be described and predicted by mathematical laws. For example, dripping from a faucet. We cannot yet describe it. Okay, we cannot describe it in equations. Okay, so what in nature is chaotic? Okay, our nature here is chaotic. So everything we want to represent in the numerical models is chaotic. Okay, so what it chaos does in numerical models? So it does like very small changes in the initial conditions can lead to very big changes in the end, because it's a nonlinear evolution, okay? So it makes the system unpredicted and chaotic. So if I don't know the exact initial condition, I've already have a problem, because if I don't have it, I can end up with a solution that is very much away from the real solution, because my system is chaotic. Okay, so just an example of chaos, and chaos can happen in our day-to-day life. So for example, John was riding his motorcycle to take an exam to enter a certain university. Along the way, John has a flat tire, so he cannot arrive in time to take the exam. So he had to enroll in another university. So the place, the people he lived with, they interact with, the job and internship opportunities could have been completely different if John had entered the university 1 instead of 2. Great? Yeah, okay. So a flat tire, which means a small change in the initial conditions, okay? It could be anything, it could be a heavy rain, can change John's futures completely, to the point of altering John's children and grandchildren can be if John met his wife in the university. Do you agree that John's children would be completely different from life of University 1 from 2? So, and just out of curiosity, films that address the chaos theme are Back to the Future, the Butterfly Effect, About Time. Did you see that? Did you see any of this?
Yes.
About Time is horrible. Don't watch it. I could not stop crying. Horrible. No, it's an amazing project. Okay, so that is chaos. Okay, so Lawrence addressed that, and his hypothesis before learning chaos was small variations in the initial conditions would all result in small variations in the results. Makes sense, right? He made an atmospheric model based on 12 variables and repeat the simulation, changing the initial conditions through rounding. Okay, so he went to point this number to point this number. So very, very small variations in the initial conditions. So for short periods, the hypothesis was correct, but for longer periods, for example, 1 month, the results were completely different. Okay, and this is the Lawrence attractor, which is it's very famous. And because why it's a butterfly effect? Because it resembles a butterfly. Okay, so sensitivity to initial conditions is associated with the non-linearity of the systems. And another thing that is important here, we are talking about climate change and climate predictions. So again, for Lawrence, for small periods, the results were not that different. But for longer periods, and we're talking here about climate projections for 50 years from now, the solutions can be very distant from the real thing. So this is the thing that we have to have in mind when we gonna work with climate projections, okay? And just one example of this chaos theory happening in real life or in real ocean. This is a project from Ondo, okay? This was the launching of 5 identical drifters. They were launched at the same point, at this, they were identical, launched at the same point, at the same instant. They cannot, so small changes in the initial conditions. So I picked one, I launched it. I picked the second, it's not the same instant. This one was already a change. And you can see here how different they evolved over time. Okay, you can see all 5 of them. So this is chaos theory in real life. Okay, so how are we? Good?
Yeah.
Still good? Yeah? Okay.
Perfect.
So far, so good? No questions? People in remote, no questions as well? No? Okay. So boundary conditions. Again, our person here running on our crutch or treadmill or something. So the boundary condition is associated with the information of how the process is going to evolve. In numerical models can also be called forcing. Okay, so here for this person, initially he was gonna run at 9 meters per second, but what if he was running at 8.8 or 9.2? Okay, do you agree that the evolution will be, of course, completely different? So in numerical modeling, we have here our ROMs implemented in our Guanabara Bay. Our boundary conditions would be information of the ocean from this part and also from this part. Okay, these are open areas. I have to have atmospheric information from to the ocean, so winds and radiation And precipitation, because precipitation is gonna alter my salinity, okay? And also for this example of the river information, this river discharge, okay? So these are the informations that our models need, our regional models need. Because I want to solve only this part of the world, okay? I have to tell my model, okay, how this ocean here, these variables of the ocean are coming to my model domain, or how my atmosphere is evolving over time, and how it's gonna affect my ocean, and how is the river discharge over time and it's going to affect my solution, okay? Okay, so, and unlike the initial conditions that must be the input at the 0 moment, the boundary conditions must be defined for all time steps. So if I'm gonna have our solutions for 1 month or for 1 day, I have to give 24 informations of the ocean, 24 informations of the atmosphere, also the river. So I have to tell my model domain how are all of those things are evolving over the time of my integration. Okay. So for just for example, for an atmospheric model, it needs from the ocean or the sea ice albedo, okay, which is the reflectance of the surface, and the surface temperature. It usually, okay, this is usually. Some models can need more or less. And for an ocean model, what it needs from the atmosphere, it's a lot more. It's wind shear, okay, how is the wind over the ocean? It's important for currents, it's important for waves. The radiation, so how the radiation is coming to the ocean, the air temperature, and the sensible and latent heat, because it's important for fluxes. Okay, so because of the components are in contact with each other, this information needs to be transmitted. So for ocean, for the ocean model, the atmosphere will always have to transmit the boundary conditions, okay? If it's in a river region, you have to have river discharge. If it's in high latitude, you have to have sea ice information. Okay, so depending on what your model is, what your domain is, you have different information that you have to give. Okay. So another example here. So here, for my regional ocean model here, if we only think about the ocean boundary conditions, I only have 3 entries here. Only have 3 open boundaries, so I have 3 regions that I have to give boundary conditions. But in the atmosphere, I have all of 4 sites to give boundary conditions to. Okay, so the basic modeling formula. I have an initial condition, I have a boundary condition, and I have a geophysical model which give me results. Okay, and I have several types of models. Okay, so I have regional models like ROMS, NEMO, WRF, and I have global models like POC, like MOL, like CAM, like or global models. Okay, but what is coupled modeling? And we're gonna talk about couple modeling now. It's when two or more models are working in an integrated manner. Okay, so now the basic formula for coupled modeling. I have an initial condition, a boundary condition, if exists, because if it's a global model, I do not have to have it. And I have a geophysical model with results. And now I have a second geophysical model with initial and boundary conditions. And I can have more than two. Okay, so now remember when I had only a atmospheric model, a motion model, and all the boundary conditions that they needed? Now if I have a coupled model, I do not need albedo and system phase temperature to be given as a boundary condition, because my ocean model is gonna provide those variables to my atmospheric model. In the same way, I don't have to have all these variables here from the atmospheric model, because from boundary conditions, because my atmospheric model is gonna provide those informations to my ocean model. Okay, because they talk to each other, they exchange information. Okay, so what was provided as boundary condition will now be provided through the model's prognostic results. Okay, so I do not need to provide the boundary conditions at every time step, at least these. Okay, because my numerical models are gonna provide to themselves. Go ahead.
So they are running in the interactive way at the same time.
Yeah.
The same, almost as the same code, the same computation.
Yeah, instead of running an ocean model, I'm gonna run the two of them together.
Or three, if you have
Three or four, or four or more.
Yeah.
And some examples are here. We have the coast, which the coupled ocean atmosphere wave sediment transport. So we can have four different models working together, or three if you want to. Okay, maybe it's an application that I don't need sediment, or maybe it's an application that I don't need waves. So I have a sediment transport model, wave model. I have two options for wave. I have wave watch, and I have one for restricted areas. I have the routes for ocean, and I have work for atmosphere. And you have a coupler, and I'm gonna talk about that in a little bit, which is the responsible one, which is a responsible one to exchange this information, okay, among the models. So what happens is that, like I said, instead of running just an ocean model, I'm gonna run an ocean model, an atmospheric model, and a wave model together at the same time. And then I have a coupler that is responsible to make the exchange of this information between the boundaries and the models. Okay. And this is an example of a coupled regional model, okay, for regional regions. And this is an example of a global coupled, okay, standard system models, the CSM, Community Earth System Model. It represents, it tries to represent all of our Earth system. Okay, so we have river transport, we have ocean, atmosphere, waves. We have a model for the surface of the Earth. Okay, and we have a model for their sea ice. They were developing a model for the land ice, okay, for the Greenland. And of course, we have a couple. So now I can, if I want to run 6 models together and have the solution that represents in the best way that we possibly can nowadays the climate of our Earth. Okay, so what is the coupler? The coupler is the most important guy in a coupled model. It's a component central and necessary acts like a communicator between the components. Okay, so imagine this. I have two global models. Okay, I have an atmospheric model with 138 kilometer grid spacing, and I have an ocean model with 111 grid kilometer spacing. Okay, and when we are talking about boundary conditions, the information that my model receives, it has to receive in the grid it's implemented in. So it has to receive in a 111 grid, okay? So what happens if I send my atmospheric fields with 138 kilometer resolution to my ocean model? The model will return a contour error or some other kind of error. It's gonna stop working because it's like me trying to use my 4-year-old cousin shirt. I cannot do it. Okay, it's not gonna work. All right. Or my 4-year-old trying to use my shirt. It's gonna work, but it's not gonna look good. Okay. So what the couplers do is that receive is the prognostic field, receive the atmospheric field. It's make calculations to give to the ocean the atmospheric field in a way it can receive, which means not in its own grid. Okay. So it receives a 138 kilometer. It goes through the coupler sends to the ocean this field in 111. Same thing happens in the other way around. The ocean sends a 111 kilometer field, goes into the coupler and goes out as a 138 kilometer grid. Just so we can think about, remember when you're talking about errors, imagine here that here is a math calculation. Okay? I have a smaller grid spacing here than here. So to perform these calculations, I do interpolation and I kind of make up data. So it's another error that I'm putting into my model. But it's a way to improve representation because now I don't have to receive atmospheric information from another model from that ran differently than what I'm running right now. I'm running everything together. It's the ultimate thing. It's the most optimized way to have most close to real conditions. But again, just know that I'm putting errors in my solutions. Okay? Yeah, is that clear? Okay. So that's it for now. 3:30. Can we go to the
Coffee.
Yeah. Can we go to coffee now and then come back? No, 30.
30 minutes, yeah.
Yeah, 30 minutes.
30 minutes.
Yeah?
Yeah.
Okay.
Questions?
Questions?
Online.
Online questions? No?
How the couple models.
Okay.
How do you know which model fits first at the same time?
It's not exactly at the same time because they run at different paces. Okay, but the coupler doesn't have to receive one and receive the other. It's receiving and sending. Doesn't have to receive it.
There is basically two classes of it's like that. The synchronous one, the couple that is synchronous, so step for changes in information between atmosphere and ocean, for example.
and they are synchronous working. So, for example, sometimes you can start the integration with the ocean model because it have an inertia to represent the temperature. It's lower than the atmosphere. And then once lies, they start to change the atmosphere. So we have different approaches, synchronous and asynchronous. So synchronous and asynchronous, they're not synchronized at the same. It depends on like that.
Or what you want to.
Yes, depending on what you want to investigate. And I don't know if I have available to see every couple of models, these two options of integration. Okay. Some models are constructed with a synchronous and other models they have a synchronous approach. I haven't really seen the both types.
Just like yeah, do you have models of initial conditions and
Yeah, initials, yes, they do not have boundary conditions. Just even with couple models, I have to know where I'm coming from. Yeah, where to start, where I'm starting.
that comes from one model?
Or each model has its initial conditions, but I only have to give it initial conditions.
And
The boundary conditions will come from another model. If think about Earth system model that have all models, okay, I don't have any boundary conditions. But if we are thinking about, I don't know, we are talking about high latitudes, and I'm only simulating an ocean and sea ice model. Okay, I have two models, and I don't have to have boundary conditions from sea ice and ocean, but I still have to have boundary conditions from the atmosphere, for example. So it depends from your simulation. If I'm representing all of the components of the Earth system, so I don't have to have initial boundary conditions, only initial conditions. But when you talk about, for example, projections, we don't have boundary conditions, but we have forcing. So now I have to include CO2 and other greenhouse gases, volcanic activity, and stuff that happens in a larger time scales. Okay, so we have forcing. So what I'm gonna force the model to go in a certain direction.
it's also linked to what we talked about in the don't know much. IPCC don't know much about that, so that component.
Yeah, right, that's it. Okay. Anything else?
Compared to the atmospheric model, that is the same principle that we do in initial condition and boundary condition, or it has another way of working, and also the grid mixing methodology. We can use it also for other models like biochemical ones, because the analytic on biological components is different from
you can answer better.
No, I'm not a specialist in biological science.
Yeah, I'm excited about this integrated coupled models.
Yeah.
I'm trying to think about integrating like the biological component into this components.
It's amazing. Yeah.
Some models, for example, as the launch model, has a package to simulate biogeochemical site inside. And biogeochemical variables is a variable and any other variable at the ocean and the atmosphere. So, talking about numerical modeling, it works this way. You need to have initial condition of your biogeochemical variable, boundary conditions. Plus, equations that simulate how the transformation of carbon, for example, will work in your model. Then you have more complex models and less complex models. For example, the coast, I don't know if in the version of the coast, the coupled model that
Lydia has showed to us. I know that the bronze model has a package inside to simulate the biogeochemical cycle, but I don't know if in the post version this code is available to execute. I think so, because the biogeochemical. I think there's another package that
I'm confused with the statistical models and atmospheric models.
Yes, yeah, statistical models are doesn't use it's not based on the physics. Okay, it's not based. We don't have like nature phenomena, and we describe it with equations. Statistical models.
Long-term trends. So
Yeah.
time series of
based on
Yeah.
data.
So they are exactly data-based models.
Yes, and that a numerical result for this data is a kind of data. I don't like to say so. I know that it's I don't know what's this word in English. It's a kind of the type of the language that people that use a numerical model says that they usually say, for example, that numerical results from a climatological basis, some reanalysis of data. I don't like to say data because it's a mixture between, I think that even said about this, but it's a mixture between the data, the observational data, and numerical model. So for me, it's a numerical result. It's not a pure data observation. I know that people said using the same data. And so a numerical result could be used as a data, as an input in a statistical model. So have a kind of performance.
To go to regional scale, and it's more efficient using the regional scale and the time series than like going already. That's
Yes, of course.
that's why I'm trying to see what model can fit more the data.
I think that every choice that we have dealing with American model depends on the forecast, depends on the demands and your availability of tools and data that you have in mind, and the demands of the response that you must have. For example, if you're in operational modes, you need to be faster. And maybe sometimes if you don't have a big completion structure to run these testing schemes that Viva showed to us, you need to find another way. Of course, always knowing about the limitation of the things that you are applying. So for example, most of these global models at the Copernicus, for example, you can find operational models in 9-kilometer resolution in the whole global ocean. So it's going to be very useful for many different purposes that you have relating to coastal resilience. And that's there. It's already for you to use, okay? Maybe if you want to study the process that occurs in a coastal lagoon in your country, you need to have a local grid numerical model.
The information is missed. We know local, almost are missed. So it's
complicated. Yeah, I understand.
Okay, sorry, any questions here?
No problem.
Because Olga Milenko has a question about the coupler. I think that
The coupler always part of bigger model, but I want to close that one up as well.
I think that if I understood, she's asking, Olga, please, if I am wrong, please set me. But if we understood, you are asking if it's always necessary to run a coupler model, or if you can use not couple models to answer some questions. That's it?
Is that it?
Olga?
She's typing.
Okay.
Yes.
Yes, Mr.
Go ahead.
I like Paulo in Italian.
Paulo.
I like it. Okay, Olga. No, it depends on your demand. Of course, the representation of phenomenon in coastal areas, as I mentioned the first part of our class today, most of the times coupled processes. You have a very complex region that you have land processes, ocean processes, and atmospheric. Are you hearing me? Yes. You have. Yes. Okay. You have land processes, ocean processes, and atmospheric process occurring together, and not only occurring together, but interacting and transfer energy from one component to other components. So if you have the opportunity to use coupler simulations, it's better. But if you don't have the option to use a couple model, you can try to integrate this regional model. For example, you can run oceanographic model forced on the ocean-atmosphere interface by atmospheric regional model. You not be coupled, but you'll be integrating information of the atmosphere with more resolution that you would have if you use, for example, a global reanalysis data set. So these are things that could be done in order to increase the consistency of your results. But if you compare with in situ data, maybe you have good results, but it's not so complete in a physical way when you use fully coupled models, okay, ocean atmosphere and models.
Okay. I think we can go to Albert.
Before we go, we need the first official picture.
Okay, great.
So let me see where can I find Nadia. Yeah, we'll. I don't know how they're going to do some magic because I don't know how we will fit in here. I don't think we will, but. Teixeirinha, você acha que todo mundo cabe aqui, tu acha? Todo mundo
Nesse momento, eu acho que seria legal se o pessoal abrisse a câmera e aí
É verdade.
transferir o vídeo para o final.
Pessoal de lá também?
Eu acho que vai ter que dar uma foto para eles também. Pelo menos hoje a gente faz uma lá e depois faz uma montagem para aqui.
A gente pode fazer frente, não?
Pode ser também.
Frente,
Frente.
Are you on remote? Can we do a first official photo? If you were kind enough to turn on your cameras, we can do a print screen with all of us here. If it's possible. No, yes. Let's do it anyway.
But we have people online, don't we?
Yeah.
Yes, but
Yeah.
One.
Hey. Hi, Olga.
Yeah.
Nice to see you. I'm tipping.
See my hand here.
I look forward to the back. The pictures?
Yeah, the first of all.
Okay, yeah.
Has to be first of a series.
Okay.
Você consegue aí, Raquel? Tirar um print?
Yeah, yeah. To the other side, yeah.
The other side. Yeah, what's you wanna do? What is that's okay, olha, all of this, don't matter.
So no success with the print screen, right? But we'll go with Olga.
Yeah.
Stay in.
At the middle, you're the coaches.
Okay, so 1, 2, 3, cheese. Okay, wait. Okay. Another one. 1, 2, 3, cheese. No, wait.
Yeah, save it.
Cheese.
No, there are others, but there are
Open your cameras.
One more. 1, 2, 3. Nice. Thank you.
Thank you.
Now let's have a real one over here.
Okay, another one.
Podemos ir todos para lá?
Yes.
Thank you, Olga.
Tá bom, Dilene?
Bem melhor.
Vamos mais uma? Alguém mais abriu a câmera? One more with the remote. Come on, one more. Gather. One more with the remote. Big smiles. 1, 2, 3. Go.
Please.
One more. 1, 2, 3. Yay. Thank you.
So how we're gonna fit here, Teixeira, but say we can do it? What's the idea? You're the photographer. But how?
Aí vai ter que voltar as cadeiras, eu acho. Não, fica todo mundo na frente.
Isso.
Okay. So we come back with it. Okay, so let's try to take a picture, all of us here, please.
Come on, it's before coffee break.
Teixeira,
We are still playing.
não acha melhor lá fora, não? Tem mais espaço.
Should have good
Eu acho que precisa chegar mais próximo. Chegar próximo, tá bom. Não precisa todo mundo encostar na parede, precisa? É isso, a gente consegue.
Move this.
Take out the table and put the chair farther in the space there. Thank you. Where is you? Oh, it's here.
But where did he go? He was supposed to be in class.
Yes.
Tem como o pessoal ficar abaixado aqui na frente, ali, assim? Tem como fechar essas tampas do laptop? O pessoal ficar aqui.
Sure. So you want one layer in front, one layer in the back.
Short ones. Short ones in front. If you can, please. Thank you.
I should do that, but I won't come back.
It's a one-way trip.
Never like you.
Pleasure speak. No, you're fine. You're fine.
So, hello, let's go and start the second part of this afternoon, our first day of the course, okay? So now, we've been planning very well the activities of this afternoon, but we like to show to you some examples of application of numerical, physical, oceanographic, or if you prefer, hydrodynamic models for different purposes. So here we will show an example of a global ocean model application for academic purpose. In fact, was the master degree thesis some years ago. And I will show an application for specific demands to attend some demands related with nautical sports in Guanabara Bay. During the year of 2014, 2 years before the Rio Olympic Games, Rio de Janeiro Olympic Games, we were, the people from the Brazilian Olympic Committee just looked for us to try to develop to them a marine and atmospheric forecast computational system for Guanabara Bay region. And why Guanabara Bay region? Because the Guanabara Bay region will be the place of the sail races, okay? And then I will talk a little bit about the developments that involve not only physical numerical modeling, but acquisition of in situ data sets, and how we deal with this both information to provide the athletes and the coaches with information that they could use in a strategic way for the races, okay? So let's go. So the name of the project was Nautical Strategy, okay? And the proposal, as I said to you, as I mentioned, was to feed the Olympic sail team of Brazil with strategy information about the currents and the winds inside Guanabara Bay. Okay, and Guanabara Bay is a very, I learned this during the games. I'm not a sailor, okay, but people said that is a very complex place to sail because you have some mountains. So the orography affects the wind direction and intensity. You have a strong influence of tidal currents, and it's a kind of difficult road to sail, okay? You need to know these things. And if you have this information in a detailed way, it's useful for these guys that sails inside Guanabara Bay. So that's it. The project started 2 years before, in order to acquire data and to implement the models. And one very important thing that is important for you guys related with this course, there is the communication to the end user. This is very important to know, because here we are in a high level meeting, okay? And we talk about physics, dynamics, but most of the times we want to use this knowledge to produce information that could be useful for the end user. That could be a fisherman, that could be athletes, that could be a stakeholder that needs to proceed with alert to the society. So we need to talk the same language. We need to know how to translate. And this was a very nice experience, because when I talk with the sailors, for example, I use it to say, for example, the velocity of meters per second. If you don't know this, they're nuts. Okay? Evidently, for them, not for me. And then we learn with that. And we learn to talk with them also, because they are the guys that give to us after each day the idea of, and what about the forecast today? It was good, it's not good. What happened? Sometimes it was a little difficult, but some of them acquired some data for us of currents. So it was a very nice experience. But let's go. So we have different research activities, divisional atmospheric modeling, regional oceanographic modeling that was integrated, okay? We use, not in a coupled way, but integrated way, use the outputs of the atmospheric model, for example, to feed the regional oceanographic model with the winds near the sea surface, okay? And we have a meta-ocean data acquisition system. And this was another very nice experience because we must deal with a thing called vandalism. I think this is common to any place around the world. And of course, here in the Guanabara Bay is described the same. I will show to you. And we use this data to evaluate each day the forecast that we did one day before using an index that I will show to you. Okay. Of course, I take this presentation from a conference that I participated in 2018 in Algarve, Portugal. So that's why it goes in the paper, because I must send a paper of this. Okay. So we are located at the southeast region of Brazil, as you already know. We mentioned a lot our location here in Brazil. This is the Guanabara Bay. Okay, we are here at the University City. These polygons, these areas that we're seeing in black lines here, demonstrate the race courses that we have inside Guanabara Bay. I don't know if anyone knows how works sail competition, but you have different sail courses that you have a lot of classes of boats, okay? 10 or 12 classes of boats. And the competitions occurs at the same time in each of these race courses, okay? So with different classes. So the idea is to provide the athletes and the coach with the real-time information and the forecast information about the currents and the winds in these race courses. But of course, as I mentioned to you before, the most important ocean forces in Guanabara Bay are tides in first place and winds. Okay, winds are important more at the bottom of the bay, but sometimes during the, how can I say this word in English? When you have the high tides, we call it in Brazil, estofo da maré. I don't know how to say in English. I don't know how to have it. But when the tides reach, when the tides reach the highest level, okay? The peak. Tide peak. Thank you very much. Tide peak or the tide peak at low tides, the currents are very low. At this time, if you have strong winds, they will act at the circulation, and it's very important to know. Okay. So these are the places. Okay, this is a tide register for the period that you have the competition, 9 August to 19 August. Okay, so you can see here that you are at the end of this period, you enter in the high amplitude phase of the moon. Okay, with currents more strong, and in the beginning you are in the nip side, so not so strong. You have mixed semi-junior tides, flood currents, more intense than currents, most intense currents aligning in the main navigation. These colors represent the bathymetry of the place. Okay, you have a river discharge with a semi-annual variability pattern, and that's it. Okay, an area near the bay mouth could be strongly influenced by the nearshore currents. So these are some characteristics of the place. Atmospheric characteristics, wind regime is influenced by different temporal and spatial scale meteorological processes. You have going from the large scale atmospheric features to the micro scales or meso scales. You have first the South Atlantic subtropical height is a high pressure system that is associated with the anticyclone atmospheric gyres here in the South Atlantic. So you have north and northeast wind in our region that is mostly affected by this feature, this large feature. You have the passage of cold fronts that invert the direction of the winds from the northeast to southwest direction. Okay, these cold fronts are associated with extratropical cyclones that I showed you before. Okay, and you have sea land breezes. There is a phenomenon that sometimes could modulate the intensity of the wind in this area, especially near the coast, and it's very important to understand some patterns also.
related with the atmospheric circulation. And of course, the ideal thing is necessity of multiple modeling approach that, of course, we didn't have at that occasion. And I will show what we have. So this is the place, Guanabara Bay. And now talking about, I think that you remember this picture that Liva just showed to you. This is the nesting scheme that you have. In fact, here was 3 kilometer and not 1 kilometer grid. We had some weather stations inside Guanabara Bay. These 2 points, because 2 points you have 2 airports. Here, the international airport where you arrived, I think so, the Galeão or Tom Jobim Airport. And here you have the Santos Dumont Airport. So you have 2 places where you acquire continuously and you have freely available data winds in this region. So this was very important for us in order to do the model evaluation. Which day we looked at the day before and compare the data that was observed in these 2 places with our model results to see if you are near or no from the reality that was observed. Talk about the regional ocean model that we applied here, our regional hydrodynamic model, which runs with 4 nested grids, 1 kilometer, 200 meters, 100 meters, and 40 meters. Found the initial condition terms for Copernicus. Okay, we use the tide model TPXO that I showed to you, and we use as atmospheric boundary conditions the results from Earth model. Okay, these are the design of the nesting grids that we use it. Okay, so we put the high resolution, of course, in that region where we have the race courses. Okay, because it was our target. 3 no is 4. Okay, I put here only the 200 meters, but we have one of 100 meters that comes from the 40 meters. This is wrong also. This is the 40 meters. Oh no, that's right. It's 100 meters. Sorry about that. This is the 40 meters. And then you have here, you can see here, when you pass the 100 meters to 40 meters, you can start to reproduce some recirculations inside the Guanabara Bay that you're not able to represent in a coarse resolution. And this recirculation, for example, is associated with this island here, Laje Island, to a kind of a shadow during the high tides, okay, and produce this kind of circulation. And this is terrible for the people who are sailing there with low winds, okay? There sometimes the sailors are captured by this circulation that stay there for a long time. So this grid was evaluated at that time. This was not evaluated. Here we have the 2 weather stations that I told you. Okay, so we have these 2 stations and these 2 weather stations. Okay, that's very important because you have different characteristics of the wind that blows here and here. Here you have much more influence of the sea breeze than here inside the Guanabara Bay. Okay? So it's important to have these 2 points to see if the model was able to reproduce these different characteristics of the wind field. And talking about the oceanographic data, we install. Here's the island that is just in the middle of the mouth of Guanabara Bay. It's a kind of fort, okay? Some years ago we have a kind of, I don't know how to say, canyon. Can, okay? Don't have more. But we use this installation to, we have a structure, electronic structure that transmits the data from a DCP that was here, 24 meters depth, and a weather station that was here also too. Both of equipment for 2 times in 4 months were analyzed. But we want to keep them working during the Olympic Games. Okay?
That was the important thing. And we use this data to evaluate also our operational model. Okay, this is an example of the time series plot of current magnitude and direction acquired by our ATCP. Okay, and this is a skill core index that we used, that is in the Shu et al. 2011 paper, that we use it to evaluate the performance of our model. So this is very important because, for example, here we compare time series plots of the astronomical tide that was easy to forecast, okay, because it depends on astronomical forcing, with what the model see reflects. So we can compare this and see if the model is representing well the sea level. And we apply this also to the current fields. So at the end, the skill score index gives to us a percentage of how the model results are aligned with observational data. So this was very important because even when the model were not capable to capture well the observational behavior, we need to communicate with the team. Today, our forecast model is not so good. Do whatever you want with this information, okay? This is very important. And nobody likes to hear this from the people who model and forecast. Nobody likes to hear, I have an uncertainty of 25, 30%, but this is the reality. I prefer to sleep well. Okay, I give you the, if you like to, if you want to be confident with my results, I think that I need to show you also the limitation of the results. Okay, this is very important. I'm talking about sports, but I could be talking about extreme weather events and a decision that a guy must do of removing a community from a place because of an atmospheric condition. So if I have 25% of uncertainty, if I was the guy that needs to decide this, I would decide to remove, of course.
I do appreciate you brought up this topic.
Sorry?
I do appreciate you bringing up this topic of attempting to communicate the advantages and disadvantages and limitations of these things.
Yes.
In my experience, I've been asked to, find oceanographic data to run models for them. I explained that, okay, if I am to do this, I need equipment A, B, and C, because they've been reluctant to do so. Because they claim that, well, there's no return on investment, which of course is silly. But how would you convince the powers that be that you need to invest time and money into this before you can potentially make money out of it? It's very, very, very difficult.
It's a challenge anywhere around the world. And, I think that sometimes for the guys who really have the financial power to feed this kind of initiative, you must talk about money. How much money you lose without this? And of course, the human lives. Yeah, of course.
Yeah. We have a difficulty in understanding things in terms of the money that we lose. We understand things better in terms of the money we make. So again, with this, you have to wait a day or two, a year before you have information, before you can tell them anything. So how do you inform the people who's hiring you for this that you can't get the information today? You have to wait. You have to wait 3 weeks, a month. How do you convince them that you have to wait?
Trying to show to us that if they wait 3 months, 2 months to implement this kind of systems, they will decrease the level of insurance. Okay. I think that's the idea. And I think that you can plan to install kind of this initiative in thinking degrees of development. For example, Lívia showed to us an example of using climate global models. That is not exactly the better information to use in coastal resilience problems. But this is information that you have in hands. It's better to have an information and of course know the limitations, but we can offer to people. I see a very strong weather events coming to my region. I don't have the high resolution to see how it will exactly affect my region, but I have this information. So this could be the first phase. Let's work with what we have in hands now. And then we start to convince these people that, oh, I can increase the level of confidence applying a system like that, acquiring all the data, okay? I don't know, maybe it's a kind of utopia, what I'm saying, but I think that you must believe in that, otherwise, nothing can be done. Okay. Let's go. And that's it. The skill core index presents a percentage of certainty of the model results, okay? And this is a website that we produced for them. In fact, our contact were not with the athletes, were with the coaches, okay? And so the coaches take the information and help us to translate this information in the same language, okay, to the sailors that will use this information in the race courses, okay? So in this site, you have marine forecast, atmospheric forecast, real-time observations, forecast evaluation, and we have the opportunity to hear from the coaches what they think about the last forecast in order to plus could use this information to improve our next results, okay? And you saw here there is sailor, but we apply this system, the results also for the aquatic marathon and the triathlon, because we have to swim in Copacabana Beach, and say them rowing, and at Lagoa de Freitas also too, because the wind affects the conditions of the surface of the water surface at the lagoon.
Is the website still online or no?
I think no.
Maybe it was just for the Olympics.
Yes, no. Our group, our information technology group developed this. I don't know if they keep online. I think no. And we also produces a version to having cell phones and iPads, because most of the coaches stay in a boat near the competitors, looking at the screen, and the wind will change. This is how the fluxogram, okay, the framework of our system. So I have atmospheric boundary conditions, feeding our atmospheric modeling system, that feed in boundary conditions our ocean modeling system, that also was fed by ocean boundary conditions from Copernicus, okay, and tidal model, TPXO. With at the end of the project, and here the competition to have the acquisition of meteorological oceanographic observations to evaluate our system. And then with the evaluation, we fill the website with this information, okay? And then look the coaches and athletes observations. Sometimes, only sometimes, they feed us with their feedbacks also too, because there's another problem. There's the communication and there is the culture also. The culture of the sailors, at least from Brazil, at that time, they don't believe too much in this forecast. They look, no, this doesn't work. Okay. But no, they prefer to go there and see the clouds. And that's it. And what I can say, sometimes it works. Okay. This is nice to hear also. Last week I was in a meeting promoted by Federal University, and I was together with some, how can we say, indigenous people, and we're talking about, I was talking about science, modern science, and they were talking about traditional science. And we must create bridges between the traditional and the modern science. Of course, they can learn with us, and of course, we can learn with that. And so I'm bringing this just to think that the communication with the athletes is very important in order to grow, for example, this culture that they don't believe in forecasts made by computers, okay? And this is important also for you. Convince the guys that things work
and break the culture. We need to bring to the community, the civil society, the idea of how it's important to understand the ocean processes for their day life. Okay, this is very important. I think this is one of the lines that the Decade of the Oceans promotes: dialogue, strengthening the dialogues.
Did the project change their opinion?
What? Some of that, yes, because as I will show, we have at least one very small piece of the gold medal. But not all of them. But there is another explication here in Brazil. At least in 2016, most of our sailor team was made composed by amateurs. They're not professionals. Okay, and what we saw during and before the Olympic Games, that each foreign team, from British, from United States, from Holland, they have their own forecast teams.
But they could not evaluate.
Yeah, we can talk about this because they were not, because when there is a competition, the Federal Sailor Association, International Sailor Association, says the following: I will acquire this data here, and this data will be available for everyone, okay? Everyone starting in the same place. But what happened is that the British, the American team, the Holland team had a lot of equipment and started to acquire data by themselves and didn't share this information with anyone. That's it. So let's go. Here we have, here, because as I said to you, these are some statistics, root mean square error, the bias and correlations that we did, because I took this presentation now, and as I said to you, it came from a presentation that I did for a paper that was associated with a conference in Portugal in 2018, okay? So these are some comparisons showing that the winds that was forecast by the model overestimate the speed that was observed, okay? Northeasterly and easterly winds are more frequently in the results, so are better represented. South winds are more frequent in the observed data. So there are things that we need to learn at that location in order to improve our atmospheric forecast model. And here it is important. Our atmospheric model has 1 kilometer resolution. And so our atmospheric model was not able to represent well one very popular mountain here in Brazil called Sugarloaf. Sugarloaf is just a very tourist place, okay? And the Sugarloaf stays near the mouth of Guanabara Bay and represents a barrier for some winds that came from the south and southwest directions. So if you do not have the right resolution to represent these mountains, you will not represent this barrier effect. It's a problem that we have. Okay. This was another comparison between the ocean model and the DCP and the bias. So as we saw, the DCP could capture in that point stronger currents than our model was representing. These are some velocity distribution patterns that agree with observation. Of course, I showed the good results. But as I mentioned to you, we had also better results. And this is planned. As I showed to you, as I mentioned to you, there is at that time was the first Olympic gold medal of these two girls here. And now they are 2 times Olympic champion. They won the medal in the other Olympic game. But in this game, this team really used our system. And so that's why I drew that this one small piece of the gold medal is for our laboratory.
And because of that, Luis Paulo, the Olympic Games were here in Rio. So Luis Paulo got a gold medal in our lab. So it's our gold medal as well.
Good method. Good method. Okay, and this other important thing that's happened, and these are the opportunities that came. This system stay alive since 2016, and now this system evolved, of course, during these years, and now we have just signed a project with the state government of Rio de Janeiro to have an operational system to Guanabara Bay waters, to monitor the Guanabara Bay water movements and atmosphere movements. We have the opportunity to have some funds to acquire weather stations and to acquire some oceanographic data to be used to evaluate our model results. And this is happening just at the end of last year. So we need to persevere. 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 It's important. Okay, so this is one of the applications that I want to show to you, related not with coastal resilience, of course, it's related to sports, but of course, all of the results that were acquired here could be used to be integrated with social, economical information in order to understand the vulnerability and the coastal resilience of the communities that are distributed around Guanabara Bay region. Now I pass the floor to Lívia. No?
There's your.
Yeah? Okay. Okay, still myself. This is another application. This was very old application, but I think for the purpose of our course is okay. This for when I did my doctorate thesis, okay, here in Federal University of Rio de Janeiro. And what I did was to apply an ocean global numerical model called a modular ocean model that is a public, has its public code. The computational code is public, okay? And the interest was to understand how El Nino impacts the circulation in the South Atlantic Basin. Okay, this is the idea. So I did. Let's go. Now, how it started with this? The question: would the heat transport and volume transport over the South Atlantic Ocean be influenced by local wind stress variability during an ENSO event? This is one of the questions that I want to respond. And if you remember the first slides of our class today, these are the questions that you must do. What is your demand? My demand was in this scale, space scale, time scale. Okay. So why use the computational ocean modeling? Why use the climate ocean modeling? Possibility to investigate separately the effect of the wind over the ocean transport. This is very important. Also, physical numerical model permits to have all of the factors that could affect the ocean dynamics there. Suppose you want to investigate only one specific aspect, how this one specific aspect could affect this. One of the powerful of this numerical model is that you can do the unperceived this kind of investigation. Okay, you can just, for example, turn off the other forcing and continue to turn on one forcing and see how it will affect or do the opposite thing. So how to apply this method? Execution of two different numerical experiments. I executed one climate experiment. The climate experiment has the main goal to obtain the ocean climate from the application of cyclic boundary conditions in time. What I did is, as Lívia mentioned to you, I start the model with a mass field in the whole water column, the whole ocean, global ocean, with climatological wind stress field and radiation field, and all the forces that atmospheric pass to the or interchange with the ocean. Okay, and then I simulate for some years to the model be stable, sterilized, and when the result was stabilized, now I can use this to see if the model is able to reproduce the ocean climate conditions not only for the Atlantic Ocean, but for other ocean lakes. If it could represent, okay, he will be my standard benchmark, okay, he will be my standard level to compare with the other simulation that I will do, that I call it perturbed experiments. So they take anomalous ocean transport associated with anisotrophic wind stress field. Then I start this other experiment, altering the wind stress field over the sea surface. By the way, it happens when we have an El Niño event, okay? And see what was the difference. Estimated difference or anomalies. So this is a framework. So to do the climate, I initialize the model with sea surface rate fields, temperature salinity fields, zonal and regional velocity fields, with some boundary conditions, short wave radiation flux, long wave radiation. The components that compose what we call the ocean heat balance. Okay, so we have the turbulent, short wave, long wave, latent and sensible heat. We have the balance of mass, of course, precipitation, runoff, and wind stress fields. So, doing this, I have my control experience. With the control experience, I took some results that I use as initial conditions of my perturbed experience. That now uses perturbed boundary conditions related with the wind stress field. The wind stress field type that happens when I am weak. Okay, I based my wind stress field in a specific El Niño that was the 82, 83. Okay. Why I do this? Because I want to. We can use any other cancel type. And my supervisor. And my supervisor also said to results. And then I will be able, with this result and this result, to estimate the anomalies and see if I have anomalies related to the heat and volume transfer fields. So these are some characteristics of a MOL model. I think that some of these characteristics Viva said. We have a tripolar grid type. So you see that it's a kind of a scalp that you have here in the 60-degree north because of the convergence of the meridians. So you have a tripolar grid, artificial, you have two numeric artificial poles here. Oh, no problem. And the idea is to avoid this perturbation related with the conversion of the meridians and represent well the circulation at the Arctic. That's so important for us to understand, for example, the formation of Atlantic deep water. Okay? And at the south hemisphere, you don't have to struggle because you have a continent. Okay? The Arctic, Antarctica. What else? What else? I think that's it. It's a Z-coordinate vertical model. What are you going to talk about? You did talk about that. Okay, but this even show to us how you can use how can we deal with horizontal resolution. But our models are three-dimensional. So you must deal also with the vertical resolution, and there is some classes of how to discretize in the vertical dimension of these models. We have the hand-following models that represents well the topography, the bottom topography. You have the isopycnal models that adjust the vertical resolution of the isopycnal lines, isopycnal surface, and you have the Z models that only just uses the level, the depth level meters to refine the vertical grids. Okay, so MOL uses the Z-coordinates. I think that now the newer version uses a hybrid scheme. Okay, but this was the MOL 4. And this is the resolution, okay, in kilometers. So we have here 36 points in longitude, 200 points in latitude, because we have more resolution between 10 degrees north and 10 degrees south, and you have 50 levels in depth. So you have 3,600,000 points to be calculated, estimated. So this is, at that time, for our structuring computation was very demanded. We have a lot of demand to proceed with this experience. This is the vertical resolution, so we have 50 vertical levels. And most of the time, what we did in numerical modeling, as you see here, okay, here you have the depths, and here you have the number of levels. And you can see that near the sea surface, you have more resolution. Why? Because near the surface, you have most part of the process that have high frequency, that change a lot. So you need to have high space resolution to better represent, for example, the mixed layer, okay, the mixture layer, and the seasonal thermal cleans, and other processes that are very important to understand. And when you go to big depths, you don't need to have too much resolution, but things are more. Okay, let's go. And this is one thing that we use a lot to understand if a model is numerical stable or no. You just try to manage and observe how the kinetic energy associated with numerical results evolve with time. So here you have 7 years of simulation, and you see that since the beginning, you have a very good cycle of kinetic energy, ocean kinetic energy, okay? So if you think in our planet, where you have more ocean, at the southern hemisphere, okay? So you can see that the high ocean energies are in southern hemisphere winter. Yeah, that's it, because it's when we have more intense winds, and you have more ocean here in the southern hemisphere. And in the northern hemisphere, you have a tilt, small tilt, but you have more land, so the energy integrated is less. And you see this cycle that's just give us, if I trace a line, okay, you can see that it's almost stable. Almost. We have a small inclination associated with the boundary, because when I start the model, I use a density field inside water column that was produced with a different wind field. And I turn on the cyclic atmospheric boundary conditions different than the ones that generate the density field inside water column. So this explains this positive growth trend of 10 to 11, okay, watts per day. Too much energy, but when we compare with petawatts, it's very small. So I look at this graph, I look at the time that I had to finish my presentation. Is okay, let's go. I will take this year 7 as my climate's conclusion. And then I start to compare with the literature. Why I put this here, I don't know, but this is the wind field, atmospheric seasonal variability, that of course produces fields like this. So here you have the surface temperature field produced in my climate experiment. And you can see a lot of things that we know very well, like the tones of warmer and cold water near the boundaries with the continents, representing the continental, the circulation, the ocean circulation. Of course, this region will have warmer system phase temperature, okay? And that's it. And then I started to see the volume transport. And I start to compare with different articles, papers that I have available at that occasion, to see if my values were okay with the literature, scientific literature. Okay, so I divided the volume transfer in 3 levels. So here we have surface to 1,200 meters, then 1,200 meters to 3,000 meters, and 3,000 meters to 50,000 meters, okay? And the integrated one is this black arrow, and that is happen only here because you have the Antarctic polar currents, and almost all the transport of volume in this region is the same direction, almost, okay? I know that here, for example, have the stronger British current that against this flow, but when you integrate the whole water column, the resultant is always okay. And here you have the volume transport, 141, for example, spheres. Okay,
associated with the volume transfer of circular points. You have other behaviors that are very important here that could be associated directly with the MOC, the division of the cell, and the AMOC also too. I will show to you the heat transport also too. So you start to see, oh, okay, the climate that I'm generating with my model is okay. This is the heat transport. So here you have the circular currents. Here you have a very nice and important characteristic of the South Atlantic that exports heat to the North Atlantic. Okay, and I could reproduce this here, this zonal section. Okay, and we have here also this branch of the region of the itself, the heat that comes across Indonesia from Pacific to Indian Ocean. Okay, that's it. And this is, how can I explain this? Okay, these are the anomalies, okay? So it's the volume transfer anomaly. So here, when I have at the circumpolar current, the minus sign here represent that in the scenario that simulates the El Niño influence, decrease the volume transfer of the circular currents in 2 is value in this region and 4 is value in this region. And between the parentheses, I have the variability. Okay, so a lot of variabilities. So you can argue if the average is confident or not. Okay, but this was a result that I obtained. And then I have 2 other places an idea of what happened with the volume transfer. Here, for example, in Indonesia, I have an increase of 2 values 0.95. Okay. And when I look to the South Atlantic, here's the heats, the transport of heats, and this is the sea surface anomaly field of potential temperature. Okay, so here you have this scale that comes from minus 2 degrees Celsius to 1 degree Celsius between a year with El Niño and without El Niño. Okay, so you can see some features that are interesting here. For example, here, number 1, this is a 1 degree positive anomaly of sea surface temperature field. Here, this region where we have a very important ocean feature in our South Atlantic basin, that is the confluence Malvinas current and Brazil current. Okay, so we have a convergence zone with a warm current, with a cold current that just moves northward or southward in the summer and winter conditions. And when we have a variability, you can strengthen the Brazil currents and just push the warmer water more to the south, and then you create this sea surface temperature anomalies. And even though there is only the surface, it's a big area, and it's not only the surface. You have the water columns 10, 15 meters. So it's a lot of heat that is passed by the atmosphere. And this is directly associated with some anomalies that we have with the precipitation cycle in the continental area near here. Okay, so this is very important to understand. Other thing that you have is sea surface positive anomaly near South Africa associated with Agulhas current, maybe. You have negative anomalies in that area that you have strong upwelling near the coast of Africa, so you increase the upwelling that is. You have also cold anomalies near the southeast region of Brazil that maybe would be associated with the intensification of upwelling events. Okay. There are some papers and works that identify this process during El Niño. And here, negative anomalies in the northeast region of Brazil that could be also associated with less water vapor being passed by atmosphere and the dry, the increase of dry season here in the northeast region of Brazil during El Niño events also. So these are some results that I obtained in my thesis applying a global ocean numerical model. Okay? So very different purpose, very different application of numerical physical model different scales, time scale, okay, and different demands also too. And now Livia will show another application of a global ocean model. The same.
Yeah, the same one. Okay, this is some results of my thesis dissertation. So apply the same global numerical model as Luis, but with a different question. Now I wanted to see how the sea ice in the future conditions could affect the deep circulation in the Atlantic Ocean. So the meridional overturning circulation. Okay, so I applied the same initial and boundary conditions for the climate run. Okay, so the same ones as his. I had my control experiments, and then for my perturbed experiments, I forced the model with anomalous sea ice concentration, sea ice thickness. Actually, I took from IPCC projections the conditions from the 2100, okay, sea ice from the 2100, and forced the ocean model with that, and to run. So this was the experiment. So you can see it was a very old experiment. This was in
AR4.
Yeah,
Assessment report
AR4,
from
2014, so 2012 to 2014. So we have here the temperature change over the years of several experiments, climate projections from IPCC, and you see dashed red ones. The red one is the most, which shows a bigger temperature change. Yeah, it would be today would be the SSP 8.5 is the most with most GHG forcing, greenhouse gas forcing. So I took the year of 2100, and this would be the sea ice. This is the sea ice thickness of the year 2000, and then I took from the 2100 sea ice concentration and sea ice thickness to force the model. So here we have the comparison between the two. So in continuous lines, I have the control, the sea ice conditions in the control experiment. So in green for Antarctic and in blue for Arctic. And you see dashed lines would be the 2100 conditions. So very much less sea ice, both in concentration, in thickness. Concentration would be the area of the ocean covered by ice. Okay, it's a percentage variable. So you can see here that much more for the Arctic, we have a big difference here, both in concentration, thickness, and this is the dashed lines was the ones forced in the ocean. So these were the sections that I evaluated, all the Atlantic Ocean. So we wanted to see what goes in, what goes out, and what happens in the north-south part. So some results, I noticed changes in water mass thickness and associated transport. So that's in Portuguese, I'm sorry. So I have here the Antarctic intermediate water, there are 88 waters. The North Atlantic deep water, the one that is responsible for the AMOC formation. And we have Antarctic bottom water. Here just the North Atlantic water and intermediate water, intermediate, deep, and bottom. And you can see in black the control run, and in dashed red what
we found in the altered experiment. It looks like a little, but for the ocean, it's a lot. Okay, few meters of difference thickness of water mass is a lot for the ocean. Okay, so this north-south section as well, and you can see here some changes here along the ocean. Okay, but there's more interesting things. So this is a volume transport, the same way that Luis Paulo calculated. This one is for this section here. You take this, we are looking like this. So we have depth and latitude. So we're looking this section here, and we have the control, the perturbed experiment, and the anomaly between them. This one minus this one. So we don't have exact pattern, okay, but we have significant changes over this section, and this one is special because it's from where we have the Agulhas current here, and it leaks through this part. And would be this part. It gets stronger because it's negative. Okay, would be this part here. The Agulhas leakage. So the drink session, same thing. Now we can see a very distinct pattern. Okay, it's much more weaker. Okay, this the transport over here, and you can see here how weak this is, and also associated with the intermediate water. Yeah. So again, in this section here, we have a decreased volume transport. Okay. Decrease in eastward flow and increase of westward flow, as I said. This one here, the Agulhas current. And I think we have a slide. Oh yeah. So I isolated only the negative transport. You can see here for the northern part of this section, the only negative transport is associated with the Agulhas leakage. So I isolated it. And here, I plot only this part, okay, the Agulhas leakage. So exactly only what leaks from the Indian to the Atlantic Ocean, and we can see that it gets stronger. So I have more leakage from the Agulhas, from the Indian to the Atlantic Ocean. Okay, increase of 3%. So this is just a map of an overview of the volume transport. So the red one would be the control, and the blue one would be the anomaly. Okay. So if the arrow is in the opposite way, I have a weakness, weaker transport. If it's in the same way, I have a stronger transport. So we can see here, we have a weaker transport of the Antarctic circumpolar current, okay? And here I have a stronger transport towards the ocean, the South Ocean, South Atlantic Ocean. Okay, now for the heat transport. So in this section here, I have a decreased heat transport exiting the Atlantic Ocean, and a decrease in the North Atlantic deep water. So I have a decrease in the exportation of the North Atlantic deep water to the Indian Ocean, and I have an increase of the Agulhas current heat transport, which the Agulhas leaks from here and goes to the towards the North Atlantic Ocean. Okay, the same map, but for the heat transport. And we can see a decrease in the same way, but an increase in the export of heat towards the North Atlantic. So the North Atlantic continues to export heat towards the North Atlantic. Yeah. And that's it today. Do you have any questions?
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 Online audience, any question?
Oh, okay. So I think Francesco would
Yeah.
you go ahead. The floor is yours.
My computer. Let's see.
Do they need internet connection for that?
No, no.
No? Yeah?
More than the internet connection.
Okay, but for them, no? Okay. Okay.
That's nice.
We have a presentation here.
Yeah, when I recognize oh wait, his name is Swat. So I saw online. I didn't pay for it. I saw it
Tem que botar mais, hein? Segurou.
You should get to see their point. I know. I did Brazil and I find my pricing sometimes. Also, no. So like, of course, yes. Yeah, like I feel like every restaurant is like
Otherwise,
you don't need to know. They just continue the out and get out.
No, I just sent the
O número de Gabriel. Eu também não sei.
yes, yes. Good exercise. They will show you the output.
And the other how to search. You're supposed to take your interviews now.
I have the contact with George in 2019 to get more documentation about the business. That's like bit complicated.
To get the answers.
Yes. I've been there with you.
Yeah.
Yeah. It was like business. Like business. There was a lot of money.
Yes. Creating the WhatsApp group.
Ci siamo adesso, ci ho pensato che tutto di download. Ah, quindi non sono quindi
Quando
devo scaricare questo. Ah,
então fica tudo. Acho que foi.
how is your internet connection in your hotel? Slow or fast?
No, entendi.
In the hotel, you don't have, you don't.
Yeah,
Yes.
that is valid. I haven't tried it yet.
Maybe not actually tomorrow. So tomorrow you will fight with a model. So you will implement the right motion model. And to do that, you need to download this Docker image that is more or less 6-7 giga. And we will start tomorrow after lunch. So it will be perfect if after lunch you will have this image. So you can start download now. I try, and I think in 30 minutes here with this connection, info connection, so we can do. If you go to the hotel, perhaps all right, because it's a little bit slow. So just what we see, Nadia and Rodrigo, we talk about another this replay program in the morning for content related to operation oceanography by Nadia, and me and Rodrigo will have platform, one based on Nemo, a structured model, and one based on Scheinfeld, that is an structured model. And then after lunch, we will start. We have 3 hours to implement the model. And you will choose one. And now we can choose now if you want, which one is fair. And
I think it's good if we choose now because this way you can start now.
yeah, because
and the important thing is that we have the images on your computers for tomorrow, so you can start.
Okay, so I put on the table. So yeah, tomorrow we will talk about SORP, what it's doing, and SORP is an on-demand ocean modeling platform designed to facilitate the implementation of language. So we have 2 components, as I said, we sharpen, we apply many regions involved, and tomorrow we will apply in this area. And as I said, we distribute this platform to the curriculum technology called Docker, so container. So tomorrow we will download this container. This is a way to isolate the software. So you need to install nothing. You don't need to install library dependency. You just take this image, all the software is contained inside, code and library needed for the software. So by tomorrow, 2 steps. You need to install your Docker computer. Very easy. Just click will show now. By just 1 click. And then you have to pull the image from 6-7 giga of image by today. So now. So out of the Docker desktop, you just saw how to download Docker desktop on Google, but you just need to go to the Docker website, and you need to download the Docker desktop of your operational system. For example, this is an example of Mac. They will tell you have a Mac with Intel or a Mac with a Apple chip, and then you just download the file and follow the instruction. At the end, after the installation, you will have Docker desktop on a local machine that will look like this. Will be empty in the beginning, and then you will load our image, image of sufficient image. Tomorrow, we will do tomorrow. So just download the Docker desktop on your local machine, and then you have to choose one of these models we will do tomorrow. So we will do this area with structure model Nemo. And if you want, then choose one about bay using the structure model. How to download the image? You just because we release the new version, it is almost ready. We prepare an alpha version for this lecture. So it's not in our website still, but it's in our server. So you just need to download the image with this command get. If you have a operational system Intel, for example, you will use this command. If you have an operational system that does an ARM64, so the new M1 and 2 Mac, for example, you use get this command. If you want to use Shifem, use the same. Shifem is just available only on Intel chip. Yes, and yeah, so now let's decide. So I need the table with all of you, and I don't need to write. Actually, decide either what you want, then you download the image.
Yeah, one more question about the operational system.
Okay. So we always try with Linux and Mac, and actually, someone has Windows. Windows 3, 4.
There is online also.
There is online. Okay, perhaps Windows will work because actually the Docker image is also, but we have the Windows with the double partition. Because the Linux has double partition. No, it's not normally
For example, for Shifem, I will go into to use another distribution system like.
Okay, there is an option because actually we didn't try with Windows, but it will work if because we also have a virtual machine in our website. You can download the machine that has already the Docker desktop. You just have to put the image and work inside the virtual machine. So this is the option that actually we try once with React, and it should work. So for the Windows, you need also to download a machine that now I will tell you what to do. Is when our website, and for the other, you just choose your downstream experiment that you want to do, and just download this image. This one for the is the name. We downstream from a global distribution achievements products to high solution with using grid region 3, so we go from 9 kilometers to 2 kilometers. And here we use an abstraction action.
Yeah.
The both.
Yeah, you can try both. So I think once we have 3 hours, for 1 hour, I think one run we will do 8 days simulation, and it will take for Nemo 40 minutes. 30 minutes. So with if you also 4 courses, I don't know how many courses you have. For Shifem, it will take more or less 50 minutes.
50 minutes?
Yeah, for 50. So 1 hour now. And, yeah, the tool can also by default we have also the automatic download. We always download. We already download. You can take the data offline. Adjust 100 mega. We can take more.
So we download it tomorrow.
Now. Now you have to take the image at 7 giga. Tomorrow we will share this 100 megawatt in data. So just input the atmospheric and ocean
Okay.
So if you want. No,
It's what?
no, if you want to, because you can do after also the other one. If you want to do, I don't know, 50% do Nemo and the other one Schleifen, and then after you can also try at the other one, because actually if you're fast you can do also in a couple of hours.
What do you think about the pros and cons of each one?
For what? For the quality of the results or for
The complexity.
For the implementation? No, for all of it. Feel free to answer this. If we choose the first one,
if you are more interested to see a current aerospace cost area, choose the one.
Okay.
If you want to see all the patterns circulating in the area, how they interact, okay, so you can choose one. From this one, you will not see, I don't know, very well represented the current, but you will see there will be 90% interacting with the jet, so
It's more global model. Compared to
I think that's what it's just a suggestion.
but
For our course,
you can go
shipping is more.
it's more for coastal area.
Yeah, it's more for coastal area. It's just a suggestion, but I think that for our course, for the purpose of our course, coastal resilience, coastal process, shipping is Schleifen, sorry.
Oh, yeah.
I would choose Schleifen.
Schleifen in this little area.
Like you want more,
yeah.
you want more information about the offshore zone, so you can use Linux, for example. Schleifen is more for coastal areas, like for example the Spain.
Yeah, now you can also Schleifen globally if you want. You can also use Nemo when nesting does giving to resolve this area. This one I've done for practicality. Now we have a laptop. So we have, I think, more or less 8 giga of RAM or 16 giga. So we select.
I think it's interesting to do perhaps how if we can manage, because it's the application of what you presented in our lecture. We'll be doing a double nesting with Surfshark also, so even to interact between the groups. We'll use I already have the results of Francesco. So we'll be forcing the Surfshark simulation with the output of surfing. Yeah. So also to do there will be part of the group doing the whole nesting, and another part integrating with the global models, also mentioned by the professor in his presentation. So how.
Okay. That's okay.
Because we find a nice solution to was better to downstream via starting from this out.
Okay.
And is changed. So we tried the because and so the one that we use the one actually the way we use the output from the one. So already captured in this area, already prepared for you. So yeah, so these are here.
Half.
One. Okay. I don't know if you want to choose now. You go ahead and team. Oh, you want I think that whenever I very want to go solid. More resolution. More resolution, yes. No.
You are going to put the table?
Yeah. Just hands up the big.
Allora. Annabelle.
Yes, thank you.
Annabelle.
Then Scheiben?
Scheiben. It's called.
Thank you.
Exactly. I will do something.
Brandon.
One bar.
Apparently, we didn't get it yet. Oh my God, it's all two.
Gabriele.
Guanabara.
Okay. Guido.
Guanabara.
Agir.
Aja. Have you ever heard about the breathing? Very interesting. Very easier and it's very
José.
It's Santos. I don't think my computer is gonna run the Guanabara grid.
It's the lady. Oh, yeah, I told you. Yeah. There, so you can watch Brenda.
Yes. I will have a
Then you
good
exchange
picture.
things, yeah.
I have experience with Cyprus. I will go with Cyprus, sir.
I think the faster ones can
Yeah. It creates a virtual machine, right? Yeah. So, but it is still will run on my computer. It doesn't have a server.
No. Yeah, virtual machine with everything it needs. Yeah, good on my computer. I use that.
Bundles.
That's it.
Then online, online they can hear us.
Yeah, I think so.
Online,
Can I check very quickly? Yeah. I think so, otherwise they would have complained already. Yeah. You can, on remote, you can hear us, right? Oh, they all are answering. Bernard, GB, Olga, GB, Amina, GB. All of it.
Second grade. Yeah, so how helps you just
I think the rest of the house so now we have more Actually, online, if you have information tool, you can download both the image and the model. You can decide what to do. So now more or less in present we are 50-50 more or less. So, okay, so just download the image and
Yes. You have the link?
the link. The link is one. Actually, I don't know.
We have a way of sharing it. Or you copy it.
No,
Yeah.
of course. I can just use them to invite.
Yeah, you come, I come, I can come. She does the sharing. She goes.
For who has Windows, Windows. Yeah, we need also to download the virtual machine. More or less another 7 GB. 6 GB. 6 GB. And we'll have a link that I can show you. Okay.
Ah, sì. Ah, mica ne immagino. Ma da dove? Ah, capito. Non so come fai a usare. È probabile.
No, but you don't need to download check it. Okay, the virtual machine here in the one so you have a physical box, but then you can download that image.
Okay. Inside.
Yeah, when you want to use it, just set the device.
In the Google one? On the internet? I just have to.
So you just have to show you.
Okay, it's because this computer doesn't have accessing a lot of.
Okay. The one.
I think the other one has. Yeah.
Okay.
Just
The other one you need to download the image.
Okay. So the image. It's
all this download the
Okay, now I get it.
Then go kind of free match.
Okay.
In fact, you can download it on
It's easier.
yeah, you can. You have an extra program here.
Maybe you can assist me today.
You don't want to
And the normal
Because the link was not full, with everybody just, we never had like so many views to connect with cell phones and laptops together. That's such a big bad for people online. I try, I ask them to do.
Thank you.
now I have to look. This is the time that I do.
but I think all of this
As for IMG,
is now reserving results.
If I could do something, I'll do it together.
This is the best time.
Okay, so I get to install the.
Sim, fazer para a máquina de Yes. Sim. Acho que isso é uma vez. Agora, você tem a.
Ela tem, nem para passar.
Sim, o que você quiser.
Mas se eu quiser baixar isso aqui abaixo, tem baixo para
Virtual box is the software. Okay, so from the Windows, VirtualBox is software that you can download from the VirtualBox website, and then you take the image and send the image, full image for the VirtualBox, where you will find a unit.
Sim. Pela jogada, não estou não. Acho que eu lembrei, acho que eu outra que eles têm
Pronto, se você decidir baixar depois a Virtual Machine, o exercício na Windows, a gente tem um guia também no site do Surf, que é
Learning. Yeah.
Change.
Interesting. Not assigned if you stay in the you have access.
You can go to the gym, do some training, and after right?
Yes.
Okay, for example, a parte do Docker,
You design it?
Vai ter a primeira depois aí embaixo tem a Instalação alternativa, ok.
Valeu.
Por nada. Pode pesquisar. Sim, som.
Tomorrow.
They suggest me tomorrow, two of you, one that took Santos, the one that took the other one, they will in the end present like 10 minutes what you got, because they want to do beautiful. Okay. You show the results, I show some plot that they will do.
Two people have hands.
Amanhã você pegou.
Oh, it's not.
Eu acho que tá falando.
2 years ago. Here's my friend. Money is the reward. Two worlds, two worlds. Existence is a little bit small, like don't focus on one thing, make money every day. But as I come from, my western part of Africa, it doesn't work that way. You know to provide these things, you know. So, we start download, but this can be done tomorrow.
Yes.
Anyway. Like was especially during the beach. My interest making money. Money. And they just wake up, complaints, we shake hands and happens here. The first, like I didn't do that would be I think that it's from our so you to issue the ideas. About telling lies and not about what are you doing? I just do this thing. I said, no, there's no sending me anywhere. Not advice me. Oh, you're not gonna send me anymore. You know? I start advising myself. Oh, I joined them. You start making money. So, and then life goes well. Life was nice. Complicated. Yeah. Oh, just getting something for our life. I will check in. I think I have right now. I should like 5 days. You need to answer.
This question. I have am I solving any sort of problems or just what's the
Downloading things and doing some. You have to put in your support in the market, so that's one thing really trust.
Yes. Oh, no, that's
Oh, yeah, right.
Oh, no, I don't.
No, yeah, I'm losing time. Find a solution.
Aí ele iniciou com tudo. Não sei mais
No, wait, no, the virtual machine, it's okay, sorry. The virtual machine, but do not download the images from here, okay? Use the link, because it's the link is okay, there you have the 2.1.
Yeah, me, I mean,
Just when the virtual machine, it's okay. Yeah. Is that ouvindo outra vez? Não. Yeah. Docker, that's okay. It's called Docker, that's inside. I don't know what happened. I still oh, was not. Yes, was. You know that. Let me check this. I'm looking for the one that she's easy, right?
Let me ask you something. You are using this, right? Is it working normally?
Yeah, working on.
Okay, no problem.
Não baixou no extra. Não, ele não vai despachar, tinha botar o negócio baixando. Mas eles não deixam agora. Pois.
I think that it's
Ah, espera.
what it means.
You could start this.
I mean, I'm gonna try it.
Yes. It's the first video in this. Okay. Okay. So me is one. So. Okay. It's shy, right? No, but wait. Yes. Yes. But the virtual machine. Yeah.
This is visual.
Experience? Yeah, up here. Here. Yeah, up here. Okay.
Yes.
Okay. We can't use my Wi-Fi.
Oh, yeah.
I think.
No, this one I already know.
Porque mais eu acho que não, você quer só fazer, né? Eu te ensinei, eu sei. Eu esperei a
But it's like
You're eager.
like show me weight.
Não seja lá então, né? Não sei, acho que vai ser. Eu não concordo, eu sei.
It sounds good. Acho que uma solução vai ser mais fácil.
Are you brother Santos? Santos. Yes, I put Santos. Yeah, well.
Everyone's downloading.
Yeah, but did we start already? No?
Everyone's just downloading.
We are just downloading. I mean, I know it's from all the
Okay, so
yes, I installed first I'm gonna try to see what if it was already pode download. Eu estou não. Somebody the audio because it's like 12 gigas, right, or 15 gigas.
No lectura al santo, vamos a minimum is 7 GB. And then I will check because the much is from
No problem.
Okay, thanks for all of this. So you need
Okay.
So are we downloading them now or are we doing? So let's start sometime. We're coming tomorrow. You are here now. You are done.
I already downloaded this. Like, not the heaviest thing, but like half the weight. I'm gonna use the rest in the what do you mean with this one?
Importar ela no.
Yes, I don't have.
Se você vai importar ela, em vez de criar uma nova. Vai
one information processor. ARM57. Connect with the ARM54 processor.
Lá dentro já tem Docker.
Ainda não está in the clear share directly with the
Back with ARM64. With ARM6.
We are Intel one. It is common. There is just the
Intel 1.
Usually the Intel appears on the.
Yeah, they will check one from here.
The system?
It is F4 F2. So the Intel one, the other one.
Okay. So for those with MacBook, anyone with MacBook? No?
My case.
No? Rodrigo? No. Yeah, no, nobody.
Yeah, I think she
Yes. Mac.
but she has another
It's
problem.
not, okay, you're checking on her? The.
Yes,
Okay.
yes, there are problems.
No.
It's enough, but it's doesn't give support anymore, so you cannot install anything.
Oh. Okay. Huh?
Okay, so Linux, you are Linux.
Linux.
No Linux, no.
Yeah, on the virtual machine.
For machine, okay. Yeah,
I'm downloading.
yeah, but you need to download from the, you need to download.
I'm downloading the images.
Too legal for what, you know.
We're gonna try to put one or two cables to try to make it faster.
The surf images in the surf docker, right?
The space, just,
I'm doing this one.
One and the other one from the.
Okay, I'm already doing
Windows.
Yeah.
Bom? We need to download the virtual machine first.
Tá, eu. Não. Precisa da. If you're not in, it's a little
It's a surfboard. Okay, it's a company from Hawaii. Use and I saw it. Okay, it's John. It's a very famous surfer from Hawaii. Yeah, kind of. So he used it rent.
Oh yeah, I'm just worried about the internet speed here.
So you guys have been?
Did you already download? No. So yeah.
Downloading.
Hours. Okay. In the morning.
Otherwise,
Era um atalho.
Baixar uma imagem de máquina virtual e já vai instalar as soluções. Você vai importar eles.
Tá só internet para todo mundo. Ó, foi pra pensar agora.
I think it started. Okay, in the second one, I have it. I think it's going to be better. Okay, it's taking too long. It's going to take too long here. Her laptop is saying 7 hours. I'm not staying here. Yeah, I didn't even say that. What you are downloading, there isn't that much.
Gets faster and then
Não, mas eu
If you.
Recently, I bought from the store. Qual exercícios podem esquecer? São começando. Você vai
It's having fun.
We are going to right now. Sorry, yes, I interrupt. You have the possibility. If I don't be so right about the model, so
No, it's
you need to pause it. Ah, it's a also it's your starting.
But if I start to download now, it's like I'll put it close here. No, I'm just saying that when I quando chegar no hotel, eu faço. Na verdade, parece um estoque. Eu vou ter que fechar e vou
Você precisa baixar isso.
Esse.
Sim.
Não.
E anotar o wget, comandos
No terminal, né? Isso aí faz no terminal, né?
Tá, aí depois que eu baixo aquilo, eu boto no terminal.
Sim, você lança no terminal dentro da virtual machine. Tá. Precisa baixar em Linux.
Tá. Ixi, a vida dessa introdução aqui é o que meu olho.
Yes, it's the virtual machine. It's not the machine. Just the virtual machine. And once you get
Para fazer download e fechar. Ah, então não vai. Me deixa pegar o quê? Acho que está ligado de porta.
you launch inside the machine, you are downloading this is a regular one day left. So which one? Is it for me?
É isso aqui dentro desse da casinha. Esse nosso
Yeah.
ele tem de dois, mas é um flat. Ele não é uma casinha, entendeu?
The virtual machine is what
You have casinha, né?
already inside. Yeah. This one. The chip Windows is better.
Hi, can you show me your adapter? Your plug.
After the machine is already with a project, but has to be understood over time. If you arrive, you have to cut.
Yeah.
Yes.
Passa daqui. Let me see your computer.
No, this is for Manavel.
Yeah.
By the end of the formation tomorrow, you get.
Ah, é aquele de micro-ondas. Então,
Entendeu?
Aquele coisa. E agora eu na casa inteira. A minha coisa agora vai ter todos os. Mesmo problema da casinha, também não vai, né? Não vai. Tem que ter um desse, ó.
Tomorrow by the end of the
Tem que ser um adaptador universal. Maybe this one.
Yes, you can use it. Shut the gate. Are we going to make it this light?
I think so.
No, I think we not only, we could only,
It's gonna be faster.
turn on 3, that's right, just, only that one. Just to respond. Ela quer just turn on 3,
Sim. Yes, né? Mas eu acho que tá indo? Sim. 6 horas.
É amanhã de manhã, não é?
O meu tá 2. Não, mas tá bastante papo.
But you have
Ih, foi pra 3 horas, viu? A gente pode deixar baixinho, pode. A rede do hotel é boa? A rede do hotel é boa? Não é. Não.
Eu não testei ainda.
Toda hora tem que ficar acessando. Você sai do quarto e tem que acessar. Toda hora. Mas dentro do quarto, mas ela não está. Não, mas fica estável. Não, fica não, porque já você assistiu a opção do celular. Você bloqueia quando você acha que você não. O meu é assim. O meu é assim. O meu é assim. Como você acha?
Sim,
Pode tentar falar com o cara do desk lá do hotel. Oh, you're right. And then CNB.
This thing is a program.
Yes. Yeah, like never real. No. You go with
No, that's what I'm downloading now. Downloading it. Yes. With that one. No, with that. And then we can just.
We're gonna try with it. Yeah, perhaps to.
No.
No, English guys. No, don't have enough. Deixa eu estar abaixando o vai ficar tudo.
okay.
So how about it? How many? 3 days? Yeah. Okay, to 1 week. All right. Monday, 1 to 20. 1 day. Okay. Okay, tomorrow. Oh, 19. Yeah. We're complaining too much. Just 11 hours. 5.
Você vai deixar o computador aqui?
Okay, we have, yeah, we have these 2 hours. You can, what about live recording? Okay, maybe. But it has the cable, aberto para frente. You can leave your computer there. You can try to download and the hotel during the night. We can lock the doors so it's perfectly safe. Okay, if you want to.
Você trabalha
saiu de. Esse aqui que deixava chato. Poxa, eu queria ficar em casa, trabalhando, jogando. You have work summer today? Yeah. Yeah. Okay. Good try. Good try, né? Okay, so. Lá. How about you, Ruth? How many days? Hours? Yeah. Okay. Yes. Okay, so we have to download that. Tô fazendo there. Or if you want to. Eu pedi 2 horas para um dia, para 6 horas.
Computador remoto. Posso fechar o meu e tá rolando.
Olha que privilégio.
E agora? Ah, mas que porra, como é que eu vou tecnológico?
Feliz. How about you? No. Oh.
I realized
Okay.
have to.
Yeah, maybe in the hotel you can rotate the flash drive. Okay, there's one person here with flash drive. Maybe in the hotel you can also rotate the flash drive.
Because you have high resolution.
He has everything. He has everything. You have everything. All the images. You have all
I don't have any.
You don't what? I hope for all you.
No.
Yes.
Lembra que tem espaço para trás.
So, you don't have Is that Yeah, so you can exchange. Okay. No one is able to leave it.
I just figured if there's it's already
Two people $1 in flash drive.
So you know, I see your model.
Yeah.
Perfect.
You see, Santos. Já ajudava, né? Já tinha alguém.
How is it better now?
Yes.
Hours to download. Under control. We have things under control. Okay, so I think we have to. Okay, so get ready to go. Grab your garbages and if you have any. Can I get? Yeah, the same. What are we gonna do? The image is in your camera. You're gonna make your amigo, você não tem sobrenome? Não é o.
Normal eu uso só, né?
Também. Eu sempre uso só. Eu botei tudo.
Quando eu vi, eu falei, rapaz, ela chegou.
Can I pull the? It's not ours. Can I take pictures? Yes.
So we were, thank you for the people who can download, so the rest of the people.
Deixa os cartões que eu levo para casa.
We
overloaded the Wi-Fi.
But they can try the slide. What do you do this time? Nothing. Yeah. Oh, where? In Trieste, in the ICTP.
Yeah.
Yeah, that's right. How did you like it then? Because oh, yeah.
I wouldn't mind.
Yeah. Where are you now?
I'm in Morocco.
Yeah, we just talked this stuff. Sorry, but I see too many people. I'm old. I'm old. Old woman. I mean, very old. Yeah, so,
Sorry?
Okay,
I thought you were Franz, I just joined your team. I got my first alert that I'm running out of space.
You're late.
No, I can say that I am officially certain.
This is
This is your new version. I have fixed something. I'm not complicated. You know what I'm talking about? With Max. I tried to explain to you that yes. Windows. Users, people.
Hey everyone, are we ready to go? Oh God. Why?
Are you? What they grew up in.
Yeah, it's okay. Yes, it's a figure.
Prefers to spend more.